many reputed international and national journals. His areas of research include statistical modeling, stochastic process, time series modeling, distribution theory, sampling theory, queuing theory, reliability analysis, multivariate analysis, microarray modeling, and epidemiology. He will be discussing Bayesian inference and MCMC methods for detection of gravitational waves with us today. I welcome Dr. K. Jose. Sir, you have 30 minutes and 5 minutes discussion session thereafter.
Thank you, madam. Thank you, madam, for your nice words. So, first of all, good morning to all participants. Dr. C. Satish Kumar, the chairperson, the convener of this, organizing secretary of this program, then Professor Dharma Bhattacharya, and the co-speakers, Dr. Bhadra, Dr. Jayakumar. So here today, I will be sharing my paper. I hope you can see. Hello.
It is fine. Now you can make it slideshow mode. It is. Or otherwise full screen.
Okay. Full screen mode, sir.
If it is possible, please. That's good, sir.
Now it is visible?
Yeah, now it is visible. It's fine. No problem.
Sir. Okay, sir. So today's talk, my talk is on Bayesian inference and MCMC methods for detection of gravitational waves. Certainly, it is actually some application of statistics in physics. So this detection of gravitational waves, that was actually seminal work actually. So in 2017, the Nobel Prize in Physics was awarded to the discovery of gravitational waves actually. And that was actually shared between statisticians and physicists. And Barish and Thorne, they were physics actually, but they were good in statistics also. They have made use of statistical techniques for the discovery of gravitational waves. And all of you know the decisive contributions to the LIGO detector and the observation of gravitational waves. And this is actually the great discovery. So this is actually something which comes in fundamental problem in physics, cosmic chapters, cosmic charts, gravitational waves from colliding black holes. So something connected to physics, black holes, you know, solar masses, then of 29, then 36 solar masses, then some collision take place between these particles, then cosmic charts, some slight noises, you can say. So that is believed to be the beginning of the universe itself. So that is like, so this is the gravitational waves. This is actually the picture, the picture given by NASA.
Sir,
so observation of gravitational waves from a binary black hole merger.
Not changing probably.
Hello.
Sorry to interrupt, sir. I think your slides are not moving.
Okay. So you have to see me also. Okay, so I will. Some problem is there with the. Let me see.
If it is difficulty, they can.
Now you can see. Now it is about it is not coming to the full form. So anyway, so observation of gravitational waves, that was actually so this is the paper which appeared in Physical Review Letters in 2016, and you cannot see me. That is actually the problem. See? I will try my best. some problem. It's not moving, I think. What?
Now we can see the first page of that article.
Oh, only first page.
Yeah, observation of gravitational waves, that
Let me see.
physical regulators. Sir, you can stop sharing and we start it.
Represent this.
Okay, so then I have to send it to you. Okay?
Yeah.
Let's try. I will stop sharing. Once again, I will try.
Now we can be, it is visible. We just
visible.
check whether it is moving or not.
Let me try.
In case of difficulty, you please send.
Now it is visible?
Yeah, now it is moving.
Oh, so let me try with this. I think full sharing is not, full screen is not.
If you need, please send to me so that I shall share from here.
These are actually the waves, the electromagnetic waves. So now I will be coming to the introduction. So for decades after the formulation of Einstein's general theory of relativity, the notion of gravitational waves was a topic for speculations. So that was not theoretically proved. So physics believed that. So the scientists actually believed that, but there was no proof at all. So theoretical works during 1970s, 1990s advanced the popularity of gravitational waves. For the first time, scientists have observed ripples in the fabric of space-time called gravitational waves, arriving at the Earth from a catalyst event in a distant universe. This confirmed a major prediction for Albert Einstein's general theory of relativity of 1915. And this was observed in 2015 after 100 years. And this opened up an unprecedented new window onto the study of cosmos and scientific research. Gravitational waves carry information about their dramatic origins and about the nature of gravity that cannot otherwise be obtained. Physicists have concluded that the detected gravitational waves were produced during the final fraction of a second of the merger of two black holes to produce a single, more massive spinning black hole. So this collision of two black holes had been predicted but never observed. That was actually the importance of this. So it was predicted for many years, but never observed. The gravitational waves were detected on September 14th, 2015 by both of the twin laser interferometer gravitational wave observatory, that is LIGO. So located in Livingston, Louisiana, and Hanford, Washington, USA. So all these actually, the experiment was conducted at various places, and it was observed in these stations actually. And as far as this paper is concerned, this paper explains the mathematical theory on gravitational waves and the role of topology and tensor analysis, as well as the role of statisticians, especially Bayesian inference and Markov chain Monte Carlo methods in this discovery. So these gravitational waves represent propagating ripples in space-time. So that is actually a physical concept. So the importance of time also, that is actually what Einstein's theory brings out. So a propagating curvature perturbation, gravitational gravity, like electromagnetism, and all these are there. So that is actually causing these ripples. So everybody in the path of such a wave feels a tidal gravitational force that acts perpendicular to the wave's direction of propagation. And in general relativity, the gravitational field is described by the metric tensor alone. But in many other theories, one or more supplementary fields may be needed. And according to the general relativity theory, any distribution of mass bends the space-time fabric, and the Riemann tensor, which is a function of the metric tensor, and its first and second derivatives is a measure of the space-time curvature. And this paper will discuss on these things and the recent developments and insights on gravitational waves. So this is actually the astronomical phenomenon. So the gravitational wave astronomy. Now coming to the Newton's theory. So as far as Newton is concerned, Sir Isaac Newton invented the theory of relativity. All of you know the apple falling from the tree and why it is coming down. So Newton explained it as because of gravitation. But actually, gravity actually. So the Earth's attraction of any particle coming down. So, but it was not perfect actually. That was actually what Einstein said. So Einstein said it is because of general relativity, and he introduced the concept of space-time. Then matter causes this curvature. Space tells matter how to move. This looks to us like gravity. So for us, it is looking like gravity, but it is not actually gravity. That is what Einstein said, or Einstein's principle. So at that time, Newton had some prominence. So people believed Newton more, but Einstein's theory was found to be more correct. And after 1 century, after 100 years, it was proved actually to be correct also. So a brief history of gravitational waves that I am not discussing much. So I will come to the statistics part. The nature of gravity. So as far as Newton's theory is concerned, action at a distance, inverse square law. So we know that. So the Newton's law describes the effect of gravity, but does not explain it. But Einstein, for Einstein, gravity is space-time curvature. And he is giving the mathematical equation also. Any mass energy bends space-time. So when some particle falls down, so certainly the curvature will be there. So the freely falling objects follow the local background curvature. Then what are gravitational waves? Ripples in space-time, and so on. So I will come to the. These are actually the general relativity theory. I am not explaining that. So it is more mathematical and physics. So anyway, so when something falls on the floor, certainly there will be some ripples. Something falls. Suppose you put a stone in the water, certainly there will be ripples like waves. So how these waves are developed, that is actually argued here. So gravitational waves. So coming to gravitational waves sources different frequencies, different temporal patterns, different data analysis methods. All these are actually there, but the data analysis was not possible earlier. That is actually, and to be true. So the stochastic nature of this data, that is actually more important. That was being identified only very recently, and many mathematicians actually answered this, and they explained it through topology. Topology describes the properties that remain intact when an object is stretched, and the importance. So it is like elastic or rubber. So it can be stretched and so on, so that we will be having different shapes of this one. So that is actually one explanation for this using mathematical concept of tensor analysis and topology. And that was actually sufficient, but later on, physics also and statisticians also involved, and they found the random nature of this. And they actually went with the photographs and all these things, and these are actually the different stations that is put in. Then coming to gravitational wave detectors in space, gravitational waves. So here, what is important is actually the data analysis. So only by data analysis, only by estimating the parameters, etc., we can explain these things. Otherwise, it is just something which is hypothetical. So data analysis were in spiral, where continuous waves and stochastic sources were done, and data analysis was in progress. And finally, they detected the gravitational waves in 2015. So these are actually the waves, then different stages. And so you can come as here. So analysis of the first LIGO science data for stochastic gravitational waves. So that appeared in a paper in 2015. Then Bayesian semi-parametric power spectral density estimation with applications in gravitational wave data analysis, observation of gravitational waves from binary black hole merger. And this actually, the mathematical or the statistical work actually won the Nobel Prize. And the credit went to physics, actually, the principal investigators or the main scientists who are working on that. So gravitational wave data analysis and multi-messenger astronomy. Then, so the confidence interval, etc., they developed, and upper limits, lower limits, and so on. So all these are actually more statistical than physics. Then stochastic background, optimal filters. So we have to make use of such mathematical concepts or statistical techniques to analyze this data. And so the study actually, so this is, here is the paper which appeared in Physical Review. So Bayesian semi-parametric power spectral density estimation with applications in gravitational wave data analysis. So this is actually something, the data is something like a time series. So spectral density and other things, power spectral density, etc., are needed. Then Bayesian methodology is needed, and not parametric methods. So semi-parametric methods are needed. And this is actually a paper which appeared in Significance magazine. So published by Royal Statistical Society, Gravitational Waves, a statistical autopsy of a black hole merger. So this paper, which appeared in the Royal Statistical Society in 2016, that describes the importance of statisticians in detecting the gravitational waves. So that was by a statistician, Renate Meyer and Christine. So they developed, they were involved in this experiment, and this was actually published in Significance. So Significance is actually a journal by Royal Statistical Society for everybody. So the statistician's role, physics are rightly celebrating the achievement in determining gravitational waves, but behind the scenes, the statistician had a part to play. The aim of the parameter estimation group was to find out what caused the signal and where the astronomical event occurred. So that is actually the importance of statisticians. So the statistical theory of gravitational waves, standard assumptions about the noise model was actually Gaussian. So stationary and Gaussian, that was the standard assumption with a non-power spectral density. That is simple, the existing theory was there. A real gravitational wave data often depart from these assumptions, and it was demonstrated in their paper, and that fluctuations in the power spectral density can moderately bias, and this is actually because of the non-Gaussian nature of the waves. Actually, high amplitude non-Gaussian transients in real detector data invalidate the Gaussian noise assumption, and the misspecification of the parametric noise model could result in misleading inference and predictions. So this was actually the problem. So the assumption of Gaussianity was violated, and people have to, or the scientists had to look into non-Gaussian distributions, non-Gaussian situations, and so on. And the statistical assumption, so this was the model. In this study, we assumed that data are a sum of the signal plus noise. So S beta plus epsilon theta, something like the regression model. But here, epsilon theta, that is not following the normal distribution, is actually it's something which is following non-Gaussian distribution. And they conducted the frequency domain analysis, that is power spectral density function, and other things were developed actually. And when we come to accompany the non-stationary noise, we adopt an idea presented by Rosen and assume that a non-stationary time series can be broken down into smaller locally stationary segments. So there is actually some theorem, Brochen's theorem, which says that any stationary time series can be broken into a number of infinite number of stationary segments. But here, the non-stationary situation also is considered. Non-stationary time series can be broken down into smaller locally stationary segments, something like what you can say, something like considering different intervals. At different intervals, it may be stationary. So on the whole, it may not be stationary. That is a good thing. So using that, we can develop the spectrum also, time varying spectrum. So different spectrum for different time periods, you can say. And then we cannot make use of directly parametric methods. So we need actually non-parametric models also. And in that case, so you have to make use of linear and non-linear regression also. So the linear regression model is given, and that is also not sufficient actually. That was actually, so Bayesian non-parametric methods were actually developed by statisticians, and this actually helped actually. So Bayesian non-parametric contains the set of models on the interface between Bayesian framework and non-parametric statistics, and is characterized by large parameter spaces and probability measures over these spaces. The Bayesian statistical framework is useful for incorporating prior knowledge and is particularly powerful when these priors accurately represent our beliefs. So these are actually statistical part which most of you know. So prior information and distribution. So certainly some prior information is needed. So you know the posterior is actually proportional to the prior multiplied by the likelihood. So Bayesian non-parametric priors are stochastic processes rather than parametric distributions. So that is like the difficulty of this one. So here we are having time series. So it is not just classical data. So instead of parametric distributions, you have to consider stochastic processes. And Ferguson actually developed such a concept, Bayesian non-parametrics, and Dirichlet priors were actually made use of. And this is a popular model in many situations. A formal definition of the Dirichlet distribution and Dirichlet process are given in their paper. And then spectral density estimation, that is also a tedious but inverse computation actually, and Gibbs sampling. So Gibbs sampling and Markov chain Monte Carlo methods were combined together to estimate these values, and reconstruction of the signal. So after estimation, so to reconstruct a rotating core collapse gravitational wave signal that is embedded in noise, that was also a very difficult problem. So that was also answered by statisticians. So to reconstruct the signal from the estimated values, just like back forecasting, you can say. So MC Markov chain Monte Carlo methods, all of you, you know, that is part of our first course. I am not discussing much. So anyway, so we will be starting with prior distribution, then proceeding. So an embedded Markov chain will be created, and then we can estimate these are stationary distributions actually. So non-stationary noise. So that is actually the difficulty here. So there actually we are considering the time series broken down into locally stationary segments, and each segment we are estimating this. Non-Gaussian noise. So usually in time series analysis we are concerned with Gaussian noise, but very recently from 1980s onwards, these non-Gaussian time series models have been developed, and means and the diagonal process is having the structure xt equal to rho xt minus 1 plus epsilon t, and under Gaussianity assumption we have the spectral density function, but under non-Gaussianity only in the case of certain distribution that is exponential, then Laplace, etc. These spectral density functions are available, and here this LIGO, the scientific physics actually consider the Laplacian distribution actually. So asymmetric Laplace distribution actually. So these are actually the estimated power spectral values, and they actually made use of that for reconstructing the gravitational waves. So detection of gravitational waves. The detection of gravitational waves was a landmark moment for science, not for physics. So it was a landmark moment for all sciences and a testament of both theoretical physics and experimental physics. These ripples in the curvature of space-time were first predicted by Albert Einstein in 1916, but it took the technological heft and spectacular performance of the LIGO to confirm their existence. So the statisticians' role, the physics were celebrating this. The Bayesian parameter estimation methods were actually made use of, and that actually required the estimation of the parameters. So there was our role. Our usual methodology was not successful. Then this Markov chain Monte Carlo methods were actually made use of. It was during late 1990s that statisticians started to look at parameter estimation in the context of gravitational wave noises. So up to 1990s, statisticians were not at all involved, but many physics observed that these are random waves. So randomness is there, stochastic nature is there. So statisticians' involvement is a must, and they approached statisticians and they have developed this Bayesian approach, and they applied this Bayesian approach and MCMC methods. This was taken up by this LBC as well as cosmologists who embraced the Bayesian philosophy. Markov chain Monte Carlo methods actually quickly became the standard approach. We know in statistics also it is actually more important nowadays, gaining more importance in the data mining and data science and data analytics sector. And so the problem was the unpicking of the signal. The signal is to be signal is not there, cannot be observed actually. So only some chirps you can observe, some very mild noise you can observe. So this is like the gravitational wave signals detected by the Tim Liggio observations, and the signal detected by Liggio matched nicely with the prediction of general relativity. Bayesian parameter estimation methods would then provide the means to know more about the black holes that cause these ripples. Waveforms of two spiraling black holes are described actually. And the first step was to make some prior assumption about the likely parameters of the two black holes and to input these into the Markov chain Monte Carlo algorithm. And then in order to produce a configuration of parameter estimates, uniform priors was chosen. So actually they started with the uniform distribution as the prior. Then actually they changed it actually. And in the absence of any additional astrophysical constraints on the source, prior choices for the other parameters were non-informative. So uniform distribution is non-informative actually, you know. And the as far as the prior distribution was concerned, so they adopted a 13-dimensional parameter space. So it was a very complicated work actually done by statisticians. And however, the Bayesian approach to parameter estimation combined with Markov chain Monte Carlo methods made it possible to estimate the parameters of the black hole merger. And it provided the means to infer important characters such as the individual masses of the black holes and the final mass. And this analysis assumed that general relativity is correct and the waveform reconstruction gives no evidence against its validity. But Bayes factors have also been used to compare the relative fit of different waveforms, approximations derived by solving Einstein's equations. This is only the beginning of the story of gravitational waves. Studies are going on. The data analysis task. So the data analysis task was the most difficult one. Over the last 20 years, Bayesian parameter estimation methods have become the norm in helping to explain these processes. This is the combined efforts of all members of the parameter estimation group within the Liggio team made it possible to achieve the goal actually. And the parameter estimation, before we go further, however, it is helpful to clearly distinguish between the detection of gravitational waves and the subsequent analysis of their measurements. The independent measurements of the same signal of both Liggio detectors with a difference in arrival time of 7 milliseconds. So 7 milliseconds means very, very small duration. It is important. So that was actually the problem. So once a gravitational wave has been detected, it is important to estimate the parameters of the signal waveform as accurately as possible, and thereby bring its astrophysical characteristics of the cosmic event that it caused it. Parameter estimation made it possible to infer that what caused the detect gravitational wave was indeed the merger of two black holes. And this actually often developed a lot of statistical inference. Certainly in years to come, certainly we will be having more role in this aspect. So statistical modeling. So binary modeling is also needed actually. So logistic regression, etc. You can make use of here. That is actually being pointed out. I am not discussing all those things. And here is actually the Bayesian methodology which has been applied. Signal given data, and the likelihood is computed. Then we have obtained the posterior distribution, and using the posterior distribution, we can estimate. So using the Bayesian methodology, so our usual squared error, squared loss function, and many others. So entropy loss functions were actually made use of, and there are many challenges even now. So this is like the paper which was published in 2016. So to where the detection of gravitational waves under non-Gaussian noises, then observation of gravitational waves from a binary black hole merger. And the Bayesian approach combined with MCMC methods provided the means to infer important characteristics of the black holes. And that is expected to be completed by 2023. And Galileo detectors have observed the gravitational waves from the merger of two stellar mass black holes. And this is the first direct detection of gravitational waves. And all these are actually, the estimating this background is challenging for two reasons. The detector noise is non-linear, non-stationary, and non-Gaussian. And that is why it was difficult. And there, the role of statisticians was very much actually. And with the new science, that is actually the new data science and data analytics methods, certainly more results, more fruitful results can be. The new discovery has resulted in many challenges and opened new problems to be tackled by mathematicians and statisticians. Mathematical models are to be developed using the data obtained. Statistical estimation and other inferential techniques are to be developed for more accurate and precise estimation of parameters. The non-Gaussian, non-stationary nature of observations pose more new problems for statisticians, and the Bayesian techniques and MCMC methods are to be modified, and we can make use of our usual so the methodology that is actually our data analytics techniques for estimate. So I hope so it is not very much scientific actually. So what I have given is actually some general introduction of this problem. So such problems are more fundamental than our usual data analytics problems. So anyway, statisticians can answer, have a significant role in such fundamental scientific discoveries. That is actually what I want to say. Thank you. Professor Dharma.
Yeah. Thank you so much, sir. Thank you so much. I think we can accept or address one or two questions. If the attendees have any questions, please. Okay, I think so. I think it was a very interesting and illuminating discussion on how statisticians and physicists have worked hand in hand to towards the detection and studying of gravitational waves, and the application of Bayesian nonparametrics and in particularly Dirichlet process modeling to deal with such huge data, and the application of MCMC methods for computational efficiency. Thank you so much, sir.
Thank you very much. This paper, which is the popular paper which has appeared in Significance 2016, that is very interesting to read for statisticians.
Yes,
so
sir.
Thank you very much. I thank Dr. Satish Kumar for giving this opportunity. Thank you.
After this talk, many attendees might be interested in exploring how to use Bayesian nonparametrics in physics, and what is the application of Dirichlet process modeling in physics. So,
okay, thank you.
Thank you. So our next speaker is Professor Dr. Bhattacharya, Department of Statistics. Is there any noise?
Good morning, madam.
Am I audible, sir?
Yes, sir. Yes, madam.
Some noise is coming from, so that's why I was.
I'm not audible?
Yes, sir, you are audible, sir.
Yeah.
Department of Statistics, and he also is the director of Center for Quantitative Techniques in Osmania University, Hyderabad. Dr. Cherulu acts as the UGC SAP2 coordinator, Department of Statistics, University College of Science. He has published more than 85 research articles in reputed national and international journals, and has successfully guided many PhD scholars in statistics. I now welcome Dr. Cherulu for discussing with us how estimation of missing responses in design of experiments. Welcome, sir.
Thank you, madam. Thank you for your nice introduction. Just I will share my screen. Is my screen is visible, sir?
Yeah, visible. You can make it full screen or slideshow mode. Yeah, now it is fine. Then we can move to the first page. Yeah, yeah, professor. Now it's fine.
Uh, Good morning, the organizers and the chair of the session. Thank you for giving this opportunity. So in this talk that I want to explore the various methods which are used in the design and analysis of experiments for estimation of the missing values. Before just going to the various methods that what I'm going to explore, in some situations when the experiment is conducted in well-planned manner, the response values for some experimental units are not available due to some natural or man-made causes like washed away by floods or fire or plant eaten by animals or destroyed by animals or pets or birds or failed to note the response by the investigator or missed due to theft. So the experimental units mixed up during the time of transporting, so etc. There are various causes may occur. Then the designed experiment is no longer balanced and loses its symmetry and cannot proceed further to carry out the analysis. In some in some experiments, the missing observations affect the distribution of the remaining ones also, and the distribution of the observed random variables of the model is same with or without the missing observations. The most common approach to solve this problem is estimating the missing values and placing in the proper place and to carry out the analysis as per the well planned experiment. So that is the major purpose. Even in the other cases, in the even there are some missing observations with the existed one, we can carry out the analysis, but whereas in the designs we cannot proceed directly with the missing observations as per the original plan. So that is one of the major issue in the design of experiments. And the various designs like randomized block design or Latin square design, some complete or incomplete block designs like balanced incomplete block design or partially balanced or Uden square or some row column designs. And also we are using in the response surfaces or mixture experiments like the various other designs. And also that I considered various analysis of covariance and RBD with M observations per cell and the lattice square design with the M observation per cell and so on. In this, the estimation of missing values in designs is playing a key role in the statistics. The several authors made attempts on the estimation of missing values. Some of them, the Alan Wishart, so initially in 1930, is first time that is tried to estimate the missing values, and later Hertz 1933, Bartlett in 1937, Anderson, Das 1954, Hartley and Haley and Mescott and Wilkinson. So that several authors made attempts and proposed various approaches for uh, estimating the missing values. So here I also contributed some same by using the some of the iterative and non-iterative approaches. So also I'm outline about these methods of the Hertz method, Hartley method, and dropper, Ravin, and just outline of these methods that I want to explore it, and the expected maximization algorithm that what we propose, and the iterative methods. So how we are estimating the missing values, and another Bayesian approach. So in the 93 that I proposed some of the iterative methods for the estimation of the missing values. In 2018, the paper is related to expected maximization algorithm for estimating the missing values in design of experiments, and using the Bayesian, that is 2020, the Thailand journal, the article. Now here, this is not only for one of the design of the specific of the randomizer block design. We can use the randomizer block or Latin square or the various the other designs also. You can implement the same methodology that what the Hayes initially that is proposed in 1933 with he considered on randomizer block design with the V treatments and B blocks, and with some M missing observations, and choose arbitrarily the values m minus 1 missing observed responses, and let xij be the mth missing observed response corresponding to the ith treatment and jth block, and he's evaluated the sum of the responses corresponding to the treatments and blocks, and also the grand total of the observed responses, and he's used the principle of the least square, and evaluated a formula that is specified at here, and the same once that is estimated one missing observation, then he is placed in that one, and remaining m minus 1 missing values, the same process is repeated every time one missing observation, and the same as repeatedly that is doing it, and this is the initial the method. And Hartley in 1956 is considered with three initial guess values for estimating the missing observations. Three initial guesses with equally spaced intervals for one missing cell value, and evaluate the error sum of squares. So based upon the three, as whatever these are in the arithmetic progression that he has considered, and analyzing the error sum of squares by using the normalized equation, and by reducing the error. And the dropper in 1961 is using some Hessian matrix by partitioning the general linear model to the known observations and unknown observations. Let y is equal to x beta plus epsilon be the general linear model that what we are considering for any of the experimental design, and we are partitioning the responses based upon the known and unknown. Yn minus m is the vector of known observations, and ym is the vector of m missing observations, and correspondingly the design matrix is also partitioned, and the error matrix is also partitioned accordingly, and is calculated the uh, error sum of squares by minimizing the residuals, and so whatever this matrix of the x transpose x inverse x, that is considered as H matrix, and that H matrix that are indicating with the elements as this one as an equation, and by solving the for the given number of missing observations, if there are m simultaneous equation that you can obtain, and by solving that we can obtain the missing values. And Rubin, that is also contributed for the same for estimating the missing observations. Assume that m observations are missing, and let xi denote the ith missing value, and let yi is equal to 1 to n minus m represent the known values, and xi denote the predictor value in the missing cell corresponding to xi, and the predicted observations are evaluated based upon the linear combination of the x values as well as the actual data. So based upon a linear equation that is constructed and evaluated the difference, and whatever this xk, the initial set value is set it to 0, and trying to minimize the residuals by forming a set of equation, and that is the general procedure that what is used of it. And the same what was extended by Subramani in 1989, Subramani and Ponuswamy. They considered the partition linear model, and they evaluated the missing observation, the normal equation, based upon almost same as that of the Hessian matrix, but they use it in a small slight difference with x is equal to a inverse b when you are comparing with the Rubin's method. And the Singh and Pratap, they also considered the same, but it is also based upon the general linear model concept for estimating based upon the least square approach only. And they considered the one of the estimated missing value, and repeatedly they are doing by considering the missing values as zeros, and the other observation that is considered as the known. And iteratively they are doing the by solving the same set of equations. And even the park is also computed for the estimated missing values based upon the general linear model according to the partitioning of the known and unknown missing values and the residual sum of squares. And the same thing what I extended by considering the values as per the expected maximization algorithm, that what one of the method that I used it, which was initially coined by Dempster and Laird and Rubin in 1977. The general EM algorithm, this is the general the procedure of the theoretical distribution. I'm not going in detail about this derivative part, and I just am giving the outline about the general procedure that what we are going to use for the same. Now I am considering the statistical linear model, and with a set of observed random sample that satisfies the model, and evaluate the likelihood function of the observed sample and the log of the likelihood function that are evaluating, and choose some initial value for the parameter in the model, and evaluate the expected value of the log of the likelihood function using the initial value, and evaluate the improved version of the parameter that maximizes the expected value of the log of the likelihood function. And we are repeating the step 3 and 4 until the two successive iterates are getting the same value. So this is the general approach that what I used it in the expected maximization. Let's suppose if I consider one of the randomizer block design with covariates. Let the experimental material is divided into n blocks, B1, B2, so on, Bn, so that in each block the experimental units are as homogeneous as possible. Let in each block there are k experimental units. Let T1, T2, so on, Tk be k treatments applied to the experimental units. The treatments are assigned within the individual blocks at random with a separate randomization for each block. So this is the basic the concept of the RBD. Let Yij be the response of the where ith treatment is applied in the jth block, and let there are some m observations are there, and the analysis of covariance is controls the experimental error by taking into consideration the dependence of y on x. So this is the outline of the data, and we are considering the statistical linear model. So Yij is equal to mu plus alpha plus gamma j plus beta into xij minus x double dot bar plus epsilon ij, and where x is the covariate and y is the response, and we are expressing the same in the general linear model y is equal to x theta plus epsilon. So this is the design matrix, and we calculated the x dash x matrix for the same. Whatever this portion that is indicating the z values with the covariates, and we are estimating the missing response using the expected maximization in the design that what I considered. The ym is the missing values. The same, just giving only the outline about the method of calculation for the real data that what the Nigam and Gupta they have taken from the one of the experimental area, that the agricultural experimental data that is considered. And here I consider the three approaches. One is whatever the missing values in instead of the trial, the zero or the mean value or arbitrary value, that you can consider it. If you are considering the zero, estimated the missing observations, and that is in the 20th iteration, it was stabilized. And when you are replacing with the mean, the number of iterations somewhat will be less. And whenever it is an arbitrary, it is stabilized, depends upon the arbitrary value that is chosen, whether it is nearer to the average value or not. And the estimated parameters in almost all the methods, once it is stabilized, is the same. That is that what I have given, and we have calculated the estimate, the missing value, and there is no much difference in between either assumed value or arbitrary value or the missing value. And ignoring the here the concept that what you are considering, one is considering the value of the covariate corresponding to the response, and without considering the covariate. So two aspects that what we are considering at here. That means whenever we are considering the X design matrix, the whatever the independent, the response is only not known, but the covariate, the design matrix is entirely is a fixed one, which is already known. So shall we have to exclude from the partition matrix, or shall we have to include it? So these are the two concepts that what I considered, and it is only deviating with the number of iterations when you are comparing with the eliminating the part. And in both cases that you are getting the same estimated response value. And there is also the interrelationships between the assumed value and the mean value and arbitrary values, the interrelationship between the parameters, that is also evaluated. And because there is only the number of iterations, that also we can almost nearer, but as and when the n is increases, the accuracy is also increases. Generally, in for the small sample data that I took around 20 iterations, and if the data is very huge, it may take the more. And these are ignored values with the covariant to the missing responses. And this is another data that what I considered with the many of the missing values. And here I'm assuming the many of the hello. Hello?
You can continue, Professor. You can continue.
Yeah, if you are having many of the missing values, all missing values that I considered. So previously that I considered with a single missing value and m missing values, the same concept that is extended. And when you are comparing with the least square and the expected maximization, the expected maximization approach uses the likelihood function of the sample observation, whereas the least square uses the linear model of the observations. And it is the expected maximization is will provide iterative and non-iterative approaches. So what initially that I had given based upon the various methods. Whereas in this one we can also use the iterative approach. Most of the expected maximization algorithms that are using only the iterative approach, and it is a distributional based. And there is a restriction on the missing limitations for the design to design. And suppose if any one of the uh, block, all the observations are missing, then estimating of that particular is almost the meaningless. If there is some block effect is also affecting it. So that's why here the missing observation limitation that also is existing it. And the same thing that the concept that is extended for the incomplete block designs, for the balanced incomplete block design, and also the partially balanced incomplete block design, because we have used a general linear model. So same approach of the normal equation that what. So this is the y is equal to x beta plus epsilon for a balanced incomplete block design. And we calculated the beta hat based upon the C matrix, and whatever the beta hat, so that we are calculating. And this is the normalized equation based upon the expected maximization algorithm that what we have derived from the probability distribution. And the same that we extended for the response surface models also. Let's x be the vector of v factors, and assume that each factor has Hess levels for experimentation, and D denotes the design matrix with a combination of the factor levels, and XUI be the level of the ith factor in the uth treatment combination, and YU denote the response at the uth treatment combination, and expected value of the response at the uth combination, that is expressed, which is generally a response surface. And the response surface design model that we are expressing, y is equal to x beta plus epsilon, and that is depends upon the response surface model is first order or second order or third order, whatever it is, polynomial it may be. And when you are applying for the same, the from the likelihood, whatever the likelihood function, because the observation that are assumed to be follows a normal with mean is x beta and variance is sigma square, and the expected value of the log of the likelihood that are calculated, and also the uh, maximization step is also evaluated to estimate the parameters, so based upon the general procedure of the expected maximization. And so this is that what I used for the response surface with uh, two missing values. One is y12 and y25, and I'm assuming that the missing values are zeros, and calculated the same values at here. This is the actual data and estimated parameters. This is based upon the zero values, and this is based upon the mean values. And the estimated responses are the same that what you are getting, but it is changing from the iteration to iteration. And the same thing that when you are comparing with the least square approach, that what generally are using the response surface model, that is also the same value that you are obtaining it. This is another example, the data and estimated parameters, that two values that is considered at here, the at fifth and 16th, the observations that I considered it here. And the second order response surface model, if you are considered, the same that we are derived it by considering the rotatability condition at here. So this is the rotatable design, the moment matrix, that is x dash x inverse. And now the same thing that what I extending for the Bayesian approach. So the estimating of the missing response values and complete block designs using the Bayesian approach, and whatever the general Bayesian approach, the normality assumption only, that what I considered, uh, and I derived the likelihood function. I computed the likelihood function and expected value of the likelihood and log of the likelihood, and we are estimating the parameters and computing the posterior the probabilities for the parameters, and based upon this that we are trying to estimate using the some of the simulation, the general approach of the Bayesian. For that I used is WinBug and OpenBug softwares, which are for simulating and estimating the parameters, and based upon the distributions of the normality, and the parameter of the variance is the inverse gamma. So this is the various approaches that and this is the general procedure that what I applied for the using the Bayesian approach. So y is equal to y n minus m, only the known responses, and evaluate the mean and precision of the known responses, and evaluate the initial estimate from the known values, and set the values for the parameters for the gamma distribution with the parameters a and b as per the derived. Set the values for the parameters for normal distribution based on the design, and generate a large sample. So repeatedly from the distribution, you can use any of the, either you can also write the R program for the same, or you can use the software for simulation of the same, and estimate the parameters each time and compute the uh, estimated parameters. And from once the parameters are estimated, then you can estimate the missing values based upon the y hat is equal to xm hat, xm beta hat. So this is the general the approach that what I considered. Uh, Here I'm summarizing the same uh, as an alternative. These are the Bayesian approach and expected maximization algorithm are alternative methods. And Bayesian approach is a distributional, and expected maximization is also a distributional. And whereas the Bayesian that are generally it is not directly as an iterative, but it is a simulated process. And whereas the expected maximization algorithm is totally is an iterative approach, and there are many iterative approaches when you can also compare with the same. And Bayesian approach is giving the more precision when you are comparing with the other. And almost when I compared for the small sample data, the least square estimate and the Bayesian and expected maximization all are giving almost the same result. And there is some interrelationship between the iterative process, and the number of iterations depend upon the initial guesses, and the rate of convergence of the expected migration algorithm is a second order convergence. So that is one of the major one. And we you can I derived and examined the same thing for various complete and incomplete and the response surface the models. And also we have evaluated the confidence interval, and based upon the general approach to this one, and which are also the compared with the least square approaches, and which will gives the same resulting values. Thank you for this. Any queries?
Thank you so much, Dr. Cheridu. So we can take one or two questions now. That was a very comprehensive and lucid presentation, giving a complete overview of different methods, starting from EM algorithm, least square methods, and Bayesian application of Bayesian methodologies for estimation of missing observations. So, if the house has any question. And also, Dr. Charilu has explained everything, supported with examples, so it was very helpful for the audiences. Sir, if I would like to ask one question, I have one question.
Yes, madam.
Sir, what I just missed, I guess, what prior was used while the Bayesian modeling on the parameters?
Huh?
What is the prior which has been used for modeling the parameters, prior distribution?
The normality only that I used it.
Okay, sir. Thank you.
Thank you.
Thank you, sir.
Thank you for giving the opportunity, Professor Satish Kumar sir, and thank you, Darba Bhattacharya madam, and thankful to all for your patient listening. Thank you.
So our next special invited speaker is Dr. K Jayakumar. He is the professor and head of the Department of Statistics from University of Calicut. And he has also served as the General Secretary and President of Kerala Statistical Association. Dr. Jayakumar has PG teaching experience of 25 years and a research experience of 31 years. Dr. Jayakumar has hundreds of research publications in many national and international reputed journals. He has successfully guided many PhD students, and his areas of research specializations are distribution theory, time series analysis and forecasting, and probability theory. Dr. Jayakumar will discuss on estimation of stress, strength, reliability for new generalized Pareto distribution using advanced sampling methods with us today. Over to you, Dr. Jayakumar.
Thank you very much, Professor Darba Bhattacharya, and I thank the organizers, especially Professor Satish Kumar, for giving me a chance to present some of my results. And my topic of my today's discussion is on estimation of stress and reliability of the new generalized Pareto distribution. That is one of the generalizations of the Pareto distribution, which we have introduced in a paper which appeared in Communication Statistics Simulation and Computation. May I try to share my screen? Is the screen visible?
Yeah, it is visible. It's fine. And
Yes, sir, it is visible.
yeah.
So the topic of today's discussion is estimation of stress and reliability for the new generalized Pareto distribution using advanced sampling methods. So an outline of the talk is, let me give, at the outset I may give an introduction of the discussion, and then we will go to the new generalized Pareto distribution, which some of the participants may not be familiar, and we will discuss some properties of it and why we are concentrating on it. And then we will look for the stress and the reliability. And now the sampling is, we may estimate the parameters based on the ranked set sampling and the PRSS. And I will give an outline of that, and we will discuss the ML estimation. the reliability, system reliability based on both SRS, simple random sampling, RSS and PRSS. And we will discuss a simulation study for the comparison and some applications to the data analysis. And as all of us know, the Pareto distribution have been extensively used in literature for modeling and analyzing of income and lifetime data. And the generalizations of Pareto distributions have applications in a number of fields, such as reliability studies, in modeling of large insurance claims, and as a failure time distribution. And in recent years, we can see that there are several generalizations of Pareto distributions have appeared in the literature. And as I have already told myself, Bindu Krishnan and Hamadani, we have introduced a heavy-tailed distribution. As you all know, the Pareto distribution is heavy-tailed. This distribution is more heavy-tailed than the Pareto distribution, and it is a generalization of the classical Pareto type 1 distribution. And it has flexibility in data modeling, and it is a better competitor for several existing generalizations of Pareto distribution. And you can say, we'll see later that the distribution is in fact belongs to the class L, that is the class of long-tailed distributions, and it is in fact a member of the class of dominated variation distributions, and which in turn implies that the distribution is sub-exponential. And as a consequence of it, you may be able to model the distribution of the maximum by the distribution of the sum by the maximum. And that is, in fact, the peculiarity of the distribution in applications. And this 4-parameter distribution, and we may denote the distribution as NGP, alpha, beta, gamma, theta. And the probability density function of the NGP is given in equation 1. And the corresponding distribution function, one may be able to compute it as equation 2. And the hazard rate function, one may get the equation number 3, and you can see that it has both IFR and DFR nature. And when theta tends to 1, that is in our density, when your theta tends to 1, theta equal to 1 and gamma tends to 1, the NGP, that it will reduce to the symbol, the Pareto distribution. And the survival function of NGP is a function with a regularly varying tails, so which is in fact a desirable property for modeling heavy-tailed data sets. And as I have already told, the distribution belongs to the class of long-tailed distributions, that is the class of long-tailed distributions, that is, and we can see that whenever your alpha is finite, the NGP distribution belongs to the class of dominated variation distribution, and as a consequence, it belongs to the class of sub-exponential distributions. And you can see that the tails, if you look for the tails of NGP and classical Pareto, they are tail equivalent. And now we will look for the inference procedures for stress strength reliability of NGP based on SRS, RSS, and the PRSS. And the system reliability has a wide range of applications in many fields, such as reliability analysis, quality control, medicine and engineering, as this for the beginners. And the system reliability is given by probability that x less than y. And it is used to describe the survival rate of a component which has stress x applied and y as the strength of the system. And the concept of stress strength model was introduced in the literature by Brigham in 1956. That is 1970. For those who are interested for the history of. And for a comprehensive review on stress strength model and reliability, one may be able to refer the book by Johnson, 1988. And the paper. And inference for system reliability under different stress strength distributions has received much attention in recent years. And Exhaustive study of different stress in the models under different distribution assumptions are available in Coates et al. 2003. Okay. Krishnamurthy et al. 2007 considered the exponential stress and strength random variables for modeling data sets. And these are some other works. Almore et al., Whitney et al., and Reyes et al. Considered estimation of stress and reliability when under the assumption that both the stress and strengths are linear distribution, or both are power linear, or both are generalized linear type 5 distributions. And more recently, in 2021, they have studied Agul et al. Studied estimation of system reliability for generalized inverse linear distribution for various sampling designs. And now let me give a brief introduction of ranked sampling for which who are not familiar with that. The concept of ranked sampling was introduced in McIntyre in 1952 in an agricultural experiment to estimate the mean of pasture yields. And the aim of ranked sampling is to collect the observations from a population that are more representative of the population than the same number of observations obtained using simple random sampling. And this technique is used when it is difficult to measure the observations, but relatively easier to rank them. That is, for selecting a ranked set sample of size n equal to mr, we draw m random samples from the population, each having size m. Rank the observations in each sample from the smallest sample to the largest by visual comparison, expert opinion, or the use of auxiliary variable. So the first, okay, these are some of the techniques. And in the context of system reliability, Sengupta and Mukherjee 2008 and Mutalak et al. 2010 considered the estimation of R when the distribution of stress and strength are exponential under RSS. Hassan et al. 2015 considered the estimation of system reliability under ranked set sampling in the case of type-type distribution. Agul and Senoglu 2017 and 2018 obtained the estimate of stress and reliability based on RSS in the case of Weibull distribution, that is assuming that the stress and strength have followed Weibull distributions, or in the other case they have considered linear distributions. And another work is on exponential Pareto distribution. And the efficiency of RSS method is mainly affected by the possibility of doing error in the ranking process. The error in ranking process due to the incorrect measurement of some error mainly occurs. The error in ranking increases due to the incorrect measurement of sampling observations, and to overcome this drawback of RSS, modifications of RSS have been suggested in the literature. And one such is by Samvi et al. In 1996 suggested extreme ranked set sampling ERSS. And another one is the median ranked set sampling MRSS. And another one is the double ranked set sampling DRSS. And Mutlaq 2003 and Alnasser 2007 suggested percentile ranked set sampling PRSS, L ranked set sampling LRSS respectively. Recently, Samande and Elmore suggested neoteric ranked set sampling NRSS. For selecting a percentile ranked set sample of size n equal to mr, we draw m random samples from the population, each having size m. And the procedure is described below. That is, where the observations are rank the observations in each sample from the smallest to the largest by visual comparison, expert opinion, or the use of auxiliary variable, as I have already explained. And if we set our m is O, then the first m minus 1 by 2 sample units in the percentile ranked set sample is the p into m plus 1, the smallest ranked observation in the first m minus 2 ranked sample of size m. The next observation in the percentile ranked set sample is the median of ranked observations from the very next random sample, and finally remaining n-2 sample units in the percentile ranked sample ranked set sample is the q into m plus 1 smallest observation. Similarly, we may be able to describe this. So to generate a ranked set sample of size n equal to mr, the entire process this is the process you may be able to repeat r times. And in our process, we assume that in our interest is to estimate r, that is estimate probability that x less than y, under SRS, RSS, and PRSS. When x and y are independent, and at the same time we are assuming they follows NGP with parameters alpha 1, gamma 1, theta 1, and NGP alpha 2, 1, gamma 2, theta 2 respectively. So we may try to estimate, find the expression for R equal to probability that x less than y, under the assumption that x follows NGP alpha 1, gamma 1, theta 1, and y follows NGP alpha 2, gamma 2, theta 2. And under the assumption that both x and y are independent, and if you compute that, we may get an expression of that integral, which we may denote as phi of alpha 1, gamma 1, theta 1, alpha 2, gamma 2, theta 2. And now our estimate is interest is to estimate R. Obviously, the solution of the above integral cannot be solved directly, as you can see. So we may use some numerical methods to calculate the stress and reliability measure. Now, to obtain the ML estimate of R, we need to find the maximum likelihood estimate of the parameters. You can see that because your R is in fact involves these 6 parameters. And for that, let me consider a random sample of size n from the xi population and m from size m from the y population, and V2 independent simple random samples from NGP with xi follows alpha 1, gamma 1, theta 1, and y follows alpha 2, gamma 2, theta 2 respectively. So this is the sample I have, and you may be able to find the likelihood. The likelihood of it is, you can see that product I equal to 1 in that. But that will give rise to the log likelihood function like this one, and we may get these 6 equations. Obviously in 6 unknowns. And we may be able to see that the problem of obtaining analytical solution for the parameters by solving these equations 4 to 9 is somewhat difficult. The ML estimates of the parameters are obtained by equating the equations 5 to 10 to 0 and solving them simultaneously. And one may be able to use the R for solving these equations using some iterative techniques such as Newton-Raphson method, and hence using the invariance property of MLE, the ML estimate of the stress and reliability based on SRS can be obtained by substituting the ML estimates of the parameters in phi alpha 1, gamma 1, theta 1, alpha 2, gamma 2, theta 2. That's obvious. Now, let me look for this, in fact, the estimation, ML estimation of R based on SRS, and let me consider the next situation, that is the estimation based on RSS. And for that, let me consider the sample, that is XIIK. I takes the values 1 to mx and k takes the values 1 to rx, be a ranked set sample observed from a set of observations taken from NGP alpha 1, gamma 1, theta 1 with the sample size n equal to Rx, mx into Rx, where mx is the set size and Rx is the number of cycles respectively. I have already explained how we may be able to take the samples there. Similarly, we have Yj, Jl, J is equal to 1 to My, L equal to 1 to Ry be a ranked set sample observed from NGP with a sample size M equal to My Ry, where My is the set size and Ry is the number of cycles respectively. And if you compute the likelihood equation, you may be able to say that L equal to product A equal to 1 to Rx, I is equal to 1 to Mx. If Xik, product L is equal to 1 to Ry, J is equal to 1 to My, if Yl, where these we know. And based on that, one may be able to find the log likelihoods, and you will get the differential equations. And based on that, one may be able to find the ML estimates, but as I have already told. But we may not be able to find the analytical solution for that. For that, we may look for some another simulation techniques or the softwares for estimating the parameters. And again, using the invariance property of the MLE, one may be able to obtain the estimates of R under ranked set sample, which I may denote it as R hat RSS, by substituting the ML estimators in the parameter in phi alpha 1 gamma 1 theta 1 alpha 2 gamma 2 theta 2, where phi is nothing, it is my expression for probability that X is Y. And you obviously you may come across two separate cases. One is the odd set sizes, and the other one is the even set sizes. And if you calculate the PRSS using the procedure, one may be able to find the likelihood function corresponding to PRSS, and the likelihood function corresponding to PRSS is given here. And the even set sizes also, we will get the likelihood function corresponding to PRSS. And for finding the ML estimate of the parameters based on PRSS for both odd and even set sizes, we equate the partial derivatives of the likelihood function to 0 and solve them numerically. And as I have already told, we may not be able to obtain a clear solution for these likelihood equations, so we may have to rely upon the estimation procedure to measure which of these methods is the best one. Which of the sampling schemes will give you the better estimates. The mean square error relative efficiency measures are compared to compare the estimated reliability. And in this simulation, we have taken a simulation study. We have taken the true values of the parameters selected as we have taken three sets. That is, the sets we have taken is 1, 2, 1, 2, 2, 1. That is the first set. Second set 2, 2, 1, 2, 2, 1, and the third set 1, 3, 1, 1, 3, 2. And you may be able to compute R corresponding to that, and you will get it is your R is equal to 0.353 in the first case. The second case it is 0.5, and third case it is 0.715. Now to apply the RSS and PRSS, let me take my MX and MY as the pairs 2, 4, 6, 6, 8, and RX and RY as 10. Similarly, I may get I have my N is equal to MXRX, M is equal to MYRY, and based on that, I will get the pairs NM as 20, 20, 20, 40, 40, 40, and so on. So, are the sample sizes selected for the SRS? Now, we generate 1,000 samples from NGP alpha 1, gamma 1, theta 1, and NGP alpha 2, gamma 2, theta 2, and calculated the stress and the reliability of R. Reliability R based on the simple random sampling, the ranked set sampling in percentile ranked set sampling, and the results are compared using the MSE and relative efficiency. And we can see that we may be able to, we have our RA1 is MSC of SRS by RSS that we know. So you can look at the quantities here. We may be able to see the MSC under SRS, RSS, and PRSs with the relative efficiencies, and which will in fact give us an idea of that the dominance of PRSs in estimating R. And if you compare for RSS and SRS, that is the first one, that is from this table one, you just compare our SRS and RSS and in terms of the mean square error. And one may be able to compare them in terms of the relative efficiency also. That is, according to RE1 values, we can see that the estimated stress and reliability R under RSS performs better than the corresponding ones under SRS in all cases. And according to the RE2 values, the estimate, that is the what is the expression for RE2, that is RE2 is MSC of RSRSS by MSC of RPRSS. That is the comparison between SRSS and PRSS. And here it is the comparison between SRS and RSS. So according to RE2, the estimate of R under PRSS performs better as compared to SRS. And in most of the situations, the estimate of stress and reliability R under PRSS performs better than the corresponding ones under SRS according to RE3. So in most of the situations we may be able to prefer PRSS in estimating our R as compared to RSS in the situation. So also, as the set size MX and MY increases, you can look for the comparison with the set sizes MX and MY. MX and MY, in the first case I have taken it is 2, 2, then it is 2, 4, 4, 4, 4, 6, etc. So from the table, also the set size MX and MY increases, the MSE of the estimates of R under SRS, RSS and PRSS decreases. So hence, RE1 and RE2 values increases when the set size MX and MY increases. That's all. And now we will look for an application to a real data set. We analyze a real data set to illustrate the use of the proposed methodology. And for that, let us consider a data set that is available in the literature. The data set is used for the analysis in the fiber strengths in the data listed in Cowder 2000. And this is a random sample of 168 failures, stresses observed in hybrid bundles of parallel carbon fibers. And one may be able to refer this paper for the details for how this data arises and so. So from this, we select two data sets which have the breaking strengths of single carbon fibers of different lengths. And the data sets are given in table 2 and table 3. Table 2 is the data set corresponding to our X. That is the strength data. And the stress data, we are getting data Y, that is given in table 3. And now to perform whether the distribution is appropriate for modeling the data set, that is the first question. Whether one may be able to use the NGP for comparison, or one may be able to assume that the distribution of your X's is NGP, or the distribution of your Y, one may be able to take it as NGP. So one may be able to do that by using the TTT transform, one of the techniques. So for that, using the TTT transform, we can identify the shape of the hazard rate function of the data. So as we know, the empirical TTT plot is given by GRN is equal to that, where Xi is the ith order statistic in the sample. And if the TTT transform is convex, concave, and convex, then concave, or concave, then convex, then the shape of the corresponding hazard rate function is respectively decreasing. That is, if your TTT transform is convex, then the hazard rate is decreasing. If it is concave, it is increasing. And in the other case, convex, then concave, it is bottom shape. And in the other case, it is upside bottom. And the details are available in the paper by Arset in 1987. And if we look for our data sets, we can see this situation corresponding to both the data sets. So from this figure, we can see that the hazard rate function in both the data sets are increasing, right? Because this implies that the hazard rate function is increasing. Moreover, the NGP distribution can be used to model the data sets having DFR and increasing failure rate in character. That we have already established in our paper in the communications in statistics. So you may be able to use that we have data for that. So we fit NDP data distribution for both the data sets separately. We first try to fit the data set corresponding to X and then try to fit the data sets corresponding to Y. For fitting, we first estimate the parameters of the distribution and also we check the goodness of it. That's the usual technique. And for the data set X, you can estimate the parameters as this. The parameters is this one, and some of the measures of comparison you may be able to consider the information measures, that is minus log L, we may get it is 58.05981 for the X data set, and for the Y data set it is 49, and whereas the case value for goodness of it is 0.08 and the p value is quite significant. So you may have in the first data set it is 0.68, and for second data set it is 1, which will in fact tell you that one may be able to model the data set. We have X data set, both the X data set and Y data sets with the NGP distribution. No, so we are choosing these data sets to select. We are choosing these data sets to select the samples based on SRS, RSS, and PRSS. And for selecting the samples via SRS, we take the sample sizes for X and Y as n is equal to 16, m equal to 20. And in case of RSS and PRSS, we take mx is equal to 4, Rx is equal to 4 for data X, and mx is equal to 2, and Rx is equal to 10 for data Y. And based on this, we have calculated R and also R based on n equal to 64 and m equal to 70 observations calculated as 0.227. The means and MSCs of the estimates of R are obtained based on 10,000 replications, and result is given here. So you have the estimate of R under SRS. This is RSS, and this is PRSS, and this gives the bias, and this is the MSC, that is the ML estimates of R based on SRS, RSS, and PRSS. And from table 5, we can say that the estimated values of R based on n is equal to 16, m equal to 20 sampling units using different sampling fees are close to the estimated values of R calculated from the whole data set. Right. That PRSS perform better as compared to SRS and RSS. Similarly, similar to previous studies, it can be easily seen that the modifications of RSS provide advantages in increasing the efficiency of the estimators of the system reliability measure. So that is the conclusion, and so these are all some of the references that I was mentioning on the estimation of system reliability. Yeah, thank you very much.
Thank you. Thank you, Professor Jayakumar. I think we can take a few questions now. Because there are no questions from the house. Thank you, Professor Jayakumar, for a very, very interesting presentation on application of advanced sampling techniques in conjunction with the new generalized Pareto distribution. I would now like to thank the organizers for organizing such a wonderful conference, and in particular Professor Satish Kumar for bringing us together on this platform again. Thank you, all of you. Thanks. Thank you, the audiences.
Thank you, Darba Bhattacharya. Thank you, Satish Kumar. Thank you very much. Thank you.
Thank you, Professor Darba Bhattacharya, for chairing the session. In fact, it was a very interesting session, and it's a wonderful session. I would like to extend our gratitude to each of the speakers, Professor K. Jones, Professor Bhattacharya Lu, Professor Jayakumar, for their very excellent presentations. Thank you all. Now we have now this time. You concluded session in time. So it is up to 12:45.
Thanks to the speakers.
Maintain the time. Yeah, very good. Thank you. And we have 5 more minutes to start the next session. By the time we can, if anything you have to mention, please. You can utilize either you can take it as a small break, or not need to take a break, but you can interact. This time we have placed in that way to interact each other.
If someone has any question.
Yeah, you can. Any question?
I think Dr. Jose has left the meeting. But Professor
he has an urgent,
meeting. He has a meeting. And Professor Jayakumar are there. So if anyone has any questions on the topics they have discussed, I'm sure the researchers present attending this session will find applications of the topics which have been discussed today in their research work. There is a variety of topics which have been discussed in this session today. So.
Of course. I hope, Professor Jayakumar, you can give some motivational or some advices to our youngsters, if you think so. If it is not difficult, give some advices to our young researchers. Or Professor Bhattacharya can also do.
So, I found Professor Jose's discussion on Bayesian non-parametric very pertinent to my research field. It was like he discussed the application of Bayesian non-parametrics in physics. We have used Dirichlet process and Bayesian non-parametrics modeling in genetics. So that was. I was thinking of exploring that field.
Okay.
You work in which area?
Yes, sir. I work in the field of statistical genetics, application of Bayesian non-parametrics in modeling case control data, genetic data. And we have explored with the application of Dirichlet process mixture models based on MCMC and Gibbs sampling for computation. So, someone has
raised the hand.
Yes, please. Yes, Hemant Kumar has raised a hand. Sorry.
Hemant Kumar, do you want to say anything?
You can please share your opinion.
In fact, Professor Kalyan has also done some works in that area, isn't it?
That was unmute, yeah. Yeah, hello.
Hello.
Yeah, good morning.
We can hear you. Anand, you can say.
Yeah. It is very nice to listen, Madam Bhattacharya.
Please.
Working in a statistical journalism. Yeah, this field is very means less important in the field of statistics, and try to interact with you.
Yes, sir. Sure, sir. Would be my pleasure. We can take that forward.
And other things.
Yes, sir. Sure.
Later on. Okay,
Sure, sir.
Thank you.
Thank you. Thank you so much. Thank you, Professor.
Conferences, seminars, and symposiums, including in ICMS 2012, NCMIA 2019, ICCM 2021, and ICSTC 2021. She has organized 4 national seminars.
Madam, there is any sound from audio?
Is it okay, sir?
Now it is okay, madam. Now it's okay. Now it is okay.
Hello?
Now it is fine. Now it is fine. We can see your slides also. You can make it full screen or slide mode. Yeah.
Yes,
Slideshow mode.
sir. I am good. Yes. visible, sir?
This visible, but I think you can make it. You can, since you are using a mobile, you can make in this. Instead of placing this way, this can, so that it will be the horizontal position. Put it in portrait. So that that window will be more, yeah. ഉണ്ടോ കിട്ടിയോ ഇല്ലേ രജിസ്റ്റർ അയച്ചൊന്നുമില്ല അവര് പിന്നെ അത് ക്ലിക്ക് ചെയ്താൽ കിട്ടും.
Sir, just a minute, sir.
Okay, madam, don't worry.
Now I think it's is it visible, sir?
No, madam, no, not that.
Sir, just a minute, sir.
Okay, let us wait. Okay, madam.
Sorry for this. Sorry for this.
Okay, it is better to mute one of these systems. It's better.
Sir, there is some problem with my laptop. So
Okay.
can I present it from my mobile, sir?
Yeah, I can present it, or otherwise you can send to me, and we can present from here, if it is.
Okay, sir. I will send it to
Yeah, it's an email to me.
you.
In case you are using, did you send it, madam?
Sorry for this. Sorry for this
waiting.
interruption.
Oh, no problem. No problem, madam. No problem. Or otherwise, while presenting mobile, using the mobile, what I suggest is to place in the horizontal position, not in vertical, horizontal position, so that the screen will be maximum size, will have the maximum size.
Okay.
That is what I mentioned.
Good morning, Professor Satish Kumar, sir.
Yeah,
Familiar?
good morning. Good morning. Yeah, good morning. Good morning, Professor Parimal.
How the sessions are going on? I think must be wonderfully.
Yeah, fine. Going on wonderfully. And in fact, last session, very interesting sessions.
Oh, that's great. I missed that.
In fact, now there is a technical issue. That is why some time we are waiting for clearing that.
Okay. So hopefully we meet in physical mode.
Sure. Yeah. Let us wait for some more time.
Yeah, surely. Because we are also organizing one conference in 2023, Feb 2023.
Okay,
so we are expecting you to be in Jammu.
Surely, Professor. Let us try our best.
Yes, sir.
I got the letter.
Surely.
Yeah. Or Desri madam, whether by the time if there is any delay, we can move to the next speaker and then comes back to you.
Sir, can we go for next speaker, sir?
Yeah,
Satish Kumar, sir?
Desri madam. Yeah, that is what I am talking about. If Desri madam has some difficulty for the timing that these technical issues, let us go to the next speaker. Professor Asha is with us.
Okay, sir.
Hi. How is your cough?
It is better. I hope I will not create a ruckus.
Okay.
I'm acute.
So by the time, let us wait 1 or 2 minutes maximum.
So am I presenting now? Or
just a minute, whether we have to get the permission from the speaker.
Hello.
Madam, we are waiting for you.
Sorry, sir. There was a sudden power breakdown. So
Madam, whether we need to
I got disconnected.
If there is
Yes,
difficulty, we can go to the next speaker and then come back to you. Isn't it? Is it okay?
Okay, sir. Please do that, sir. I will be ready by then, sir.
Okay. Very good.
I'm ready.
So, Chair, please.
Hello. I will be ready by then, sir.
Yeah. Okay, welcome.
I will send you the PPT, sir.
Yeah. We shall do.
Thank you, sir. Thank you.
Welcome.
Sir, can I?
Yeah.
Hello.
Yes.
Can I now introduce Asha Gopalasoman, sir?
Yeah, please introduce the speaker and then invite him.
Okay, sir.
Please introduce the speaker briefly and then invite.
Okay.
Asha, madam, how are you?
I'm good, sir. How are you?
Yeah, fine. Thank you.
Nice to see you, at least online.
Okay, thank you. Okay.
Satish, Professor Satish, you are muted.
Yeah. Sorry. Namaste, Gopal sir, and hi to Dr. Sudesh.
Hi.
You're from Chennai, isn't it, Sudesh?
I came to notice today.
I think Dr. Saroja is introducing me.
Yeah, please.
So we'll get on with that session.
Okay.
Sir, I'm trying to download Asha Gopalan's madam's biodata.
No need. Just tell me where I am from.
Madam, 1 second, madam. It is not opening. Professor Jayashree madam's biodata is already opened, and this is. I will briefly describe about Asha Gopalan Madam Garu. She completed MSc, MPhil, and PhD. He is professor in Department of Statistics, Cochin University of Science and Technology, and he published many reputed and international Scopus and Web of Science and UTC Care listed journals, and he participated and presented and taken invited talks in the different national and international level programs. She is a good researcher in statistics. This is the brief description about Asha Gopalan Madam Garu. Now I am requesting you, Madam, to continue your presentation.
Thank you so much, Dr. Saroja. On the outset, let me thank the organizers and especially Professor Satish Kumar for the rightly spoken by the last speaker, consistently conducting very good quality conference like this. Definitely it will have an impact on the researchers. Congratulations to you. And thank you so much for your patience, asking, but catering to all my requests, put my talk here, so on. Thank you so much for your patience also. So let me just present my slides. And I'm going to talk on curate models. I hope my slide is visible.
Yeah, madam. Yeah.
And I
Professor
hope
Rajan.
I'm audible also. In case I'm not audible, please
Audible? Yeah.
interrupt me.
In
Okay.
case of any difficulty, we will inform you.
Yeah.
Don't worry. Okay, please.
So I'm going to present the curate models, actually the transmuted curate models in a competing risk perspective. This is a joint work with my student C.S. Surya, and it's an ongoing work. So to give a brief introduction to curate models. Models for survival data with surviving fractions are known as curate models or long-term survival models. And this has application in many fields like biostatistics, finance, criminology, demography, and also reliability. So initial work on curate models appeared in a paper by Bong and Bergson and Robert in cancer studies, because it was seen that many patients who had cancer, they showed that population showed a survival probability and they would survive. So the two models that were popular were the mixture model and the promotion time model. Now mixture curate model were subject to a lot of study and is still subject to a lot of study and modifications even now. Even in this conference, I see 1 or 2 papers on curate modeling. So the basic model was this: if T is the failure time, then the probability of survival of the total population, that is G bar T, is now represented as a mixture model, P plus 1 minus P F bar T, where F bar not T is some baseline survival distribution. Now, if you look at this, as T goes to infinite, you can see that G bar T goes to a constant P, where P is lying between 0 and 1, a parameter. And this P, if you look at P...
Nikhil will share it from here.
If you look at P, this P is a proportion of those people who survived in that cohort. That was the idea of it. Or the logic of this is that... Is there any... Or the logic of this is that this G bar T is an improper distribution. So every curate model is an improper distribution, or in short, we can use improper distribution or defective distributions for modeling populations with long-time survivors. So if you look into papers on this, the basic idea is how to formulate the basic logic or the basic idea is simply this: how to formulate an improper distribution and how to give it a meaningful physical representation. These are the two things. So all papers are based on these two logic. So it was in 1984, Cox, the paper by Cox, competing risk perspective for this curate model was given. So here, if M is an unobservable random variable denoting the number of competing causes related to the occurrence of an event of interest with probability mass function Pm, where M takes the value from, it's a random variable, discrete random variable with the suppose 0, 1, 2, etc. And Wj, that denotes the time to event due to the jth competing cause. Now I assume Wj are independent and identical with the survival function St, and the number of causes M and the lifetime Wj associated with a particular cause is not observable. What is observable is T, that is minimum of W0, W1, W2, Wm, with probability of W0 infinite equal to 1. So W0 is the time. If you look at W0, it is the time to event due to the jth competing cause, and when there is no cause, there is no death. And that this is what is inducing the cure fraction in the model. So now the population or the long time survival function of P is defined as S pop T equal to expectation of St raised to n. If you take M as a Bernoulli distribution, this just reduces to your mixture model, the conventional mixture model, which was introduced by Bog. Rodrigues in 2009 generalized it and gave M a composon distribution with PMF of this form in 4. The survival function of the composon cure rate model is given as this. And if you substitute over here, you get what is known as the composon cure rate model. When phi tends to infinity, this model, this composon model, it actually generalizes many cure rate models in literature. When phi goes to infinity, the composon tends to the Bernoulli distribution with parameter 1 plus eta. And when phi is equal to 1, it reduces to the promotion time cure rate model of Yakola and Sodico. A lot of work on this composon model has been done in recent years, and it's still in interest. These are few of the references. Now, what we did is, instead of assuming Wj to be distributed as St, a proper distribution function, we can assume to have a distribute G0, the G0 infinity equal to C0. That is a improper distribution for the baseline distribution. So what it actually means that each cause has only a probability of inflicting the death. So W1 is now distributed as G0 T, where G0 itself is a improper distribution. In that case, what is now observed is T, where T is now minimum of W1, W2, Wk, and each of this now has a probability of actually surviving that. Each risk has a probability of inflicting that event. So now M is again an observable random variable denoting the number of competing causes related to the occurrence of event of interest with a shifted binomial Pm, probability of given in equation 7. And once you take this shifted binomial, the density of the GTC or the generalized, we call this the GTC model. Let me tell you why this is called the GTC model, is obtained of this form 8. Now, this is nothing but the transmuted distribution function. So, if you take M equal to 2, you get what is popularly known as the quadratic transmuted distribution. This quadratic transmuted distribution has been, I don't know, there are infinite number of papers. Every distribution has been introduced a transmuted parameter and worked upon, showing it is a better fit. But if you take it, introduce it in this way, you get a very general model, which includes all different transmuted model or different rank transmutations. You have the if M is equal to 2, you have the quadratic transmuted. M equal to 3, you have the cubic transmuted. M equal to 4, you have the quint, and so on, M of order M. So the transmutation goes in that way. If you look at the density and the effect of this parameter P, you can see that P actually affects the skewness, or it manages the skewness of the new distribution. So it is now a right contender to involve the covariate through P. So now we propose a new distribution by extending the Rodrigues model with M being considered to have a shifted binomial distribution and the baseline to be a improper distribution. And now the covariates are introduced through the parameter B, and we take the logistic form for the reason P lies between 0 and 1. So define two classes of the form 9 and 10 and 11 for P. We observe that the new model or the new curate model is of this form, which we refer to as the general class of transmuted curate model. When M is equal to 2, this is that popular quadratic transmuted model for that reason. The class of models corresponding to 12 can be written in the form of 13, and the Kerr fraction for this class of models is of this form. So this also now, sublimes a lot of curate models. For these baseline distributions, you have the defective curate model by Rusha, the quadratic model by myself and my student, then the model by Granzotto and Rahman. These are not Kerr models, but these are cubic transmuted models which they have discussed. So we study the GTC in detail, and these results are very intuitive. So I have excluded the proof, though they do have a theoretical proof. Now this is a relationship between the hazard rate of the model and the baseline hazard. So it's a decreasing failure. So you have that the GTC model has a decreasing failure rate if the baseline G0 has a decreasing failure rate. The failure rate of the GTC model is an increasing function of the number of competing risk M. It's very intuitive. As your risks or as M increases, the GTC model will definitely have an increasing failure rate. Now, this cannot be said about for increasing failure rates. Both these are very intuitive results. And these are the plots to show that how P is affecting. So one problem, if you look at the Kerr rate, is one would question the identifiability. Now, this is the Kerr rate form, and this is the distribution. So the identifiability of the model, especially Kerr rate models, are very challenging because you have censored individuals. You don't know what is happening after that. So issues in distinguishing censored individuals in susceptible groups from non-susceptible individuals is a challenge when it comes to Kerr rate models. When you work, because every Kerr rate model needs to be investigated for identifiability issues to obtain unique estimates of unknown parameters. So we subject our model also to the study of this. We can observe that the generalized transmuted model can be represented in this form, where UTX theta, so X is my covariate, remember. UTX theta is of this form 1 minus P plus P into G bar naught. Then the function U is identifiable within the family P and G if the equality UTX theta equal to U star X T theta star, where U is defined as above. For some P, P star in P, and G naught, G star in G. And this would imply, if this is true, this should imply P is equal to P star and G bar equal to G naught star. The identifiability of mixture cure rate model has been extensively discussed in Lee and Hannon and Huang. And from this, or appealing to the results over here, UT is identifiable for P specified as a logistic function. So GTC is identifiable if UTC, sorry, this is a special case. Please ignore this statement. The general theorem is GTC model is identifiable if UTX is identifiable. Now from Hannon and Hang, we have that UTX theta is identifiable if P is of a logistic form. So we have taken P in a logistic form, and so now we have our model as identifiable. So going to the estimation of parameters, the likelihood method of estimation seems to work quite well under right censoring. So we define Ci as the censoring time of the ith subject, Ti is minimum of Yi Ci, and delta I is the censoring indicator, X is the set of covariates, beta is the corresponding regression coefficients. And then the likelihood, this is quite direct for a right-censored model. Likelihood is given in this form. And we consider the profile likelihood approach for the GTC model. And the estimates or the asymptotic distribution do enjoy all the properties of a likelihood estimate when we use this technique. So making use of that, we now try to illustrate the likelihood method or look into confirm whether the likelihood method works for this. It is often observed that in some clinical data on cancer survival, the hazard rate decreases exponentially with time. So this motivates us to take the Gompertz distribution as the baseline distribution in the GTC model. The survival function of the Gompertz is given of this form. And if you observe, when A is less than 0, the survival function corresponds to a proper Gompertz distribution, and for A greater than 0, it is an improper distribution, or you can use the Gompertz distribution as such to model. Excuse me. You can use the Gompertz distribution to model long-time survivors. So we use this model as our baseline distribution. And the general transmuted class of Gompertz cure rate model is now given by equation 21. The cure fraction of this model is given in this form. And the likelihood corresponding to our example is as in 23. We also consider the Bayesian inference procedure to estimate the parameter, and the posterior distribution is proportional to the likelihood, and we have 3 parameters where pi A, pi B, and pi beta, they are the prior parameters independent of each other. They have independent distributions. And we take them as gamma and beta to have a normal prior. The joint posterior distribution is obtained as this. So as you can see, the likelihood is not very conducive to analytical solutions. So we use standard MCMC procedures to solve this. Now, if you're considering a case of 2, the GTC model reduces to the shifted Bernoulli-Gompertz cure rate model, and you can use any cure rate model as a baseline for this GTC model. Even we have a very broad class introduced by Rodrigues, all that can be also used as the baseline distribution. So under two censoring percentages, that is 20 and 40, we carried out the maximum likelihood estimate. Though it is a little compromised for small sizes of 20, it works extremely well as the sample size increases. This is like consistent with the theory. However, for sample size 25, it is not that bad. So these are the plots of Q rate for samples of n equal to 25, 50, 100, and with 20% censoring. So you can see that if you have a fairly large sample size, you can have a good prediction of your Q rate. For this, for 20% censoring. The same thing follows for 40% censoring, though for size n equal to 25, we have to be a little careful, but otherwise it works well. The same can be said for the Bayesian estimates using informative prior. It seems to work quite well. We use the MH adaptive package in R to obtain this. So this is what we obtained. And we now apply it for the malignant melanoma data. This data is available in the TimeRec package in R, and it includes 205 patients, those who are diagnosed and treated for malignant melanoma between 1962 and 1997. Now, this data is relating to the survival of patients after operation for malignant melanoma collected at the Odense University Hospital by Drebesky. I hope I pronounced this right. Survival status is denoted by numeric vectors 0, 1 alive and dead from the melanoma and dead from other causes. So here, here M is equal to 2. You have dead from melanoma and death from other causes. The observed time t ranges from 10 to 5,565 days and refers to the time until patient's death or censoring time. Here the censored observation, 65% censoring is seen in this data. So we fitted a lot of models into a lot of Q rate models in literature as well as for different baselines, and this is what we saw. This is what we saw. The generalized exponential Q rate model by Kannan et al. And then we gave the standard mixture Gompertz model, then defective Gompertz model by Rocha, shifted Bernoulli with Gompertz model, destructive negative binomial by Rodrigues, shifted Bernoulli destructive negative binomial Q rate model. So these are the different baselines we used. And then we saw that this model seems to work. The negative binomial model, destructive negative binomial Q rate model of Rodrigues. This seems, when that was used as the baseline, that seemed to work well in all in this data. So we validated this through our bootstrap technique, and this was consistent. The results were consistent. And this is the plot of, as a sort of validation.
Excuse me, madam?
Yes. I have time, 5 more minutes.
Madam, can you conclude?
Okay, okay.
Yes,
so
madam.
This is the Kaplan-Meier. This is a type of validation. So we took 2 covariates also. And included that in our Bayesian inference. So This is what we obtained with the covariates. So the negative binomial seemed to work well. And this was the cure rate for the covariate ulceration status absent and present. So this is also very intuitive and consistent with previous studies. Now, second is our bone marrow transplant data. So this data has, let me show you, this has 6 competing risks. And this is analyzed by Fiocco in 2005. So this has also been analyzed using these covariates. And our model with a DAGM baseline has given a good fit for this. So the conclusion is we proposed a general class of transmuted cure rate models motivated by rank transmutation of improper distribution, which accommodates more than one competing risk. The identifiability issues were studied. The cure fraction of the model is obtained in this form. And an example is proposed to illustrate through defective Gompertz as the baseline distribution, and also the many other baseline distributions were considered in, like, illustrating the applications of the model. So these are the references. Thank you.
Any questions from audience? Okay, no questions, madam.
Yeah, I have
Nice presentation.
No, Sudhir has a question.
Tell me, sir.
Dr. Sudhir has to say something. Yeah.
Yeah, we here this covariates is considered in the Bayesian setup only. Is it?
Covariate?
Sir, considered only in the Bayesian analysis setup.
We did for the data in the covariate, but we did the simulation work also. I didn't present it here.
Yeah, and one more thing, we have a semi-parametric analysis for this type of situation, where we don't consider any baseline distribution.
Okay. No, that needs to be developed. So we simply looked at this competing risk, and I was like concerned about that W naught equal to probability of W naught equal to infinity equal to 1. We tried to reduce, and we saw that it just reduces to a very well-known transmuted distribution.
Okay, thank you.
Yes, sir.
Sir, your mic is muted, sir.
Gopal sir, please unmute your mic. Gopal sir, please. Professor. Your mic is muted, Professor Gopal.
Gopal sir, your mic is muted.
Okay, if m is equal to 1 in your equation number 15, that HIT will be equal to H naught of T.
Yes. Then it reduces to the baseline distribution, which is once again an improper distribution. And any improper distribution you can use to model a long-time surviving data. So that has been worked by Rosha. He has done a good work on simply using improper distributions.
The proportional hazards, that and all is not applied here.
That is exactly what Sudesh was pointing out now.
Okay.
He said there is scope for, I understand his words now. He says there's scope for work.
Thank you.
Very well presentation, Professor Hasan.
Thank you, sir.
Yes.
Okay.
Take care of your health.
This is common, sir.
Thank you.
Okay. Thank you so much.
Madam, very good presentation on cancer patients and all things. Now I'm question Jayashree madam. Jayashree madam.
Yeah.
Yes, madam.
Excuse me, the chair, please introduce the
Madam.
Briefly and.
I will introduce Jayashree madam. I'm a professor, madam. Professor G. Jayashree completed her MSc Statistics in 1995 and PhD from Osmania University. He has 27 years of experience. She published 15 research articles in the various national and international reputed journals and presented 10 research papers in the national and international conferences. She recently organized an international virtual conference on statistics and data science theory and practice for progress and perspective in collaboration with Indian Society for Probability and Statistics during March 11th to 13th, 2022, and also organized one-day pre-conventional international virtual workshop on data and statistical sciences on 10th March 2022. And she organized many national level workshops, faculty development programs, symposiums, and conferences. She is member in statistics and member of Department Committee of Statistics 2007. She is member of Doctoral Research Committee since 2017. She is also a member in Board of Studies in many colleges and universities. She is a life member of Indian Society for Probability and Statistics and Society for Development of Statistics. She is elected as Treasurer for Society for Development of Statistics for the period 2018-22 and 2020. She worked as Chairperson BOS in Statistics, Osmania University during 2017-19 and worked Head Department of Statistics of Osmania University, Department of Statistics during 2019 and 2021. Recently received an Outstanding Woman of the Year 2022 award on behalf of International Women's Day celebration by the NSS unit of University College of Sciences, Osmania University, Hyderabad. Presently, she is the Vice Principal of University College of Science, Osmania University. Now, I am requesting Jayashree Madam to continue her talk.
Thank you, madam.
Jayashree Madam. Thank you.
Thank At the outset, I would like to thank the organizers and especially Professor Satish Kumar sir for giving me this opportunity. Thank you, sir.
Madam, Nikhil will share from here.
Thank you, sir.
Just a minute.
Thank you. So today I am going to speak on a new type of power series. One of my students along with me, and the base level idea of this is when we take the ratio of any two generating functions, what is going to happen. So series distributions which are well documented in the literature. So using those particular distributions, we have derived this particular new type of distributions. Now, contents of this present talk are contents of this present talk. Next slide, please. Is next slide. is introduction, literature review, power series distributions, derived power series distributions, and examples, applications. So here, as all of us know, as I said already, we have many types of power distributions with finite parameter space and continuous distributions also. And in the discrete case, we have the parameter space as the finite or infinite parameter space. So in the finite hypergeometric distributions, and in the infinite case, next slide please, in the infinite case we have the geometric Poisson negative binomial distributions. Now using these particular distributions or derived distributions, the compound distributions, modified distributions, generalized distributions, truncated distributions, which have various applications in statistics. In the theory of discrete probability distribution, several methods have been proposed in the literature for to get the probability existing ones. So compounding of distributions, if f of x theta is the original distribution and the parameter theta follows some other distribution, if it is taken not as a constant but as a random the distribution, then we call it as a compound distribution and it is denoted by f theta hat g. So when we take the example for such a distribution is if x follows Poisson distribution, which is the parameter which follows some other distribution, say gamma with the parameters as alpha beta, then the compounding distribution is nothing but it is a negative binomial distribution. Next slide. Category of distribution is the generalization of distribution. That is, in this particular case, if we have two probability generating functions or distribution functions, P1 of Z and P2 of Z, functions of two distributions, then their argument can be written as P1 of P2 of Z in a polynomial in Z with non-negative coefficients. Also, when Z equal to 1, then we will have 1 is equal to 1. Thus, there exists a discrete probability distribution corresponding to P1 of P2 of Z, and this is generalized by a generalizer G. And generally, we denoted by this. The next category of distributions, next slide please. The next category of distributions is the modifications of distributions. Now in this particular modification of distributions, what we do point, this is specifically for the discrete case. At a particular point, if the probability is concentrated more, if the probability of occurrence of that particular value is more, then that probability is all other points of that particular distribution, then the new distribution, we call it as modified distribution, or it is known as zero inflated probability distribution or probability with added zeros. In this occurrence of zero will be more, so that probability we take it and we will distribute it among all other values of that particular distribution. And if the original distribution, next slide please, if the original probability of x equal to k at different values taken by k, then the modified distribution with added zeros is p naught dash equal to alpha plus 1 minus alpha p naught, and p be taken as a linear combination of the probabilities. Now we have the next one. Next slide, please. We have the next one as the truncated distributions, wherein we truncate the values of the distribution at a point, and we consider the values of the random variables x1, x2, xn in a given region are excluded. We truncate at that particular point, and those probabilities are added up to the next values. Then the joint cumulative function is of the variable function, where r is the complement of the random variables and comprises of all the points that are not truncated. So this particular distribution, we call it as truncated. New distribution which we get it is g of x equal to f of x by probability of x greater than a. Next slide, please. The next category of distributions is the power series distributions. A series distribution, if its probability mass function can be arranged as, or it can be represented as ax theta power x by f of theta, where f of theta is summation ax theta power x. And this particular earliest found by Professor Nock in 1950, and Professor G.P. Patil in 1961-62 has made a thorough investigation of this class of distributions and studied their properties. Sekara and Tonkin in 1992 have introduced a discrete probability distribution in connection with certain survival process. So the probability mass function related to this is px equal to x power alpha summation x power alpha q power x. This distribution also belongs to the family of power series distribution for a fixed alpha. Next slide, please. Next slide, please. Thank you. Ahsanullah had shown that the first two central moments of the power series distribution the power series distributions like the binomial, logarithmic series, negative binomial, etc. And Razak and Patil in 1994 have discussed certain stochastic characteristics of the power series distributions with their probabilities. Next slide, please. Generalized power series distributions. These were actually thoroughly studied by Professor G.P. Patil. Next slide, please. I already told you that we define the probability mass function as ax theta power x by f of theta, where f of theta is summation ax theta power x. And the mean of the generalized power series distribution series distribution can be expressed as mu equal to theta into f dash of theta by f of theta, whereas the variance is given by the equation 1.3. And the probability generating function of the theta by f of theta given by equation 1.4. Next slide, please. Examples of this power series distributions is negative binomial distribution comes under this particular to the power minus n, and ax as minus 1 to the power x into minus nc x, where theta is nothing but p by 1 plus p, and it lies between 0 and 1 for n greater than 0. Geometric distribution also can be also comes under this particular category. And then we have the Poisson distribution. Next slide, please. It also comes and next slide, please. So here, this particular power series distributions gave us a thought that why can't we take the ratio of two power series and using the result from Abramovich and Stegen book, we have Abramovich and Stegen research paper. We have which says that when we take the ratio of two power series in the same variable, so using that particular result, we have taken the ratio of two probability generating functions as they generate the probabilities, so that it will give us the probabilities of the new distribution. So probability of x when we took the ratio of these particular two probabilities, it gave us the new distribution, and that new distribution in general is again a discrete probability distribution. The distribution is a proper probability distribution when we take di as given in 3.5. Next slide, please. Next slide, please. di and in dash, and pi is given. Pi is nothing but the probabilities which are given by equation 3.4, and it gives us a proper probability distribution. Now, this particular new power series distributions. Next slide, please. Next slide, please. And we have shown that these particular new distributions, they are proper probability distributions. Next slide, please. Next slide, please. Here we can see that the total probability is 1, and then we could find out the probability generating function of this new derived power. Slide, please. And next slide, please. We have found that the mean of this new derived power series distribution is nothing but it is the difference between the means of the numerator and and similarly, we have found that the variance is also the difference between the variances of the numerator and denominator power series distributions. Next slide, please. Next slide. And we have derived a new one with a special case as the geometrical Poisson distribution, where in which we have taken the ratio of the geometric distribution probability generating function, and we got a new power series distribution. Next slide, please. By taking the pi as p e power lambda di and di as given by using equation 5.5. Next slide, please. And we could prove that this particular new distribution is also a proper probability distribution. Next slide, please. Rating function and its mean. When we took the mean, again we have observed that the mean is the difference of the two means, and variance is the difference of the two variances of the two distributions taken. Next slide, please. So in the example, slide number 35. Okay. In the example, we have considered number of accidents that occur to 650 women, and in this parameters P hat, Q hat, and we fitted the distribution. We fitted the geometric distribution. Next slide, please. And to the same when we compared, the Poisson distribution is not a good fit, but the geometric distribution was a good fit. And when we took the ratio of both of them, that is the new distribution, we got it as a good fit. So in the three cases, next slide, please. In the three cases discussed, we observed that chi-square is smaller in geometric or Poisson distribution when compared to geometric and Poisson. The graphs, next slide, please. When we have drawn the graphs, these are the graphs related to the Poisson geometric and the geometric or Poisson distributions. Similarly, we have taken of negative distribution. Next slide, please. Negative binomial distribution and geometric distribution. Their ratio is again a derived power series distribution, and it is also a proper. Even the mean of this new derived power series distribution is the difference between the means of negative binomial and geometric distribution, and the variance is also the difference between the variances of the two distributions. Please. And slide number 43. For this particular example, the data is related to the number of cells in experiment. For that particular data, we have fitted negative binomial distribution, geometric distribution, and negative n-bino geometric distribution, that is negative binomial and geometric derived power series distribution. And we found that when compared to the other two distributions individually. And slide number 45, we have drawn the graphs for all the three distributions.
Yes, madam.
Yes. Yes, ma'am.
Can you conclude within 2 to 3 minutes, madam?
Thank you for reminding me. Thank you. So here we slide number 46. We have this new distribution, that is the binomial derived power series distribution, wherein which we have taken. We have found that it is a proper probability distribution, and not only that, we have derived many of its properties. Slide number 48, we have proved. Slide number 48, we have proved. And slide number 49, we have derived many of its properties. and like mean, variance, mu3, mu4, skewness, kurtosis, all those particular properties of that particular new found out its mode, and the distribution, the new derived distribution is a leptokurtic distribution that is given in slide number 53. Slide number 53, please. Distribution, and then slide number 54, we have the graphical representation of this particular binomial distribution. If for various values of P, Q, N1, N2, we have drawn the graphs. Slide number 55. Slide number 56, these are the bibliography. Particular study. And our conclusion is that these models, if not better, they are equivalent to the already existing models, and this is a new distribution, especially for discrete case. Any questions or suggestions?
Thank you, madam. Any questions from audience?
No, I have a question.
Yes, madam.
I could not follow it fully, but I could not see the slides also. But still, I thought I saw that you took the ratio of two power series, and you had the mean mu1 minus mu2.
Yes.
And sigma 1 minus sigma 2.
Sigma 1 square minus sigma 2 square. Yes.
So, are you putting any constraints that sigma 2 should be less than sigma 1?
Put the conditions on the parameters.
You have put the conditions?
Yes, yes. Conditions on the parameters exist.
Okay, okay.
Any other suggestions?
Okay.
Okay, no questions. Thank you, madam.
Thank you all. Thank you, Professor Satish Kumar sir.
Thank you. Thank you. Thank you, Professor Jayshree.
Yes, sir.
And thank you, Professor Asha, for your nice presentations. And also, we would like to extend our gratitude to Professor Sarojamma for chairing this session. Let us move
Thank you, sir, for giving me this opportunity.
Thank you all.
And thanks, guys, once again. Thank you all, organizers.
Yeah.
Thank you, sir.
Thank you. Now we let us move to the next session. Here, Professor Parimal Kumar is here to chair the session, and Sudhish. Two speakers are there, including Sudhish and Manik Avele. And let us, student, Anjana, 45. Aishwarya, okay. Aishwarya, please introduce the chair and do the needful for the further proceedings.
Thank you for the warm introduction and first of all, I would to put thanks to the organizer of the conference, Dr. Satish Kumar, for giving me an opportunity to chair the session here. So this is session number TS35, and we have two presenters here. So the first presenter is Sudhis K. Kachmanil. He is present. I can see his name. And the second presenter is Manik Awale. So he is also present. I think only one presenter is present at this moment.
Both speakers are here in the group.
Manik is also there. So Manik Awale is also there. So the first speaker is Sudhis K. Katumanil, and he will be presenting his paper, A New Method for Analyzing Transformation Model for Computing Risk with Cure Fraction. So because we have only two speakers and the time is about 1 hour, so you can flexibly present your paper, and I invite you to now present your presentation.
Just sharing. Shares. You can see anything?
Yeah, it is coming, but now you can see your now the okay now
yeah,
it is fine.
It's there. It's there. Yeah.
Okay. I think my I don't know, somehow my both these things are not coming. Means my face and this presentation. I don't know what is the reason. Okay. So thank you, Professor Satish Kumar, for inviting me to this conference to present some of my recent work. This is a joint work with Professor P.G. Shankaran of Cochin University and Dr. Sridevi EP of Maharajas College, Ernakulam. And today I'm going to present a new method for analyzing transformation model for computing risk data with a pure fraction. We have already listened to Professor Asha Gopalakrishnan's talk. He is my teacher, and she given a nice overview of a pure right model. So my task is actually simple. So this is the outline of my talk, motivation, basic concept, then we will introduce the model and our new methodology, and then some computational algorithm, asymptotic properties, and then some simulation and data analysis result. Why we go for pure right model? In survival studies, researchers generally assume that all the study subjects will experience the event of interest if they are followed long enough. However, in some situations, a non-negligible portion of individuals may not experience the event of interest even after a long period of time. So normally we consider a censored case. Those individuals cannot be treated to be a censored individual and can be considered as cured individual. This is the scenario. So one need to consider the entire population is a mixture of two groups of patients, susceptible and non-susceptible. This is the mixture cure rate model. There are some other model also that I am focusing on this mixture cure rate model. We have seen several models in the last talk. Yeah. So why go for computing risk? Yeah. In survival studies, computing risk refer to the situation where failure of an individual may be attributed to one of several causes or types. Consider an example from a clinical trial on HIV infection and AIDS of 329 homosexual men from Amsterdam, Dam reported in Discuss 2015. During the course of period from HIV infection to death, there may be two type of causes. Two types of process can happen. Thus is actually the virus may be switched to SI phenotype and AIDS. So note that both these conditions affect the disease progression differently. Hence, it is important to observe which infection has occurred first. So that is why we actually interested in competing risk data. Then why competing risk data with cure? If you look at this example, an interesting characteristic of the data is that time of occurrence of this event vary from 0.112 years to 13.936 years. So this actually gives, okay. We also found that after 12.4 years, there are only 3 events observed. However, around 14.5% of the total lifetime reported are larger than 12.4 years. So this is why we suspect that there may be the presence of QA individual in this time. So that is why actually we are interested to model the data using competing risk as well as the pure fraction. So this is why. So this is the basic setup. We know later Tj with the competing risk data with pure fraction, but T denotes the time to the first event, and J is equal to 0, 1, K. Here, this J equal to 1 to K indicate the failure of a subject is due to one of the Kth causes, and J equal to 0 is used to denote the pure fraction. And we also consider a covariance set with a three-dimensional covariance, possibly time variant. And we denoted this pi k theta is the probability of experiencing an event of interest for given set. And pi naught theta is the pure fraction, there is a theta is missing there. So how to model this data? We have competing risk as well as pure fraction. So in these cases, T can be decomposed as this expression, where this I is the indicator function. And, now, the overall survival, how to model this T, this is the question. So mixture cure rate model, where we have a mixture of cured and non-cured individual. We assume that the overall conditional survival function of T given set as the representation given by this one. So you can see that we have a S of TB by 0 theta plus summation K equal to 1 to K pi K theta into S of KT. And how to proceed further? If you wanted to estimate the survival function, how to proceed further? That is a question. So what generally we do is we model these two things separately. We model pi k theta and sk separate. And normally we use some transformation model or some semi-parametric approach to model this sk, where we use logistic regression to estimate this probability pi k theta. So this is actually we have two models, so it costs a lot of time. So this is why we actually thought about a new methodology for analyzing or finding this overall survival function. That is the motivation. So there are some recent work where you can see that using this transformation model. Yeah. So we use a linear transformation model for modeling sub-distribution function. So this is the idea. So we use a linear transformation model for modeling sub-distribution function of complexity. So what is the advantage? The probability of experience in an event K need not be estimated separately by means of logistic regression. So we have a lot of advantage. You don't need to go for a separate modeling. From one model itself, you can estimate this your probability as well as the overall survival function. Yeah, this is the just to give an idea what is linear transformation model. Suppose T, C, and Z denote the survival time, censoring time, and p-dimensional covariate vector, respectively. Let H be a completely unspecified, strictly increasing function. Then the linear transformation model is specified by H of T is equal to minus Z beta plus epsilon, where epsilon is a random error with a known distribution function. And the distribution function G and is independent of the covariate Z. And beta is a unknown p-dimensional vector of regression coefficients. The linear transformation relates the transform survival data to the covariate. And if you look at this too, one can easily find, maybe easily observe that if you put some distribution for this epsilon, it reduces to well-known model like proportional SAR model and proportional Peirce model. That is the why it's a very useful model. So if you look at this Cox proportional hazard model, and using some algebraic manipulation, one can write this. So now from the model, one can see that hence a pH model is a special case of linear transformation model when epsilon follows extreme value distribution specified by the distribution function 1 minus e power minus e. And the same way one can easily see that the Cox proportional odds model also is a special case of LT model, where epsilon follows logistic distribution with the distribution function. So if you want to know about more about this model, LT model, one can go through this paper by Docs. And there is a nice review in JSPI by Guo and Zhen about the semi-parametric models used in survival analysis. LT model normally we consider as a semi-parametric in the sense that we know we have epsilon has epsilon normally don't specify, so that is why. Yeah. So I will discuss the method how. First, we express this overall survival function in terms of the conditional subdistribution function defined by this probability of t less than or equal to t, j equal to k given set. You can see that the subdistribution function is very famous in computing this analysis. We can see that this is just the probability that it failed due to some force k. And we express this subdistribution function, conditional subdistribution function this way, and then substitute these things to our conditional survival function. So we get this expression. Now, if you look at this expression, one can see that we can use this subdistribution function to find the overall survival function. So in this proposed method, we formulate the conditional subdistribution function to a class of linear transformation model specified by this. And you may be wonder why this is like this. This is actually the same as the this LT model which I showed earlier. Some manipulation one can obtain these things. So we have this. So we use this. And then you can use that. Yeah, this is the very nice paper by Chen et al. They actually discuss this linear transformation model and propose an estimating equation for finding the estimators of regression coefficient. Yeah, using that, you can see that we have a conditional survival function of t given z is given by this. And from this representation, it is clear that we can find the overall survival function of t without estimating pi k theta. So you can save a lot of time, computational time. Now the question is, if somebody is interested to estimate the cure probability, whether our model allows us to do that. Yeah, so you can see that by the definition, we have this probability of j equal to k. Given z, we have this. This is we have a joint distribution, then you know how to find the marginal. So this is the way. So we have this using this. We can see that from the proposed model itself, we can estimate the cure probability using these equations. So that is the beauty of our method. So we then we actually obtained an estimating equations. So this is the observed data. We have this is the usual setup. Right hand side case with the founding risk. Yeah, this is the idea. Let lambda kt and lambda kt is the conditional cost-specific hazard function and cost-specific cumulative hazard function. And then we consider some counting process. This is the NIKT, with the counting process associated with the failure time of the ith subject to course k. And if you know a little bit martingale theory, one can see that the counting process. This is a sub-martingale, and you can do some martingale associated with all these things. The main idea is actually for the intensity function corresponding to this counting process can be associated with the hazard rate. That is the main idea. So we always use this counting process to find the estimating equation. So because it has we can have a martingale associated with this counting process. So using that, one can find the estimating equations like this. So this is the estimating equation we developed for finding the estimators of regression coefficient as well as this HK. So computational algorithm says the estimators of beta k and HK are obtained as the value that solve the equation 7 and 8 above. And maybe you can simplify these things. I'm not going to the details. Yeah. So this is an iterative algorithm where we choose an initial value for the beta and then find HK, and then next we find bk and you repeat this step 1 until convergence of beta. So asymptotic properties, we have some notations anyway, and we'll skip this. So these are the under some regularity conditions, one can easily prove that beta k hat and hk hat are consistent estimators of beta k and hk respectively. We prove the weak law. weak consistency. Under the regularity condition d1 minus d, you can see that as n goes to infinity, root n into beta k hat minus beta k converges in distribution to multivariate normal with the mean 0 vector and covariance vector sigma k, where sigma k have this expression. So we proved the asymptotic properties of the estimators we obtained, and then we did some Monte Carlo simulation. We consider two models where the post-specific hazard function is specified by these things. So here you can see that if you put r equal to 0 and 1, it actually reduces to proportional hazard model and proportional modes model. And yeah, the covariate Z1 is generated from Bernoulli distribution with the probability of success is equal to 0.5. And yeah, for T, how we generate T using the model expression, this one, when r equal to 0 and when r equal to 1, we have some other expression. This you can obtain from that model specifically. And one can see that we have very nice result. You can see the bias and mean square error. Beta 1 equal to 1, beta 2 equal to 1, and then another set, beta 1 equal to 1 and beta 2. So this is for a proportional hazard model, and this is for proportional force model. There are some mistakes. And, oh, this is also proportional hazard model with the different values of beta. And then we have the result for proportional odds model. You can see that now we apply our proposed method to a data obtained from a clinical trial, HIV infection and AIDS of 329 homosexual men from Amsterdam. I already discussed about this data. And then, yeah, this data is actually available in R package and state. And as I mentioned, we have two courses, SI and AIDS. So we are interested in combating risk setup, and we also see that there is a possibility of cured fraction. So we are interested to estimate the cure fraction, cure probability, as well as the effect of this age and age and the presence of CCR5 chromosome. You can see the presence of WW, absence of the CCR5 delta theta. So we wanted to know the significance effect of these things. So we analyzed the data assumed pure fraction with our model. The regression parameters were estimated using proportional hazard model and proportional odds model. And this is the coefficient. One can see that the standard error and p-value. You can see that age is actually not significant. One can easily see that the age is not significant. And if you look at this plot, this is the plot for CIF. And then we estimate the cure probability using our model. For that, we actually classify this as a four-group. For that, we have age into two groups this way, age less than 34.5 and age greater than 34.5. This 30.4.5 we took because it is a median age. Then we estimate this QR probability. This is the probability. And we also estimate this QR probability using logistic model, ignoring the costs. Then one can see that there are a lot of inconsistency in the logistic model. And from this table, one can also see that the age does not have much effect on the pure fraction, pure probability, because it is same in both the cases. So what it tells you doesn't matter which age you infected with this virus. This is an important information, right? And if you look at this, what is the guarantee that our results are good? Okay, we got a consistent result, but here you can see that there are. And you see, if you look at this Kaplan-Meier plot, you can see this here. You can see that here we have just below this 0.2. You can see in one cases we are estimating this 0.1575, and another case 0.44. And this is what you can see here. It is above the 0.4. If you look at this Kaplan-Meier curve, one can observe that the pure probability obtained using our model is somewhat accurate. I hope we hope that our method will have a good impact on pure rate model. We develop a new method to analyze the community risk data with pure fraction. And this is my conclusion. We formulate the CAF using LT model. The new method enables us to estimate the pure fraction from the model for C. We illustrate the proposed method using data for AFs. So, and we actually sincerely hope that this has a good impact on the research of pure rate model with computing risk, because it's a new model. It gives a lot of advantages. And yeah, this is some of the references. Anyway, I am happy to answer some of the questions if I know.
Thank you, Dr. Sudhish, for this wonderful presentation. So before we open the house for the interactions and the queries, so let me introduce Dr. Sudhish to the audience. So Dr. Sudhish presently is working as associate professor at ISI Chennai, and he is a brilliant researcher, as is evident from his quality publications, and he has been awarded Dr. C.R. Rao Gold Medal in Statistics in 2021, instituted by ISPS, and he is also the recipient of one of the, you can say, most coveted prize among the young researchers, that is Jane Tingaban Award for the young statistician from developing countries. And he has a vast experience of working in the universities among the across the globe as a postdoctoral fellow, and we are thankful for sharing your work with all of us. And the presentation was good, and I believe that most of the young students who are attending the this conference must have learned the newer ideas of application of such kind of pure fractions models in their particular expertise. So thank you, Dr. Sudhish, for this wonderful presentation. So I have one or two queries. One is that while you have talked about in your presentation about the simulation of the data, and you talk about this MC simulation. So have you used some particular algorithm because the functions that you have used are not the standard functions?
No, actually we use our own program. We have a computational algorithm. Now we use that algorithm and we write our program, and then actually it is just accepting stage. It will be available. All this program also available.
Okay, so that algorithm is
actually a minor revision submitted yesterday. So
okay, fine.
So,
Now, is this model is applicable for other kind of studies also, as you have talked about the AIDS? So, is it applicable for other disease-related studies or in industry also?
yeah, wherever we are actually interested in this cure rate model, we can play this. There is no specific to biostatistics or something.
Okay, that's great. That's it. Now it is open for audience queries.
Sudesh, I have a question. It's a wonderful work, first of all. Secondly, did you consider censoring percentage?
Yeah, we actually in the simulation we consider censoring percentage.
Okay. You have I think I missed it.
Yeah.
So in the data,
I mentioned that it is actually the censoring variable are generated from uniform 0C, where we have probability of t greater than c is equal to 0.2 and 0.4.
So your data had how much censoring percentage?
See, data, if you look at this data analysis, I don't know, my thought is that we should consider it as a pure fraction than trying to estimate. We have around 40 point, around 16 point or something censoring percentage. But we assume that it is not censoring. We assume that it is a pure fraction. That is our feeling.
Okay. Okay, nice presentation. Very good.
Hi, Dr. Sudesh. It was a nice presentation. And my query is regarding the pure fraction, what you have estimated. So based on the pure fraction, can you say that which one is the better model?
Which one is the better model? Means we compared with the standard technique. So then we see that our model is better if you compare with the Kaplan-Meier plot. So we don't have any other theoretical justification. But if you look at this Kaplan-Meier plot, we see that our estimator is somewhat near to the one which given by this Kaplan-Meier.
Whether it is based on some information criteria or?
I didn't go through that. Maybe I can think about it. Yeah, we can find the AAC in both the model. Yeah.
Yes. Thank you.
Yeah. Okay, thank you.
So any other query from any other audience? So thank you, Dr. Sutish, for this wonderful presentation and sharing your work with us.
Okay.
So now,
thank you all.
Fine. So now I invite Dr. Manik Kawale for the presentation. So let me introduce Dr. Manik to the audience. So Dr. Manik Kawale, presently working in the Department of Statistics at Savitribai Phule University, Pune, as assistant professor, and his area of interest include modeling count time series data and the statistical process control. So today he is going to present his work on integer autoregressive model with seasonal structure. So welcome, Dr. Anik, and you may present your work. Dr. Manik, are you there? Yes, it is coming up.
Is it visible?
Yes, it is visible.
Okay, thank you.
You can present, yeah.
So, first of all, I must thank Professor Satish Kumar and Kerala University for organizing this conference and giving us opportunity. So today I'll be talking on the integer autoregressive model with seasonal structure. So this would be the outline of my presentation. First, we shall see some motivation, then model, then how do we estimate the parameters, how do we forecast, and some simulation study, and the data analysis at the end. So we have a data on this Campylobacteriosis disease. These are weekly cases of a disease. And if you see the time series looks like this. And these are all counts. So as it is number of cases of a particular disease, these are all counts. And you can see here these counts are smaller, 0 to 10 max. But I can't see the seasonality just by observing this time series, but most of the time we can observe it. But if I plot the ACF, I can see the seasonality in the data. And we can see it's if these are the weeks, we can see around the yearly seasonality. And we know the most of the diseases have these seasonal patterns, mostly with weather, like influenza, cold, etc. And so this ACF gives us the idea about the seasonality in the data. If we use non-seasonal model which is for the seasonal, we cannot have the good forecast. So we should take care of the seasonality in the data. Now, how do we get the data? So for this integer autoregressive models, we use this thinning operator. So there are two thinning operators presently we are using. One is binomial thinning operator and second is negative binomial. Now, how do we get the data? So I have some graphical presentation for it and two different scenarios. In first, we have T0 to T3 and it goes on. So suppose initially we have 3 infectives and they can lead to some 4 infectives in the another time point. And these two different color dots or pictures are these new arrivals. They are independent of the previous cases. So these 4 we represent it as a cases generated by the previous cases, and these 2 are the independent. So we call it as we can say immigration or innovation. So they are coming from a different source. And similarly, so they together will give rise to one case and these 3 new arrivals independent of the previous cases, and so on. Sometimes it may be 0 also. And similarly, this is another scenario where we have 2 infectives and we can have the process goes on. So, so this is how we get the data. So this is the say number of cases in first week. These are the number of cases in second week. These are number of cases in the third week and fourth week, and so on. Okay, and we are trying to model this data. Okay. Now we have. So this is the definition of the process: a discrete time non-negative integer valued stochastic process is said to be a negative binomial seasonal in our process with seasonal period s, and given by the equation 1. Now here we are using a negative binomial as a marginal distribution, because if we have over dispersed data, Poisson is not of much help. So it's better to use geometric or negative binomial. But negative binomial is generalization of geometric, so it's much better than the geometric. But it should follow some conditions. That xt is a sequence of random variables with negative binomial distribution, and its form is given like this. Second, this epsilon t is an innovation sequence. It is IID non-negative, and it is independent of the previous cases. It's like if you see in equation first, so the first component is alpha star xt minus s. It is sometimes it is called as alpha composed xt minus s and epsilon t. So alpha composed xt minus s is the number of cases generated or somehow lead by the number of previous cases, or the number of cases in the previous week or previous day or something like that. The previous time point in a time series. And these epsilon t's are the innovations, these are the new arrivals, or these are independent of these previous cases. This may be from another city or maybe because of another source. Okay. And so we say that for m less than t, this epsilon t and xm are independent, and they are all independent of ws also. Oh yeah, I forgot to define this alpha star xt minus is actually, this star is called a thinning operator, and this thinning operator is a negative binomial thinning operator. So it is alpha star xt minus is actually summation from I1 to xt minus s of wi, where wi's are geometric random variables. So this is actually sum of geometric random variables up to xt minus s. And this negative binomial thinning makes sure that this number of cases generated by the previous number of cases can be more than the number of cases in the previous generation. So it's like in last week, suppose there were 5 cases, they can lead to the 10 cases or 20 cases. But if we use binomial thinning, we cannot have this number of cases more than the previous cases. So that was the disadvantage of binomial thinning. So we are using negative binomial thinning. And here also the thinning at different time points is independent. So we are saying that this thinning of xt and the random variables xt minus js are independent. So as it takes care of seasonality, so it depends on the previous s is the seasonal period, so it depends on the previous s lag. So we have simulated some series using this model, and we can see the sample path for this series in autocorrelation function and the partial autocorrelation function. So here for simulation we have used seasonal period is 12. So we can see here this is a series, this is ACF and this is PSF. So first PSCF is significant at 12, and from ACF also we can see that the ACF is significant only for the s is multiple, so multiple of s. So it's like 12, 24 and so on. And you can see for all these cases. So for other cases it is not significant. So that actually this is one of our proposition, and we are going to see in the next slides. So these are the propositions. The SB in RS process has a unique stationary solution given by this equation. Xt is distributed as this sum. So the meaning is xt can be in distribution, it goes to some distribution of innovation, so which makes it stationary. Second is important because second makes why we need this model. So we have 3 processes previously before this process, that is NG in R1 process, it is new geometric in R1 process defined in 2009, SG in RS process defined in 2020. Before that there was another process in 2017 by us, and NB in our own process proposed. So this RISTIC is in JSPI, this is in TN is statistical papers, RISTICs in JSCS. So these are all special cases of our process, that is SNB-NAR. So for some particular parameter combinations, these processes are the special cases of our process. And the autocorrelation function of this process is alpha raised to h upon s, and this actually holds for h multiple of s. For others it is just 0. So this is the conditional distribution. So this we can call it as one-step transition probability, transition probabilities. So probability xt equal to y given xt minus s is x. So these are the probabilities for x0, y0, for x0, y greater than 1, and so on. So this we are going to use for finding the maximum likelihood estimators for the parameters. And this is the probability for if x is greater than 1 and y is greater than 1. Now for forecasting, we are using the coherent forecast. So for coherent forecast, what we are proposing is the median and mode of the forecast distribution. So for finding the forecast distribution, we should have the k-step ahead process distribution. And to obtain that, so we should write the process in k-step ahead process. And you can see from this question 2, we are writing the k-step ahead process in this form. So we are making little adjustment for the seasonality, where this q is k upon s and r is qs minus k, where this dot, this k upon s should be the upper integer part of this ratio. Okay, and here this is not a power. Alpha raised to bracketed I is not power. It's not alpha raised to I. It is the operation of a thinning operation of this negative binomial thinning I times. So only exemption is alpha raised to 1 is alpha and alpha raised to 0 is 1. So using this k-step ahead process, we can obtain the k-step ahead forecast distribution, and this can be given as like this. Whereas these are just notations P naught, eta, D, epsilon, F, and all. So, sorry. So these notations are, these expressions for these notations are given here. Okay. Now we have proposed 3 estimators for these parameters. So we have 3 parameters, alpha, P, and theta. So this alpha is actually thinning parameter, P and theta are from the marginal distribution of negative binomial distribution. So first is Yule-Walker estimator, and based on sample SAF and mean of the process and variance, we can easily find the Yule-Walker estimators using this autocovariance function. Second is conditional least squares. So here we have 3 parameters, and some parameters are some function of the initial other parameters. So what happens, directly we cannot find these conditional least squares for all the 3 together, but numerically we can find. But to find the expressions, initially we are finding the parameters estimates for 2 parameters, that is mu. Mu is actually theta p, it's the marginal mean of the process, and variance is theta p into 1 plus p, so that is sigma square. So once we find the expression for this mu and sigma square, we can find the estimates for p and theta. So first we shall find the estimators for alpha and mu, and then we'll go for the sigma square. Okay. So this expression 3 is the so by minimizing expression 3, we can find the estimators for alpha and mu, and these expressions are given here. And in the next step, we have to define another random variable, that is Wt, that is xt minus expected value of xt given xt minus s, the square. So to find the estimator of sigma square.
Dr. Manik, sorry to interrupt you. Can you focus on main results and main findings?
Yeah. So, so by minimizing this equation, we can find the sigma square. So once we get the sigma squares, we can find the p hat and theta hat. Okay. And the last one is conditional maximum likelihood. So by maximizing the likelihood from this first theorem, so this probability xt given xt minus s we can use from the first theorem, and we can maximize it numerically, and we can find the estimates. So these are the simulated results for these parameter estimates, alpha hat, theta hat, and p hat for different parameter combinations. So here we have given only 2 parameter combinations, and the rest of them are in the paper. And we can see here this MSE is in the second row. So MSE is decreasing as the sample size increases, and a maximum likelihood as it's performing much better than the other 2, as MSE is decreasing with the sample size. So we have used the 3 forecast accuracy measures to find the accuracy of this forecast. So first one is predictive mean square error, PRMSE. Second is predictive mean absolute error, PMAE, and third is PTP, that is percentage of true prediction. So first 2 should be less, and third should be more. So third is actually the 0-1 loss function. So it's whether we are hitting the exact for actual value or not. So we are using simulation, we are verifying these accuracy measures. So these are the simulated results from these. So we have simulated the data from the NB-NRS process, and we have compared with the forecast using NB-NR1 model as well as seasonal and non-seasonal model. And here also we can see that this NB-NR1 PRMSE and PMAE is greater than NB-NR seasonal model. So it means these errors are more for this non-seasonal model, whereas they are less, and it's for all the cases. Similarly, we have for table for the PTP also, and here also we can say the PTP is more for seasonal NB-NR and then the non-seasonal NB-NR model. Okay. Now, one of the reviewer asked us to simulate data from other model and do the comparison for this forecast. So now we have simulated data from the SGNRS process and found out these forecast accuracy measures for this data. And in that case also, so this SNBNR1, actually this should be S. This PRMSE is smaller as compared to the SGNRS process, though the data is from SGNRS. So because of the proposition, we have seen that is SGNR is a special case of SNBNR1. And similarly, we can see here in PTP, the PTP for seasonal NBNRN is more than the SGNRN in all the cases we can see here. So it means that our model performs better in terms of forecasting than these other competitors. So we have applied this method to one data set. This is from this Lorraine County of Freiburg territorial unit. This is German data set, and this is for 325 weekly observations for Campylobacteriosis cases. And from this mean and variance, we can see that it is over dispersed data. So we should have a over dispersed model for it. This is the time series autocorrelation function and partial autocorrelation function. This is the marginal frequency plot. So we can see that the geometric is out because in geometric most 0 is the mode. So here 1 is the mode. So we should have another model. We have another plot that is called marginal calibration plot for verification of the marginal distribution. This is a plot of f minus fn. It's empirical distribution and the estimated distribution function from this assumed distribution. And we can see here this negative binomial is much closer to the 0 line as compared to geometric and the Poisson. So negative binomial marginal is more appropriate for this data. We have done AIC-BAIC model selection criteria for this most of the possible distributions using. Among these, SNBNRS is having the less AIC-BAIC. So this is most suitable. So we have given the point forecast for the last 10 observations from the series, and its mean, this conditional forecast, that is traditional forecast, its mode, its coherent forecast, median, and highest predictive probability interval for this data. And so these are the forecasts, and you can see the most of the time mode is a better forecast in this case. Most of the time mode accurately forecast the observation as it has more PTP also. So that is the data analysis, and these are the key references we have used. And that's it. Thank you.
Thank you, Dr. Manik, for this wonderful presentation. So I have one query.
Yeah.
As I could see in your slides that your predictive MSE was little bit higher.
PRMSE.
Yeah, because your parameter was around 4 and the PRMSE was around 7.
See, what happens is negative binomial, if we simulate data from this series, you will get higher counts. And in higher counts, you are likely to have higher variation in estimation. Whereas if we have lower counts, it's your MSE is also lesser. So it's like if my actual value is 100 and hitting 95 or 105 is sometimes good, but all the counts are less than 10. In exact value is say 5 and hitting 7 or 4 is not a good forecast. So we should, so 3, that's why we have used the 3 measures of accuracy. This mean square, so it's a squared error loss, absolute error loss, and 0-1 loss. So it depends which loss you want to minimize.
Fine. So good. So any question from the audience? I think there is no question. So we are thankful to both the speakers, Dr. Sudhis and Dr. Manik, for the wonderful presentation in this session. So now over to you, Dr. Sudhis.
Thank you, Professor Parimal, for chairing this session. In fact, we missed to introduce the chair. Our students, please just once again do the, and thereafter let us conclude. Aishwarya? Yeah, please. Thank you, Professor Parimal, for
Thank you so much, sir.
sharing.
Thank you, Aishwarya, for the nice introduction.
A brief introduction is necessary to make aware our youngsters. So that is why, Professor Parimal, thank you so much.
Thank you so
also, we would like to extend our gratitude to Professors Sudhish and Professor Manik for.
Thank you.
Thank you.
Okay, thank you, sir.
Thank you.
Now let us have a break.
Share the penalized regression with the all the members of this group, that how penalized regression can be used in the not only agriculture research and other fields also. Sir, generally we do the multiple linear regression models are used in many fields in various disciplines, and there are good reasons why use the linear regression. And it is simple and also provide an adequate information and description of how two inputs affect the output. But sometimes a linearity assumption and other assumption are practically not applicable in the field of live data, and it is very difficult to get the proper interpretation from the analyzed data. And the standard linear models in a situation where we have the large multivariate data set containing number of variables are superior to the number of samples, and it is better to use some alternative method, and it is the penalized regression. And this penalized regression along create a linear regression model that is penalized. We are imposing some penalty to the original linear regression models, and it gives some parsimonious model also, some variable selection and other things. Regularized and shrinkage method is also known as the other synonymously used for the penalized regression. The consequence of imposing this penalty is to reduce the coefficient of value parameters value towards zero. This allows less contributive variable to have close to the zero, so that that variable and the predictor may be removed from the models. Multiple regression models have various problems already discussed. First and foremost is the choice of underlying functional form of the model. If researcher incorrectly formulate the initial model, and other problems are the assumption. Generally, we do not verify whether assumptions are fulfilled or that is valid or not, particularly in the normality and independence of error and constancy of error variance are the most of the assumption. And in practical situation, and I also encounter that we do not go for this normality, independence and other testing for the available data. The prediction accuracy can sometimes be improved. It can be improved by shrinking the sum of the coefficient towards zero by allowing a little bias, the variance of the parameter estimates, and further with large number of predictors, the interpretation can be improved if you use a smaller subset exhibits the strongest effect. And there, here I'll discuss the three main penalized regression model. Very first is ridge regression, and that ridge regression is already very much popular, but it is not properly used in the field of forecasting and statistical modeling in practical situation in the field of agriculture and related field. Rigid regression shrinks. That the shrinkage and penalized techniques have been proposed to improve the OLS estimates. In particular, rigid regression, which is given by the Horrell and Kennard, and minimize the residual sum of squares subject to penalty of L2 norm. Here we look here that L2 norm. This is the L2. This is normal. We have the multiple linear regression model. This is the, and we are giving a penalty. This is the penalty we are imposing, so that sum of the coefficient, square of the coefficient should be less than the some desired or some particular value. If you go the estimation process of this rigid regression, this is minimized. We are there's a mean square here, and if you go to the final stage of this model, this is the beta reach somewhere like this, lambda I x prime. This is the penalty term where I is here the identity matrix of dimension p, how many variables we have in the model. In the shrinkage of coefficient is achieved by penalizing the regression models, and the amount of penalty, this is lambda is the amount of penalty, can be that penalty can be means we can select some proper techniques how to this penalty can be used. There are many methods to get this lambda penalty value. There are many methods how to get this penalty. When lambda is equal to 0, if you go the lambda is equal to 0, that is originally come to the multiple linear original model, and if you give the value of lambda as per the proper techniques, we get the proper parsimonious model, and we get the however we get the some variance of the estimates of parameters would be somewhat more, but we get the parsimonious and other desirable things from this modeling by using the rigid regression. The amount of penalty can be fine-tuned using a constant called lambda. Selecting a good value is critical. Already I mentioned that this is the value is critical how to get this. And before going to analysis of data, we should standardize our input data just like a standard neural variate we can transfer, so that comparison would be properly done for one model to another model. The contrast in the ordinary least square rigid regression is highly affected by the scale of predictors. Therefore, it is better to standardize the predictor before applying the rigid regression, so that all predictors have the same scale. One important advantage of this rigid regression, it still performs well compared to the ordinary least squares in a situation when we have the number of data points less than the number of parameters. Means we have only 10 data points, but we have more than 10 predictors or that independent variables. This is also huge in this case. When lambda is greater than the complexity parameter that controls the amount of shrinkage, and the greater the amount of shrinkage, the coefficients are shrunk towards 0. If you give the value of lambda towards higher, and it shrinks the coefficient towards the 0, but it is not desirable to give the lambda higher value. As a continuous shrinkage method, rigid regression provides better prediction performance through a bias variance trade-off. However, rigid regression cannot produce a parsimonious model, as it always keeps all the predictors in the model. Another penalized regression is lasso, a promising technique that is given by the Tipsirani in 1996, but nowadays when bioinformatics and biotechnological data is much more in the big data analytics, and this method is very much popular in bioinformatics data. We have many variables, but data points is very less. In that case also, that lasso is very much popular. Lasso is a shrinkage method. It will select the variables and estimate the parameters in a regression setup simultaneously. Here, lasso is the where I mentioned that this is L2 norm. Lasso is the L1 norm. It minimizes the residual sum of square subject to the sum of absolute value to the sum less than a constant. Here, this is the penalty on the original multiple linear regression. This is known as L1 norm. And lambda is defined as earlier complexity parameter or that tuning parameter, shrinkage coefficient. There are many synonyms what are used for this lambda. In regression, this is the sum of that beta square, but here is the sum of absolute value of the coefficient should be less than some constant. Here, if you go to the estimation process, here this is the argument to minimize this subject to this summation. Sum of the absolute value of regression coefficient is some less than t, and ultimately this leads to the this condition, and ultimately we have this lambda is Lagrange multiplier with a penalty parameter related to this value of t. Owing nature of annual penalty, the lasso does not both the continuous shrinkage and automatic variable selection. Here, continuous shrinkage is coefficient of regression is shrink somewhat some lesser value to original, and if we go to the value 0 or almost 0, that variable should be removed from the model, and that parsimonious model is selected. Although the lasso has some success in many situations, it tends to select one variable from the group of the when there if we have the many correlated variables in the group of our independent variables, and lasso model select when pairwise correlation is more, only one important variables are selected from this group of variables. In such situation, it has been empirically observed that the prediction performance of lasso is dominated by the ridge regression. In order to extend the power, and another model, elastic net. And elastic net is nothing but is the combination of L2 norm and L1 norm. In elastic net, and if you go to this is the model for this minimizing the sum of a square, and this is the L2 norm. Here this is the L1 norm, and this we have simultaneously minimized this lambda, minimize the sum of a square, and condition is this lambda 1 and lambda 2 are the tuning parameter for this elastic. To estimate this, how to get this model tuning parameters, it is if you remodeling this procedure, and we can view that penalized least square method. Alpha, if you put this lambda 1 divided by lambda 1 plus lambda 2 is equal to alpha, then solving beta is equivalent to optimization problem of L1 norm. But this elastic net transform or it is converted into L1 norm modeling, and if you put the alpha is equal to lambda 1 divided by lambda 1 plus 2. There are many advantages of the elastic net that when P means number of predictors is more than number of data points, then the lasso selects at most n variables. Here n variables, if P is greater than n, only n variables, n predictors are selected by the models. But in the nature of convex optimization, this seems to limiting feature of the variable selection method and may not be desirable features for many practical problems, particularly microarray data. What I discussed in microarray bioinformatical data generated from the biotechnological field. Moreover, lasso is not well defined unless the L1 norm of the coefficient is smaller a some certain value. If there is a group variable among the pairwise correlation are very high, then let's select one variables or a few of them from the group of shrinkage raised to 0 and doesn't care which one is selected. Again, this may not be desirable feature in the case of lasso. When n number of data points is greater than p, if there are high p correlation between predictor, it has been empirically observed that lasso is dominated by the ridge regression in terms of prediction, and elastic is better performing in all this lasso and ridge regression when number of n is less than p. And there is many methods to estimate the parameters in this penalized regression methods, and due to some convex optimization and the other process, we can estimate the standard error of this. But it is difficult to get the closed form of standard error form of formula for this penalized regression, and bootstrap method of estimating the standard error of the coefficient are generally used for this penalized regression. And in the case of a number of degree of freedom, how much degree of freedom, how many degree of freedom for the model would be there. There are many way we have effective degree of freedom. In the case of ridge regression, is a trace of x prime x matrix of that H matrix, trace of H matrix, which is H matrix is the x prime x plus lambda I, which I already discussed in the model in the ridge regression. And also we have, if there is non-zero coefficient of this model, that is the number of effective degree of freedom for the model. Elasticness also, that is number of independent or number of non-zero regression value of the parameter. If you go the I took the one example from the how to get the analysis from this penalized regression. I have analyzed the one of the set of data, animal science data, and this have the 150 odd crossbred cattle from the history pedigree sheet, and this is data from the Lala Lajpat Rai University of Veterinary Science and Veterinary and Animal Science, which is formerly known as HAU Hisar, and data was analyzed using the different methods. And if you go the first, we have analyzed this multiple linear regression method, and this is a predictor variable. This predictor variable is lactation milk yield 1, lactation milk yield 2, age at first calving, lactation length 1, lactation length 2, calving interval 1, calving interval 2, service period 1. These are the independent variable in the case of this data. These are independent variable, and we give the lifetime first lactation milk yield. This is the lifetime milk yield was the the dependent variable. And we have the coefficient of multiple luminescence here, and this is the ordinal analyzed by the general SPSS software, and we have this standard error and coefficient of this variable. If you go to the same data analysis by ridge regression, we have, if you go to the same data analysis, we compare here the bootstrap standard error and coefficient was like this, and it is somewhere, if you look the some data point here, that coefficient is 498. If you go to the ridge regression, its coefficient is 4710, and bootstrap standard error is this much. And bootstrap standard error for the different coefficient we have calculated with this tuning parameter lambda is equal to 2.46, computed by generalized cross validation method for the ridge regression. Same data was analyzed using the lasso. Here we have given the much more importance to the variable selection and parsimonious method. Here we looked at the AFC, age at first calving become 0 when lambda was given the value of 0.0047, and remaining there 4 variable are out of the model by using the lasso method. And we have now again we can analyze the data if we want to. Again, important variable are only this LM1, these are, and remaining are removed out from the model and extended like this using the bootstrap. Same data was analyzed using the here elastic net method, where I already have mentioned that there are 2 parameters in elastic net. Tuning point alpha is equal to 0.10 and lambda is equal to 0.1, and we have this parsimonious model, and in this model these 6 variables are selected by the model, and remaining 5 variables were rejected by the model. Using the bootstrap extended error, we have the coefficient like this. And this is the how we can use the this penalized regression. And I use the 3 methods, and using the how models are performing, we compare these are the performance measure by using this statistics. However, data is not sensitive for this data. However, we try to compare the model. If you go to the comparing method here, as you already mentioned, data is not much sensitive like this, and we have this almost same, but if we data having the sensitive data, we can have better this comparison statistics like this. If you go to this elastic net model, in all these 5 criteria, it is shown that the elastic net method was based on for the prediction of this our data set. So these are the references I have used, and we have also some our data. We have published some articles on this. Thank you, sir. Hello.
Thank you very much. Thank you. Now it is time for clarifications, questions. Anybody has any question? So you can. So, anybody has any questions? So, Dr. Hemant Kumar, so
yes, sir.
Your topic was on penalized regression. Elastic net actually comes under this elastic net. See?
Pardon, sir?
Your topic was actually on penalized regression. So,
yes, sir. Yes.
And you have shown that elastic net is actually the best one, or the
yes, sir. Yes, okay. Elastic net was found better, where L1 and L2 norm both are imposed on the multiple linear regression model.
Okay. Okay. Thank you. Thank you. So, thank you very much for your nice presentation and your expertise in agricultural statistics and use of SAS, R, and the softwares. Also, certainly that is very interesting. Thank you very much. So now we shall go to the next speaker.
Thank you very much.
Thank you. So the next speaker is G. Sirisha. G. Sirisha is Senior Assistant Professor at the University College of Science, Osmania University. And she is an expert on distribution theory, relativity theory, and so on. And today she is making her presentation on study of compound lifetime distributions. So, Dr. Sirisha.
Thank you, sir.
So, try to share your slides.
Yes, sir. I'm trying to share.
Okay.
Is my presentation seen, sir?
Yes, no problem.
Thank you, sir, for introducing me, sir. First of all, I thank my supervisor who has helped me all the way. And I would like to thank the organizers of this program for giving me this opportunity. Today, I'll be speaking on a study on compound lifetime distributions, introduction in any industrial practice, the application of statistical quality control and reliability have a vital role. Statistical quality control deals with maintenance and improvement in the quality of the manufactured product, whereas reliability analysis deals with the lifetime of the manufactured product. Quality of the manufactured product is assessed by using a suitable quality characteristic. And this variation in the quality characteristic of different items manufactured by a production process is characterized by some probability law with the help of a random variable. And the duration, the lifetime of this manufactured product is characterized by a random variable which is of continuous type, and as it is time, it should be positive half of the real line. And today's my talk will emphasize on the combination of these two aspects, quality and reliability, lifetime and quality characteristic. I'll be using in this topic modified control limits as well as compound distributions. Modified control limits are used in situations where the Six Sigma spread of the process is smaller than the spread in the specification limits. All the results presented in this talk are according to this situation, wherein the process mean mu is allowed to vary over an interval mu L to mu U, where mu L and mu U are obtained according to this modified control limits when the process is capable of producing items that can meet the specifications. In other words, certain amount of shift in the parameter mu is allowed, can be allowed on either side of the target value of mu, so that still my products will be according to the specifications, upper and lower control limits, they will be between. Now, compound distribution. In applications of statistics, one generally has some a priori information regarding the variation in one or more of the parameters of the probability model under consideration. Such variation also is specified by means of a probability distribution on an appropriate support when this information about the parameters is made effective and is superimposed on the basic model, and the probability density function is derived as a marginal, then the resulting distribution can be termed as the compound distribution of the basic model. Generally, any distribution will have some parameters. If these parameters also follow some probability law, and if this probability law is superimposed on the main distribution, then we call the derived to be as compound distributions. And here, to go on with the derivation of the compound distributions, I have used several assumptions. First assumption is we have assumed the quality characteristic, measurable quality characteristic X of the product to be normally distributed with mean mu and variance sigma square, and let U and L be the upper and lower specification limits in such a way that U minus L is greater than 6 sigma, so that I can use modified control limits. And the manufacturer, because the product can be still improved, the manufacturer decides to relax certain operating characteristics of the process by fine-tuning either one or more of the three M's, that is material or manpower or machinery, to increase the manufacturer's profit. Definitely the manufacturer has to do some changes, means relaxations in the quality with respect to the quality. And lifetime T of the product is assumed to be exponential in two of my new distributions. And in the other two distributions, for deriving other two distributions, I have considered the lifetime to be as Rayleigh distribution. Then followed with these two assumptions, I have one more assumption that is connected with the modified control limits. when the shift in mu resulting out of fine-tuning follows uniform distribution. For two distributions, I have assumed the shift to be as uniform distribution. For two distributions, I have assumed it to be as triangular distribution. Uniform in mu L, mu 2, mu U is U minus 3 sigma and mu L is L plus 3 sigma. It can be observed that the greater the shift in mu, which results in a greater deviation from the process mean mu naught, will cause a reduction in the lifetime of the product. When the lifetime of the product is reduced, even the expected lifetime will get reduced. And so I have considered the relation between the expected lifetime and the variation in the target value. Theta is equal to C plus mu, which is V, where U is absolute deviation from mu. And we know that probability of mu lying between mu L and mu naught is same as probability of mu lying between mu naught and mu U, and is equal to half because it is uniform distribution, and the probability density function of U is derived by using uniform distribution, which turned out to be G star of U is delta inverse, U lying between 0 to delta, and mu naught is mu U plus mu L by 2, delta is mu U minus mu L by 2. With this density for U, I have gone for, we have obtained the density for V. Density of V is C plus mu, would be M delta inverse, where V lies between C and C plus M delta. Now the other part, other two distributions, I have used the shift in mu according to triangular distribution, and the relation here I have used is root 2 by pi into 1 by sigma is C plus mu, which is V. This is in relation to Rayleigh distribution, mean of Rayleigh distribution, and in that case my G star of U turned out to be 2 into delta minus U into delta power minus 2, U lying between 0 to delta, and mu naught is remaining the same, mu U plus mu L by 2, delta is also the same, mu U minus mu L by 2. The probability density function of V by using this U density is 2 into M delta plus C minus V into M delta power minus 2, where V lies between C and C plus M delta. First distribution which I am going to discuss is compound exponential lifetime distribution 1. Here this can also be called as compound exponential uniform lifetime distribution. I am calling lifetime because I am connecting the quality characteristic to the lifetime aspect of a product. And here I have used my lifetime to be as exponential, of my product to be as exponential. Then the shift in mu, manufacturer has used some relaxation towards the quality characteristic. Then this shift in mu has resulted in a uniform deviation in mu values. Then the new distribution, new lifetime distribution of this new manufactured product according to this relaxation would be exponential, compound exponential uniform lifetime distribution. And here to derive, I have used the assumptions 1, 2a and 3a, which I have shown on the slide. The characteristic features of this compound exponential uniform lifetime distribution are the density of T is derived to be as f star of T. I'm calling a star for the new distribution. F star of T is M delta inverse integral over C into C plus M delta V power minus 2 E power minus Vt by gamma 2 dV. T lying between 0 to infinity. And if I expand the integration, it would be 1 by M delta into C plus M delta E power minus of C plus M delta T by minus T plus C E power minus Ct by T minus E power minus of C plus M delta T by T square plus E power minus Ct by T square. The same probability density function can also be expressed in terms of gamma integrals as F star of T is equal to M delta inverse gamma of 2 comma C minus gamma of 2 comma C plus M delta T lying between 0 to infinity and 0 otherwise. Now the characteristic features of this new distribution are the expected lifetime. The mean lifetime of this distribution would be M delta inverse log of 1 plus M delta C inverse. And here if we see according to our consideration, as we have assumed the expected lifetime of this new distribution, is always less than that of the exponential distribution. This I have checked. Then we have checked, then the variance of this distribution is turned out to be 2 by c into c plus m delta minus of m delta inverse log of 1 plus m delta by c whole square. The distribution function f star of t is given to be as, derived to be as m delta inverse e power minus ct by t e power minus m delta t minus 1 whole plus 1 t line between 0 to infinity and 0 elsewhere. These are the general properties of the distribution. Now the reliability aspects of this new distribution are, the reliability function is m delta inverse e power minus ct by t 1 minus e power minus m delta by t m delta t. Then the hazard function or the failure rate of this distribution is given by h star of t is c plus 1 by t minus of m delta e power minus m delta t by 1 minus of e power minus m delta t. The cumulative hazard rate, cumulative failure rate function capital H star t is given to be as Ct, derived to be as Ct plus log t minus of log of 1 minus e power minus m delta t. Now, this is the example which I have considered to compare the original exponential distribution with this compound exponential lifetime distribution. This is the example which is based on the piston rings, manufacturing of the piston rings for an automotive engine by using a certain forging process. This example is drawn from Montgomery book 1991, page number 206. And the inside diameter of the rings manufactured by the process is my quality characteristic x, which is assumed to be normally distributed with mean mu and variance sigma square. The upper and lower specification limits u and l are given to be as 75 mm and 73 mm. With these two values and by using modified control limits, I could obtain mu naught to be as 74.001 and sigma is 0.00989. Mu u is 74.97033. Mu l is 73.02967. Then my delta is turned out to be my delta is turned out to be 0.97033. Now, this is the table of all my values. I have considered different C and M values. And with this C and M values, I have obtained density function, distribution function values, reliability function values, hazard rate function values of the new distribution as well as the old exponential conventional model also. I have obtained the values. The same have been projected in these graphs. The first graph is based on density function, comparison of the new with exponential, likewise the distribution function, reliability function and hazard function. You can see all the values are almost your exponential and compound exponential are almost the same. And hazard rate, we can see that as exponential in the beginning for the beginning values of t, as exponential, even this new distribution also has constant failure rate. Then later on, as t is increasing, the value is increasing, hazard rate is increasing. Implies as t increases, your new model has increasing failure rate. Then the second distribution is compound exponential lifetime distribution 2. Here I have used the assumptions 1, 2a and 3b. 2a means I have assumed a lifetime as exponential and the deviation relaxation in the quality characteristic is assumed to be triangular distribution, and so we have called it as compound exponential triangular lifetime distribution. The characteristic features of compound exponential triangular lifetime distribution are density function is obtained to be f star of t is in this form. When I have expanded the integral, I have got 2 into m delta power minus 2 c m delta e power minus ct by t plus c plus m delta e power minus of c plus m delta t by t square minus of c e power minus ct by t square plus m delta c e power minus ct by t square plus 2 e power minus of c plus m delta t by t cube minus 2 e power minus ct by t cube. The same thing in terms of incomplete gamma can be given to be as 2 into m delta power minus 2 c plus m delta gamma of 2 comma c minus gamma of 2 comma c plus m delta minus of gamma of 3 comma c minus gamma of 3 comma c plus m delta. For this new distribution, the expected lifetime is derived to be as 2 into m delta power minus 2 c plus m delta log of 1 plus m delta c inverse minus m delta. And here again, the expected lifetime according to our understanding, the expected lifetime of this new distribution is always less than the exponential distribution. Variance is derived to be as 4 into m delta c inverse minus 4 m delta power minus 2 log of 1 plus m delta c inverse minus 4 into m delta power minus 2 into c plus m delta log of 1 plus m delta c inverse minus m delta power minus 2. The distribution function f star of t is obtained to be as 1 plus 2 into m delta power minus 2 e power minus ct t power minus 2 1 minus e power m delta t minus m delta e power minus ct t power minus 1. The reliability function r star of t is given to be is derived to be as 2 into m delta power minus 2 m delta e power minus ct t inverse minus e power minus ct t power minus 2 into 1 minus e power minus m delta t. These functions have been derived by using the standard definitions. The hazard function of the distribution is given to be as h star of t, derived to be as h star of t is c plus 1 by t plus t m delta plus 1 minus e power m delta t into e power minus m delta t by t into t m delta t minus 1 plus e power minus m delta t. Cumulative hazard rate is obtained to be as h star t is the integral over this small h star of t. Integral 0 to t small h star t dx. Now these are the values for the new distribution compared with exponential for different c and m. My graphs look like this for this new distribution in comparison with the exponential. Here also I can say all the values exponential and the new distribution have almost the same trend we can see in all the functions. In hazard rate function, if you've seen, the hazard rate is looking like decreasing up to some point of time. Thereafter, it is maintained a constant like exponential. So up till some point of time, the new distribution is showing a decreasing failure rate trend. Later on, it is maintained as constant. The other distribution which I have derived is compound Rayleigh lifetime distribution 1 or compound Rayleigh uniform lifetime distribution. Here I am using the first assumption, that is my quality characteristic is normally distributed and I can use modified control limits according to the specification limits. Then the other assumption which I have used is the lifetime model for the general product is Rayleigh distribution. The other assumption is the relaxation in the quality characteristic is according to uniform distribution. The density function of the new manufactured product on using the relaxation is f star of t is m delta inverse integral c to c plus m delta pi t b square 2 inverse e power minus of t square v square pi 4 power minus 1 dv, t lying between 0 to infinity and 0 otherwise. The same density can also be projected in terms of incomplete gamma distribution as 2 into m delta inverse t power minus 2 pi power minus half gamma 3 by 2 omega 1 minus gamma 3 by 2 omega 2 t lying between 0 to infinity and 0 otherwise, where omega 1 is t square c square pi 4 inverse and omega 2 is t square c plus m delta power 2 pi 4 power minus 1. The expected lifetime of this new distribution turned out to be m delta inverse log of 1 plus m delta c inverse. This expected lifetime is the same as the first model, compound exponential lifetime distribution, and this distribution have the same mean. And hence even the expected lifetime of the new distribution is strictly less than that of the Rayleigh distribution. Variance of t, V star of t is 4 into pi c c plus m delta inverse minus of m delta power minus 2 log of 1 plus m delta c inverse whole square. The distribution function is derived to be as 1 minus m delta t inverse pi power minus half gamma half omega 1 minus gamma of half omega 2. The reliability function turned out to be m delta t power minus 1 pi power minus half gamma omega 1 minus gamma of half gamma omega 2. Hazard function, hazard rate, small h star t is t power minus 1 plus 2 t power minus 1 into omega 2 power half e power minus omega 2 minus omega 1 power half e power minus omega 1 gamma of half gamma omega 1 minus gamma of half gamma omega 2 whole inverse. Here gamma 1 and gamma 2 are according to omega 1. Omega 1 is given to be as t square c square pi 4 inverse, and omega 2 is t square c plus m delta square pi 4 power minus 1. Omega 1 and omega 2 are the same. Then the cumulative hazard function capital H star can be obtained by integrating in the range 0 to t the small h star of t. And these are the tables which I have obtained, table values for the new distribution in comparison with the Rayleigh distribution for different C and M values. These are the curves which I have obtained. We have obtained. You can just see here again the values are new distribution and Rayleigh values are, curves are almost similar. Hazard rate also is depicting the same pattern as our Rayleigh distribution. This new distribution has increasing failure rate distribution. The last distribution which I am going to discuss is compound Rayleigh lifetime distribution 2 or compound Rayleigh triangular lifetime distribution, which is derived by using the assumptions that the lifetime is Rayleigh distribution and the relaxation in the target value or process mean is according to triangular distribution. The density function of t is derived to be as 2 into m delta power minus 2 integral c to c plus m delta plus c minus v t pi v square by 2 e power minus half t square v square pi by 2 dv, t lying between 0 to infinity, v lying between c and c plus m delta. The probability density function, this f star t can also be expressed in terms of incomplete gamma as the expression which is given below, where omega 1 is t square c square pi 4 power minus 1, omega 2 is t square c plus m delta square pi 4 power minus 1. Expected lifetime of this distribution is derived to be as 2 into m delta power minus 2 c plus m delta log of 1 plus m delta c inverse minus m delta. And this new distribution expected lifetime is less than that of the conventional Rayleigh distribution. Variance is obtained to be as x into m delta power minus 2 pi inverse m delta c inverse minus log of 1 plus m delta c inverse minus 4 into m delta power minus 4 c plus m delta log of 1 plus m delta c inverse minus m delta whole square. Distribution function is turned out to be 1 minus 2 into c plus m delta power minus 2 t power minus 1 pi power minus half gamma half omega 1 minus gamma half omega 2 plus 4 times of m delta power minus 2 t power minus 2 pi power minus 1 gamma 1 comma omega 1 minus gamma of 1 comma omega 2. The reliability function R star is 2 into c plus m delta power minus 2 t inverse pi power minus half gamma half omega 1 minus gamma of half omega 2 plus 4 times of m delta power minus 2 t power minus 2 pi power minus 1 gamma of 1 comma omega 1 minus gamma of 1 comma omega 2. The hazard function of this new derived distribution is h star, which is given like this. Then cumulative hazard function on integrating in the range of 0 to t, this small h star we can obtain. Table values in comparison of the new distribution with the conventional. You can see the values. The curves are looking like this. Even in this case, The new distribution curves and the conventional distribution curves are almost similar. Even the hazard rate is similar fashion. It is increasing failure rate distribution, the new compound distribution. Conclusions: generally, any manufacturer would like to relax the conditions imposed on men, machinery, and material in the situation where there is a possibility of doing so. That is, whenever U minus L specification limits difference turns out to be greater than 6 sigma. In the process, one may ignore the effect it has on the lifetime of the product, because we have seen there is a slight difference in the values in terms of the product reliabilities, which in turn leads to loss to the customer and to the manufacturer in terms of the number of complaints on warranty period. So it's better the manufacturer, if wants to relax the conditions, he can relax, because the new distribution also has similar hazard rate function and reliability function. If he wants to relax, he can relax, but project the correct, maintain transparency, project what he has done, because there is no much difference. A proper lifetime distribution should be used, and the situation would be the compound lifetime distribution rather than the conventional one. These are the references which I have used. These are the references which I have used.
Thank you, Dr. Sirisha, for stipulating the time. So it is time for questions and discussions. Anybody has any questions, please raise. Hello? Dr. Sirisha, you have not made use of any data to...
Yes, I didn't collect any data. I took only the standard example from Montgomery.
And in many cases, your comparison was with respect to exponential only.
No, exponential and Rayleigh distribution.
Oh, okay. So anyway, you have to go with the data actually. So actual data.
Even I have worked with respect to Wiley distribution as well, sir.
Okay. So anybody has any questions? Any other persons?
Yes, really, ma'am, your presentation is very nice, and I got your through presentation. But you, in your numerical results, you did. How did you take the value of M? You are taking the value of M. How to? Is there arbitrary taken the value of M, or some techniques used?
No. I took arbitrarily the values for C and M.
Okay, ma'am. Okay, thank you.
So for comparison, there should be some indices or something. So just these graphs do not sufficient. Is not sufficient actually. So
yes. One thing also, ma'am, you're through these numerical results, you are taking the graphs.
Yes.
Graphs and numerical results are the same.
Yes.
Okay, ma'am. Okay. Thank you.
Okay. So, any more questions? If there is no question, let me thank Dr. Sirisha for her nice presentation and on her work on compound lifetime distributions. Thank you, Dr. Sirisha, for your nice presentation.
Nice presentation.
Thank you, sir.
Nice.
Thank you, sir.
Our next speaker is. So you may just stop your sharing. So now next speaker is Dr. Manoj Kumar, who is Senior Assistant Professor at Central University of Haryana. He was formerly in Central University of Rajasthan, and he is an expert in Bayesian inference. And today he will be talking on assessing the effect of predator-prey model parameters under Bayesian paradigm. Dr. Manoj Kumar, please. Manoj Kumar, your mic is off.
Is my slide is visible, sir?
Earlier it was, now not.
Okay. Is it visible, sir?
It is coming. Yeah, now it is okay.
Okay, sir. Okay. And first of all, very good afternoon to respected Professor K. Jose sir and Professor Satish sir and his team for such of these workshop for the every year. Really, I am very happy, and I am also every year joined such of the WSTA before 2 years, and I also honored and privileged to get me opportunity here to present our research. And Professor K Josh sir already know me before, I think more than 6 years. So here I am going to presenting here the assessing the effect of predator-prey model parameter under Bayesian paradigm. Actually, this is totally based on the mathematical form, and these mathematical forms is going to convert in the statistical model, that is go to the stochastic model, and then going to presenting our in the form of the Bayesian paradigm. Basically, here I take here the Lotka-Volterra model. I think Lotka-Volterra model, everyone know about the Lotka-Volterra model. And this is the two of the scientists here use. And first one is the chemist and statistician, Lotka, as well as mathematician also, Volterra, and studies the ecological problem for the predator prey population. So here I consider this problem in the form of the statistical paradigm under the Bayesian. And because in statistics there are two paradigms. First one is the classical paradigm, that is the totally based on the samples, and another one is the Bayesian paradigm, which is considered to be the parameter, also considered as a random variable. So these techniques apply here to get the ideas about the Bayes estimators are used to control the predator and prey populations. Predator and prey populations are used in the ecosystem because in ecology is a study of interaction between the organism and their surroundings, including other organisms. Organisms grow and multiply, occupy different regions, complete with other for the resources, and prey upon the other, transform into the different species and which are used. So that's why I consider this problem to apply for the Bayesian paradigm. Basically, in the here, consider three things. First one is apply for this ecosystem, how to manage or equilibrium for the prey and predator population. So in ecology is a study of the relationship between the living organism and their environment. Some ecologists are using the Bayesian inferences to study the species population and two species population of the dynamic to understand the ecosystem process. So recently, I think in the previous year, one of the paper published in the Gaussian process for the Bayesian estimation in the ordinary differential equation, which in this year of the this paper are published in Valley, and the author is Wali and Wang and David Barber. That's idea is that's idea I have to take in to study in the Bayesian framework. On that paper, they have a study about the Bayesian parameter estimation in the couple of the ordinary differential equations. So here I have to consider here to be the ordinary differential equation, and then converting this ordinary differential equation into the observational model. So ecology is not only deal with the study the relationship between the individual organism with their environment, but also we study about the population of communities, ecosystem, biosphere as a whole. And ecosystem is a functional unit of the nature where the species are interact among themselves. So here is the two dynamic of the population ecosystem may be available. A biotic community and biotic environment interact with each other and the functional together as a system called as a ecosystem or a ecosystem. This term was first established by Tansley in 1935 5, they have give the idea how to the ecosystem to be the survive together for the long terms. But here the both of the populations are very important. Here the two words are used in this model analysis. One is predator and another one is the prey population. Predator population are those population and the animals that eat the another animals to the survive for the long period of the time. And the prey population are those population which gets eaten by the another animals, and their food surroundings depend on the nature. These two things are very important in our natural life, because both of the existence are very important. How to manage these both of the issues to through the statistically techniques apply and get the idea about how these population are survive for a long time in a habitat or in a forest, even in a microorganism or in a seas also. So here the this is the main equation of the Lotka-Volterra equation 1920. Can you hear me, sir?
Yes, no problem.
Yes, okay, it's okay, sir. Okay. Here the Lotka-Volterra in 1920 published and proposed his model based on interaction of two species, prey and predator population. And this is the equation of the problem for a study about the two species, that is dx upon dt is equal to alpha x minus beta xy, where alpha x is the prey population, changes with respect to the time, and y represent the predator population where change with respect to the time. And alpha is the coefficient of auto increase for the prey, and gamma is the coefficient of auto decrease for the predator population, and where beta coefficient and delta represents the interactions between prey and the predator respectively. This is the basic model of the Lotka-Volterra model. Now the population dynamic can be changed the size with the composition of over the time, and how these populations, both of the populations like a prey and predator survive together, and these are the parameters alpha, beta, delta, and gamma to be the estimate through the statistically and verify how to survive together. So now my whole idea about that problem is to estimate Bayes estimator for the parameter of predator and prey model using non-informative prior, because in habitat or in a habitat center have some idea about these population. So as a prior considering two ideas and incorporating this prior and get through the data and getting the posterior and making the posterior and give the idea about the Bayes estimator for the parameter. Actually in the Bayes estimator is nothing but it is a Bayes action. Bayes action is an estimator or a decision, maybe say that decision that rules that minimize the posterior expected value of the loss. So here consider here I have taken the predator prey model using non-informative prior and Bayes estimator of the parameter obtained under different loss function. The loss functions are many types, may be symmetric or may be asymmetric. Symmetric loss function are those loss functions when you have to overestimate, there may be loss, and when you have to underestimate, there may be also loss. When the both losses are equally, then we can say that the symmetric loss function. And another one is the asymmetric loss function, as like a Linux loss function, general entropy loss function, that are the asymmetric loss function. But here I have to consider the three losses. Here the squared error loss function, that is the symmetric loss function, and another one is the absolute error loss function, and another one is the 0-1 loss function. Both are equally important. So that's why here consider the three losses and comparing these parameters alpha, beta, and lambda and delta based on that loss function. and the efficiency of the proposed estimators are compared in terms of the risk. Risk is nothing but it is the expected value or a average of the loss is known as a say risk. Here whole ideas for the long run study about the parameters estimators we have here through the simulation study. Now here is the model. Basically this is the Lotka-Volterra model, and applying this model to make a observational model, and this model can be derived in the simple form or maybe in another form. So here through the above Lotka-Volterra model, I defined here the logistic model, and this logistic model has been proposed by George et al. In 2004. Use this terms of the predator populations. dp upon dt, this is the this is the prey population, and p is the prey population, and n is the predator population. So here r into p into 1 minus p upon k, because this is the logistic model where r represents the per capita growth rate for the prey population, and p is the prey population, k is the carrying capacity. That means in any habitat has some capacity. Capacity means how many are lions are survive in that habitat, or how many of the rabbits are survive in that habitat. So this is that's why here taken here the logistic model behind this one. So this is the logistic prey population model, and similarly this dn upon dt and C1, C2 represents the interaction rate between the prey population and the predator population. This is these are the parameters. So here are C1, C2 and D. All these are the parameters. My interest is to estimate these unknown parameters, how much of the R per capita growth rate is available in this habitat, and how many population interaction rate between the prey and population to be estimated here. So after this model, this is the deterministic model, and through this deterministic model I am going to making the observational model. This observational model has been developed based on the paper of the Wang and David Barber. Wang and David Barber have give the idea about the Gaussian process for the Bayesian estimation in ordinary differential equation. So here I also goes to apply the observational model, and this observational model can be defined in terms of the time series observation of the prey population and the predator population. This is the observational model. xt is equal to pt plus epsilon 1t. This is the epsilon 1t is adding the noise terms, that is known as a error terms, and that's why this xt, that means prey predator population converted into the random. So this model converted into the observational model, and so this observational model has a sum of the continuous time interval, and so this model should be written as equation first and second, and this will follows a normal distribution with parameter pt and sigma x square, and y t given nt is represent the predator population, nt and sigma y square. Sigma x square coefficient and sigma y square is the used as a noise terms. This is the noise terms to be used. So this is the observational model. After getting the observational model, and now go to the Bayesian analysis. For the Bayesian analysis required, Bayesian is directly proportional to the posterior basis of the posterior. The posterior is directly proportional to the likelihood into the prior. So In Bayesian inference required priors. There are a lot of priors are available in the literatures. But here I taken the non-informative prior because I have no idea about in the habitat center how many species are survive and how many of the predator prey population are survived. So that's why I have unbiasedly taken here the non-informative priors for the all the coefficient of the rate parameter R, K, C1, C2 and D. So that's why this is the uniform prior. Uniform prior is nothing but it is the vague prior. It is also known as a vague prior, and this vague prior is considered here and to the for the further analysis. And another thing another prior for the noise terms sigma x square and sigma y square, this is taken to be the gamma. Gamma is a informative prior because I have an idea about the noise terms. So here taken as a informative prior for the gamma and for the further study. So that's why this is the mechanism to posterior density. So posterior is directly proportional to the likelihood into the prior. So here these are the parameter R, K, C1, sigma x square is directly proportional to the likelihood into the prior for R, prior for uniform prior for K, and C1 prior for 1 upon B3 minus A3, and gamma prior for the sigma x square. In the this is the proportional. Actually, here taking the proportional when you are taking equality, and these integral terms come to be the in the numerator terms. So this is the posterior distribution for these models for the prey population and for the predator populations. And now these parameters are very these posterior distribution is not come in closed form. Closed form, that means this is not getting you have a very simple in the form of the distributional form. So that's why this is the big challenging issue, how to estimate these parameters when I have no idea about the distributional form. So there are a lot of numerical techniques are used to estimate these unknown parameters. So getting the full conditional posterior density, that means it is directly proportional to the kernel functions. So that's why sigma x square is directly proportional to the above equation. R is directly proportional to 1 upon 2 sigma x square, and K is proportional to these, and C1, C2 also. And then these are the full conditional posterior distribution for the each of the parameters, and all these parameters samples are generated through the Markov chain, and Markov chain through gives sampling. And these methods are discussed a very nice way in the Gelman et al. 2003 books. And even a lot of the literatures are available for the how to generate the random samples through the posterior distributions if you have no idea about the density or a distributional form of the posterior. But your posterior is a proper form. So that's why Gibbs techniques are used here to obtain the sample to generate from the each of the conditional distributions. After taking the distributions, then go to the loss function. And already I have told that here I taken for the this is my first analysis in that dimension. So I have taken here the three basic loss function. These the first one is the squared error loss function. This is the symmetric loss function, because overestimation and underestimation both are equally important. That's why I have to take in here the squared error loss function. And this is a very simple, because a squared error loss function is restricted the class of estimators by including the randomized estimators. So that's why I have to take in here. This is the loss function, and this loss function is known as a squared error loss function, theta minus theta hat is squared. Theta hat is nothing but it is the estimate of the parameter, and this estimate of the parameters, that means this loss is minimized. This loss is minimized. When this loss is minimized, that means optimization problem, when theta hat is the expectation of theta given x. Because this is the square, this is known as a Bayes estimator under this loss function. Similarly, for the absolute error loss function, the Bayes estimator under the absolute error loss function is the posterior median. So that's why I have to take in here the posterior median as a Bayes estimator and posterior mean as a Bayes estimator for the squared error loss function. And similarly, another one loss function is a 0-1 loss function when theta hat is not is equal to the true value of the parameter theta. And here theta is belongs to the set of the parameters. Set of the parameters is like R, C1, C2 and delta, all these parameters of the coefficient for the predator-prey model. And this is the posterior mod. So here the three types of the estimators. In the squared error loss function, posterior mean; in the absolute error loss function, posterior median; and in the 0-1 loss function, posterior mod. There are three types of the estimators you are proposing here. Now comparing all these estimators for the variation of the different value of the prey and predator population and comparing their risk on these three losses. And after concluding the idea about your idea about the prey and predator behavior of the estimators. And apart from this, also here discuss about the SPD interval. SPD interval, that is the that is known as SPD, may be also in Bayesian paradigm said to be a credible interval. Credible intervals are used for the symmetric posterior distribution, but when your posterior is not symmetric, then you can say that this is the HPD. This is a HPD interval. So these HPD intervals like theta 1, theta 2 is the 100 into 1 minus alpha percent credible interval for theta if theta 1 is less than equal to pi of theta given x into d theta is equal to 1 minus, where pi theta given x is represent the posterior distribution. Okay, and theta 1 and theta 2 are the lower limit and upper limit of this interval. So this is the mechanism, and for the highest posterior density obtained through these of the intervals, and this interval is theta hat is. And then for the study point of view, I have arbitrarily taken the value for the ground of the justification about our research is going to be long run performance is really what is going on. And through the simulation study, I did verify all these results. So the ground of truth data generated using numerical computation over the interval 0 to 120. This is the time interval. And through 0 to 120 interval, and R is taken to be 1.8 and K is equal to 120. This is the carrying capacity. C1 is the interaction parameter 0.2. C2 is the also another parameter 0.1, and D is the death rate of the parameter, and sigma x sigma y square is the noise term are equally for the each of the prey and predator population. And for here x represent the prey population and y represent the predator population, and 10 to 20 30 this is the increment, and this is x is equal to 60 to y is equal to. I study here the two of the table, two types of the graph. This is the population size for the when your prey population is 50 and the predator population is trained, and taking the arbitrary these of the parameters. What will be the population size with respect to the time? After the 60 time, say 600 times, we observe that this is the trajectory plot represents the population of the prey and predator population remains constant. Okay, the similar trends are to be observed for the 50 and 20 combination as well as 50 and 30 combinations. Similarly, for the another size, I have to take in when the predators population increase 60 and the predator population 20, what will be the happen? Similar results I have to I got through these simulated results. This is the two tables simulated. This is the simulation results, and these in the first column, X represent the prey population, Y represent the predator population, and this next column is the parameter, and the next column is the posterior mean. This is the Bayes estimate under a squared error loss function, posterior median under the absolute error loss function, and under the 0-1 loss function posterior mod. This is the simple estimate. This is the simple estimate. Through this estimate, we cannot never compare. So comparison point of view, we are going to the loss function. This is the average of the loss is known as a risk. So here the three types of the risk are given here. One is the squared error loss function. S stand for the squared error loss function. S stand for the squared error absolute error loss function, and this is known as a 0-1 loss function, that is a balanced loss function. Okay, so every loss function, and then I have to compare this risk through the variation of the value of the predator population. What will be the happen in the risk of this population? And one thing also very important point to be got from this study, the estimated true value is 120. Estimates are common to be the 122 for the carrying capacity as well as every parameter for these estimators. Okay, and then HPD interval, all these estimates are belongs to that interval. So our results is also justified for this considered for the simulation results. And the next table is also a study about the 60 and 20, and the similar trend is obtained. This is the conclusion. This is a very well-known results, and our results is also justified here. When we fix the sample size of prey and increase the size of predator, then the Bayesian estimate and their respective risk increases, and the size of HPD credible interval increases. When we vary the size of prey, and then the Bayesian estimate increases, but their risk decreases. That means when your sample size increases, the MSE will also decreases, but here is also in the Bayesian framework also I have to getting this such type of the results. And finally, we can say that the number of predator increases, there is more food availability for the predators, allowing the predator population to increase as well. When the predator population grow to their threshold level, however, they kill so many prey, and the prey populations being to decline, followed by the decline in the predator population because the scarcity of food. And when the predator population is low, the prey population size being the increase due to its in the past or to low predation pressure and starting the cycle anew. Such these are the some references which are related to my work, and this is the main idea taken from the Bayesian process for Gaussian process for Bayesian estimation in ordinary differential equation. They have given the idea about how to make the observational model, and then I can proceed for such type of the study. This is thanking you, sir. Just sir, can you hear me?
Thank you.
Yes,
thank you, Dr. Manoj Kumar, for the very nice presentation. So,
okay, sir.
On a not very common topic, it is a
yes,
model.
Yes, sir.
An economic model. So you have done it very well. So I have taught this topic for statistical ecology for biostatistic students. So I know these things. And anyway, so you have done very well. So this type of work I have not seen earlier. So this is time for questions. Questions? If anybody has any questions, please. Nobody is asking questions.
Yes, sir.
So anyway, you have done, so we can make use of different types of other loss functions also. The next loss function, then entropy type, generalized entropy type loss functions discussed. This is actually very useful. So
yes, sir. Actually, right now, one of my student, Dr. Anurag, is actually such type of the work is he very eager about my PhD students. That's why I involved in such type of the work.
Usually, these statistical ideas are not much used in this area.
Actually, problem here problem is computation. Main problem computation.
Definitely. And nowadays it is possible.
But nowadays it is possible, sir.
Okay, sir. So, in the absence of any more questions, we will thank the speaker, Dr. Manoj Kumar, was also my own colleague also at Central University of Rajasthan.
I am just like your student, sir.
Okay, thank you. So, thank you very much. We will go to the next speaker. Deepthi is here? Yes. Okay. So the next speaker is Dr. T. Deepthi, who is Associate Professor at Geethanjali College of Engineering and Technology, Hyderabad. And her areas are design of experiments and big data analysis, machine learning, etc. And she had one Australian patent on big data retrieval system using machine learning techniques. And today she is actually going to talk on dimension reduction of size of RSD model when responses are missing. So dimensionality reductions of size of RSD model when responses are missing. So I request Dr. Deepthi to make her presentations.
Thank you, sir. Today I want to discuss.
Not much audible. Increase the volume.
Yes, sir. Yes, sir. Is my screen is visible, sir?
Okay. Little more louder.
Okay. Okay, sir.
Now it is okay.
Today my topic is dimensionality reduction of size of response surface design model when responses are missing. I want to introduce what is response surface design model, and in that first order response surface design model, second order response surface design model, and missing responses in those models, and then how to estimate the parameters with illustrations, and then dimensionality reduction using Bayesian approach. So coming to the introduction to the response surface methodology. So in statistics, design of experiments plays a vital role in any scientific investigation. Many of the designs were developed with increase of applications in science and technology, medicine, agriculture, social sciences, etc. Response surface methodology is an advanced design in design of experiments, and it is a collection of mathematical and statistical techniques developed by Box and Wilson in 1951 to find the optimal settings of input factors or design variables that maximize or minimize the response variable or target variable, and to quantify the relationship between the measurable response variable and a group of experimental factors. So coming to the model, how the response surface model will be. So generally, the study of functional relationship between the response and the factor combinations is represented by expected value of yu is equals to functional of xu1, xu2, so on up to xuv is said to be a response surface study. So let there be v factors, that is xi, I represents 1, 2, so on up to v factors, each at s levels for experimentation. And let D denote the design matrix of the combination of the factor levels, and let yu denote the response at the eth combination. The factor response relationship is called the response surface, and the designs used for fitting this response surface are termed as response surface design model. So in this response surface design model, we will consider a first order response surface design model, and let it be in linear, and which will be in v factors, and it can be expressed as y is equals to x beta plus epsilon. So that is, as it is a first order, we can represent it general y is equals to x beta plus epsilon as yu is equals to beta naught plus beta 1 x u1 plus beta 2 x u2 plus so on up to beta v x uv plus epsilon, where y vector represents y1, y2, so on up to yn be the vector of observations, and x represents the design matrix, that is 1 comma x u1, x u2, so on up to x uv be the uth row of x, and beta, that is beta naught, beta 1, beta 2, so on up to beta v be the vector of parameters. Epsilon, epsilon 1, epsilon 2, so on up to epsilon be the vector of random errors. And here we are assuming epsilon follows with a mean 0 and variance sigma square I. The least square means generally ordinary least square estimate of beta is given as beta hat is equals to x prime x whole inverse into x prime y. Then the estimated response at the uth design point. So here it is, this is the estimated response at a particular design point, which is defined as this one. And the variance covariance matrix of yu hat is given as, so variance of the matrix is x prime x whole inverse into sigma square. So here the moment matrix x prime x is denoted with, is defined as first row, first column, n elements, and the remaining you will be having in terms of x factors. The variance of the predicted response at the uth point is defined as variance of beta naught plus summation xi square into variance of beta I hat plus double summation xui into xuj covariance of beta I hat comma beta j hat. So here we impose the restrictions on the moment matrix towards means we can reach to the orthogonality, so that we can reduce the moment matrix. Suppose the restrictions are imposed on x prime x towards reaching to orthogonality as summation x and summation xu and xj is equals to 0. And later summation x square is equals to n lambda 2 over u is equals to 1 to n and I not equals to j, that equals to 1 to so on up to v factors. Then the variance covariance matrix x prime x can be obtained as this one. The estimated variance response at a particular design point u is variance of yu hat is equals to variance of beta naught hat plus variance of beta I hat, where variance of beta naught hat is defined as sigma square by n and variance of beta I hat is defined as sigma square by n lambda 2. So this is about the first order response surface design model. And coming to the second order response surface design model. So here the model which will be expressed in the form of u is equals to intercept plus beta I into individual terms plus summation beta double I into square terms, then summation beta ij into cross product terms plus epsilon, where xu be the design matrix which is defined as 1 comma individual factors xu1 xu2 so on up to xuv, and these are the square factors x square u1 x square u2 so on up to x square uv, and these are the cross product terms. So is the uth row of means a particular row we are defining. Let us define x represents, this is the matrix, a complete matrix. Then beta is defined as similarly we can define the beta as intercept, individual, square and cross product terms, which is the parameter vector. Then the estimated response at uth design point is defined as yu hat is equals to beta naught hat plus summation beta I into xi plus summation beta I hat into x square plus summation beta ij hat into its cross product, after estimating the response at a particular uth design point. And here the moment matrix x prime x for a second order response surface design model is defined as like this. So here you will be having individual terms, square terms and cross product terms. Then the least square estimate of a parameter beta is given by beta hat is equals to x prime x whole inverse into x prime y. Then the estimated response of yu hat is defined as this one. Similarly, variance covariance matrix of beta hat is defined as x prime x whole inverse into sigma square, just like first order response surface design model. And here the moment matrix in a short form is represented as x prime x is equals to n, and these are the related to sum of x terms over n design points. So here we describe each and every letters like I, ij, ijk, ijkl and ijkl term, or all the terms are related to sum of xui, xui, xuj, xui, uj, uk, and here xui, uj, uk, ul, and these are the xui, xui, xuj and xuj over the n design points. The evaluation of the variance of yu hat in case of second order response surface model is not in a simplified form because of its moment matrix x prime x and its inverse x prime x whole inverse. So for this reason, we are imposing restrictions towards the moment matrix towards its orthogonality. So on the moment matrix, if you impose the restrictions, that is all odd power summations are 0, that is this one. And later summation xui square is equals to n lambda 2 and x power 4 ui is equals to cn lambda 4 and summation x square and x square is equals to n lambda 4. Then the moment matrix reduced to this very smaller portion, and then its inverse becomes this one, where delta represent lambda 4 into c plus v minus 1 minus v lambda 2 square, which is always a constant that is greater than 0, where variance of beta naught hat is defined as like this: variance of beta I hat, variance of beta ij hat, and covariance of beta naught beta jj hat is defined as this one, and variance of beta I hat and covariance of beta I hat, and some other covariance terms will vanish. This becomes 0. If xui square is equals to rho square, then xui power 4 is equals to rho power 4 minus this one. Then the variance of the estimated response is defined as, this is for second order response surface design model, estimated response of variance. So which is in a simplified way, that is variance of YU hat is equals to this one. So this is about the first order and second order response surface design model towards its orthogonality. Means we are imposing restrictions on moment matrix. We are defining towards orthogonality. And now, is it necessary to estimate the parameters when responses are missing? So generally, missing values in design of experiments plays a common phenomenon in real world problems, and it has attracted a lot of attention in the recent decades. Suppose if an experimental design has missing observations, it results in insufficient sampling. So it is necessary to estimate the parameters and missing responses to carry out further analysis. Several authors made attempts on this estimation of missing values in design and analysis of experiments. Very few authors made attempt on estimating the parameters and missing responses for different designs with different approaches. So, especially this Ajanta and Bhattacharya in 2015, they made an attempt to estimate the parameters of missing values in Latin square design using Bayesian approach. So not only Latin square design, they have find the estimating the parameters of these missing values for RBD and repeated measurements also using Bayesian approach. And Srinivas and Bhattacharya, they made an attempt to estimate the parameters for missing values in first order response surface design model using EM algorithm, expected maximization algorithm. But there is no significant work is found on the estimating the missing values in first order response surface design model using Bayesian approach. So here it is the methodology that we are going to estimate the parameters when the responses are missing in a particular response surface design model. It may be a first order or it may be a second order. Let Y be the vector of responses corresponding to a design matrix X. Beta be the vector of parameters and epsilon represents the vector of random errors. Suppose if an observation is missing, then the resulting data is going to be incomplete to carry out the further analysis as per the original plan of an experiment. Hence, it is necessary to estimate the missing responses to carry out the analysis. Let us assume that at some design points, the responses are missing, then the model y is equals to x beta plus epsilon can be expressed as a partitioned matrix. That is y1 ym, which is equals to x1 xm beta plus epsilon 1 epsilon m, where y1 be the vector of known observations, ym represents missing responses, x1 be the part of design points corresponding to the known values, and xm be the missing observations, and the error is also partitioned accordingly. The least square estimate of the parameters from the known observations is beta hat is equals to x1 prime, x1 prime, x1 prime, x1 whole inverse into x1 prime y1. Means we are estimating the parameters with respect to known design points only. The joint density of observed sample y for the given parameter theta called the likelihood function of y, which is denoted by P of y given theta. Probability distribution for each parameter encapsulates the prior beliefs held about their most likely values called prior distribution. P of theta explains the information about the parameter theta called prior distribution of theta. And it is an updated measure for each of the parameter values theta based on prior and given knowledge on y called the posterior distribution of theta given y is equals to given y, that is P of theta given y. Then the estimated missing observations can be obtained by using this equation. Y m hat means ym represents the vector of missing responses, and ym hat represents the estimated values for the missing responses, which is defined as xm into beta hat. If y be the observed responses, then the likelihood function of an observed sample y with the given parameters beta and sigma square is this one. Likelihood function for the given parameters beta, sigma square with the model y is equals to x beta. That is dou L by dou beta is equals to 0, then beta hat, and dou L by dou sigma square is equals to sigma hat square. Then the distribution of the parameters with respect to beta comma sigma square is defined as like this. Then the posterior distribution of the parameter beta is which follows approximately multivariate normal with a beta hat, means estimated parameters, and its inverse moment matrix into sigma square. So here for the first order model, we are going to consider n minus v into sigma hat square as this one, y minus x beta hat whole prime into y minus x beta hat. And the posterior distribution of the parameter sigma square is defined as this one, and which follows a precision, that is inverse gamma of n minus v by 2 comma n minus v sigma hat square by 2. So in this, we made an attempt to estimate the missing responses in response surface design using Bayesian approach, and then we will go for the dimensionality reduction, because without estimating the missing responses, we are not going to reduce the dimensionality of the model. So that's why it is necessary to estimate the missing responses first. For this, we use Winbugs. It is an open source software to estimate the parameter values. So here it is the example, and orthogonal means imposing restrictions on the moment matrix, and without imposing restrictions on the moment matrix, I took as example. So here, to determine the effect of pressure, temperature, and peanut moisture, flow rate, and peanut particle size on a particular total yield of oil of peanuts with 16 design points, of which 2 responses are missing, and the corresponding design matrix with 5 factors is given below. So these are the responses, and in these responses we are having 2 values are unknown, that is missing due to some conditions, and the corresponding design points are here. So now, to reduce the dimensionality, first we need to estimate these values, then only we can able to do the further analysis. So the estimation of missing responses at the 4th and 11th design points are evaluated using Bayesian approach and is presented below, and the estimated values of parameters at the known design points are evaluated using Bayesian are presented. So this is beta naught hat, beta 1 hat, beta 2, beta 3, beta 4, and beta 5 hat. The resulting estimated missing responses for 4th and 11th design points are 83.8394 and 80.1726. So now, this is the Winbugs code used to estimate the parameter, to estimate the responses. That is here, it is the model specification. After model specification, we need to load the load the given data, and then we need to give the initial values by using general procedure, that is ordinary least square method only. So while executing this problem, we can take the 1 lakh sample of under iterations, so that we can get the parameter values exactly. Similarly, without restrictions imposing on the moment matrix, that is non-orthogonality. So here I took 3 variables with 3 responses missing. So if here y5, y8 and y11 are the 3 responses are unknown to us. So for this, I estimated the missing responses at the 5th, 8th and 11th design points using Bayesian approach. So these are the resulting estimated missing responses for those values. Now we estimated the responses, missing responses. Then we need to reduce the dimensionality. So here, dimensionality reduction. When the number of factors increases, the number of relationship between the combinations of factors are also increases. As a result, the difficulty level of the analysis of the model increases, and it will be relatively inaccurate in higher dimension. With this increase of number of factors, the size of the data set also increases, and the difficulty of the level of the model also increases. It leads to the problem of dimensionality. Hence, the size of the data or model cannot be reduced directly because it affects the model and analysis of the data sets. And it has enormous applications in various fields in industries, and it can be applied in an optimal way with respect to time and cost related to the agricultural sciences, mechanical engineering, chemical technology, pharmaceutical sciences, clinical trials, biological studies, image processing, pattern recognitions, etc. Means we can apply this dimensionality reduction in almost all the various of fields. Several researchers made attempts on the reduction of size of the model for different specific problems using some mathematical and statistical techniques, identifying and eliminating some insignificant factors or variables. So in general, high dimensional data sets or models makes many challenges as well as some opportunities bound to give rise to new theoretical developments. This can be studied in two aspects. So what are the two aspects? Means you are going to minimize the number of factors or factor combinations in the model with the minimum loss of information in the data. So now constructing the designs with minimum number of design points, keeping in view of the factors that are more active. So here we apply again Bayesian approach to reduce the dimensionality, as it is a powerful technique that can be used to estimate the uncertainties of parameters based on their posterior probabilities. Posteriors can be computed using the likelihood and prior distributions. Since marginal likelihood is simply a normalized constant which need not be explicitly calculated. And here y represents the observed sample which can be drawn from the population with parameter theta, and the joint density of this y is given as called as likelihood function, that is p of y given theta, and the probability distribution for each parameter encapsulates its prior beliefs held about their most likely values, which we are going to call as prior distribution. So it explains the information about the parameter theta called prior distribution of theta. An updated measure for each of the parameter values theta based on prior and given knowledge on y called the posterior distribution of theta given y. And this is the methodology to reduce the dimensionality for the response surface design model. So here we construct M1, M2, so on up to MM be the all possible models, each containing subsets of x1 to xv factors. For each j, means for each model, we define a family of distributions p theta j, that is a prior distribution, and this dimension of p theta j for each j need not be the same value. Then the posterior probability of all possible models can be evaluated based on their priors, likelihood and normalized constant. Then select the best model M star with the highest posterior probability from these all possible linear models. So to find the highest posterior probability for each and every model that have prior distribution having unknown normalized constant. For this we use Metropolis, Hastings and Gibbs procedure of Markov chain Monte Carlo simulating procedures. So for these simulation techniques, it is impossible to calculate manually. So hence we use the R package for finding this highest posterior probability. So this is what the example that I have taken previously with the 5 factors and 16 design points. In that 2 missing observations are there. So without means before reducing the dimensionality, first I estimated the missing responses, then we will go for the dimensionality reduction. So for this I used R package so that I construct 2 power 5, that is 32 linear possible combination models are going to be evaluated with highest posterior probability 0.354. Means among all these 32 linear combinations, I choose one model which is having highest posterior probability corresponding to 2 factors, that is x2 and x5, with the R square value is 0.912. So hence the resulting reduced Bayesian model will be resulted as y hat is equals to intercept plus beta 2 x2 beta 5 x5. Means among x1 x2 x3 x4 x5 we reduced this 5 factor model to 2 factor model with R square value 91%. Similarly, without means non-orthogonal problem, in that problem means I have taken the same example which is defined in the example 2, that it is having 3 factors and 11 design points. So in that I consider 3 missing responses. So first I estimated those missing responses, then I reduced that model. So for this I used again R package. I construct 2 cube, that is 8 possible linear combination models are evaluated with the highest probability 0.684, and this 0.684 is corresponding to only 2 variables. Means among 3 variables I have chosen only 2 variables with this probability highest probability and with R square 0.895. So even for full model also probably you are going to get the R square value is 0.895 only. Means without loss of generality I am reducing the model with 3 variables to 2 variables by using Bayesian approach with the help of R package. So this is the model. So here we have 3 variables and the reduced Bayesian model has only 2 variables, and this x2 and x1 gives the significant factors with respect to this model y. Thank you. Any queries?
Joseph?
Hello, Dr. Deepthi. Thank you. Thank you very much for your nice presentation. Your topic was also somewhat unusual, response surface methodology. So she had narrated here, described with examples the different problems associated with this under this situation when observational responses are missing. So any questions? Any questions from anybody? Anybody has any questions? Otherwise, in the absence of questions, I will thank, we shall thank the speaker, Dr. T3T, for her nice presentation, nice and informative presentation.
Thank you very much.
So thank you, Dr. Deepthi.
Thank you, Satish, sir.
Now over to Dr. Satish Kumar.
Namaste, sir.
Thank you.
Satish sir, very much thank you.
Thank you.
Thank you, Satish sir.
Thank you, sir. Thank you. On behalf of the organizing committee of this conference and Department of Statistics, University of Kerala, we would like to extend our gratitude to you, our Professor K Jayakumar, for chairing the session and concluding the session in a timely way, strictly adhere to the timing. And also, we wish to extend our thanks to speakers, Dr. Hemant Kumar, Dr. Sirisha, Dr. Manoj Kumar, and Dr. Deepthi for their excellent presentations. Thank you so much. Let us give a big clap to the speakers.
Thank you very much, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you. Thank you. Thank you. I hope everyone are satisfied with the informative talks given by these young researchers. And now let us move to the next session. There we have Professor Jayashankar is here in the group to chair the session, and Professor Ilankavan and some young researchers from Anamale is also there in the group. I hope this session is a invited come contributory session. And Professor Ilankavan was here. So
wait,
anyway,
sir, I call me, sir.
Okay.
No, I call me, sir. Stay long, sir. Right.
Yeah. Okay. Let us wait 1 or 2 minutes to Professor Ilankavan. Yeah. Anjana, you are ready?
Sir, good evening, sir.
Yes, sir.
Yeah, good evening. Good evening. In fact,
yes,
Anjana, are you ready to?
So may I introduce our chair, Professor Jayashankar?
Yeah, just a minute, 1 minute. Yes. Let us wait for Professor Ilankavan, and also now it is 3:33. This session is scheduled at 3:35.
Yes.
So yes, 1 or 2 minutes we can wait for.
Nice, sir.
Yeah.
2 minutes break, sir.
Yeah, 2 minutes break. Yeah. How is Dr. Manoj, Haryana?
It's fine, sir. And you said, sir. First of all, sir, once again, congratulate to you. Your university is getting A++.
Oh yeah, thank you, Doctor.
And really, sir, this program is, every time like your program.
Thank you so much.
And there are so many special lectures, but unfortunately, I am busy in NAC work here.
Okay. They are in your university.
Also, yes, okay. That's why. But in the previous year, I was very most of the times I involve in your.
Yeah. Okay. As a central university, I hope you have. There is a lot of scope for attaining a better. Yeah.
Yes.
Anyway, all the best for your NAC accreditation.
Okay. Thank you. Thank you, sir. Thank you, sir.
I hope now it is a time. Anjana, you please introduce the chair. And if Professor Ilankavan join chair, you can give the invited talk. First, you can start with invited talk. Otherwise, you can start with the contributory talks.
All right. So,
Anjana, please.
Yes, sir. So, hello, everyone. Now we have the technical session 37 of Wsta 2022, which is a special invited with contributory session to be chaired by Dr. T. Jayashankar. Now, Dr. Jayashankar is the assistant professor and head to the Department of Statistics at Bharati Darshan University, Tamil Nadu, India. He has over 15 years of teaching experience and has guided many postgraduate, MPhil and PhD students during his career. His areas of specialization include stochastic process, sampling theory, survival analysis, and design of experiments. He finds that guiding field data collection is the most gratifying experience in his work and is a recipient of Patent Award. We are really fortunate to have such an excellent academician chairing the session with us today. So without further ado, I invite Dr. Jayashankar to take over the session. Over to you, sir.
Welcome, Professor Jayakumar. Yeah.
First of all, thanks to Dr. Satish Kumar for giving this instant opportunity to me for this excellent.
Professor Jayakumar, you can increase the volume of that your audio. Yeah, now we can hear you. Otherwise, okay.
Now, sir? Is it
yeah, now it is okay. It is fine. It's fine. It is
okay,
fine.
Okay. First of all, thanks to Dr. Satish Kumar for giving this instant opportunity to me for this excellent continuous. Regularly, you conducted this type of program. Sir, Dr. Ilagon sir is available? He joined or not, sir? Hello, sir? Sir, not audible, sir, please.
Not much audible.
Audible, sir. It's audible.
Yeah. Sir, Dr. Ilagon joined or not, sir? Hello? Hello, sir?
Yeah. His name is not not able to locate in the list.
Okay,
Dr. Vijay Shankar? Dr. Vijay Shankar?
Yes, sir. My student Sivaranjani is first to present, sir.
Okay. Let us start with the students.
Okay, now I request you to
Sivaranjani.
Miss Sivaranjani.
Yes, sir.
Hello. Kindly deliver your talk, please. For your research work.
Okay, sir.
Okay, welcome.
Hello. Professor, hello.
Sir,
Professor Ilangon here.
Sir, Professor Ilangon, sir.
Yeah.
So
my session is
Sivaranjani, wait for
better to
sir.
Start with the image talk.
Professor, I have some urgent work. Please let me know. I have to present now.
Okay, that's better. Okay.
Sivaranjani.
Okay, Professor, I will introduce the resource person. Professor Dr. R. Ilangovan finished MSc, MPhil and PhD statistics, and also he got the MBA with PhD in business administration, and he served as more than 30 years of experience for academic side, and also under his supervision 22 PhD awardees and 44 MPhil scholars. He delivered more than 40 invited talks and presented his papers, more than 80 articles on national conference and 46 for international conferences at various universities. He chaired for more than 40 national and international conferences. Professor published more than 10 books, and he visited various countries, France, USA, London, Hong Kong, and Sri Lanka, etc. So now I request Dr. Ilangovan, please kindly deliver your invited talk, please. Hello.
Sir, Ilangovan, sir. Present.
Thank you very much for your nice words, sir. I thank Dr. Satish Kumar, Professor Department of Statistics, the organizing committee member, for giving me an opportunity to deliver my talk, sir. So thank you very much, Satish. Thank you, respected sir. I want to present my talk.
Thank you, Professor. Thank you.
Thank you. That is, this work is motivated the previous conference, that is one of the application of AFT model using Binomial counter distribution for reliability analysis.
Professor?
Yeah, I want to put the mic, sir, please.
Yeah, okay. You can place the mobile in a horizontal position. Then that will be more visible.
Okay.
Then the delegates can read. Yeah, that's fine. That's fine.
So, when I have a brief introduction, and then we have some application of this model. When modeling time to failure T of a device or component whose flight time is considered a random variable, relative measure R of T is defined as R of T probability of T greater than T. Describe the probability of the component of failing or exceeding a time T. In basic statistical inference procedure, various statistical cumulative distribution function denoted by f of t can be used to model a lifetime characteristics for a device on test. In doing so, the relationship between the reliability and cumulative distribution function for t is straightforward, and R of t equal to 1 minus f of t. Choosing a model f is assuming the behavior of observation t. The frequent size of CDF in reliability model include Weibull, log normal, gamma distribution. A description of this model given by Mann et al. 1974 and Meeker and Ecobar, for example. This paper will focus on minimum sounded distribution and its application in reliability and live testing. And this distribution will be described later in this section. The BS particle live distribution has an application in the general area of accelerated live testing, and two approaches given here yield various three-parameter generalization and extension of the two original form of the model. The first approach uses the inverse power law model to develop the AFT distribution using standard method. The second approach uses different assumption of cumulative damage arguments to yield various strength distributions that are similar in form. Estimation and asymptotic theory for the models are discussed with some application to various data sets for engineering laboratories. Now we can discuss about accelerated testing. Many high-performance sectors can have extremely large reliabilities when they are operating as intended. For example, through advances in engineering science, a measurement such as time to failure of an electronic device would be quite large. For this situation, calculating reliability is still of interest to the manufacturer and the customer, but a long period of time may be necessary to obtain sufficient data to estimate reliability. This is a major issue. In addition, performing a test over a long period could be very costly. One solution in this issue, obtaining meaningful live test data in a timely fashion need to perform the accelerated live test. The procedure involves observing performance of the component higher than the usual level operating stress to obtain failure more quickly. And we can refer to Pareto 1984 for this testing. Many different parameter acceleration models are derived, and we can same Pareto 1984. The power law model has an application of the practical failure time model. And this model will be used in this paper. It is given by h of v equal to nu into v to the power minus eta, represent the level of accelerated stress. And this, by performing this substitution, it is assumed that increased environmental stress has effect of changing the mean scale of lifetime model, but the distribution fairly remains effective. So remaining things are we can discuss about the see-through good budget paper 1984 and another paper in 1995. So what is Birnbaum-Saunder distribution? While considering the physical properties of particle failure of material subject to cycle stress or strain, Birnbaum of 1990s derived a new family of light distribution. In that derivation, they assume that the case of failure occurs progression of a dominant crack with the material imminent to critical strength. Ultimate results in the particle failure. The cumulative result in the cumulative distribution function of Birnbaum-Saunder distribution given in expression 2. A random error T following the distribution will denoted by Birnbaum-Saunder alpha beta. The parameter alpha is a shape parameter, beta is a scale parameter, also a beta median for the distribution. The cumulative distribution function, interesting qualities, and the first after of interest for the discrete burst and the first reciprocal of the moments is given by this expression 3, and PDF T given by this expression 4. And Desmond 1988 shows that the equation 2 also describes the failure time that is observed when they are account for accumulated damage. So accelerated Birnbaum-Saunder distribution. So as per the equation 2, there is a two-parameter Birnbaum-Saunder distribution is 1985, derived a practical life distribution, and the Birnbaum-Saunder 1916 present review of the distribution along with some of the basic. This is one of the paper 1969 by Birnbaum and Saunder. Lot of work then using the distribution by several authors in the recent past also. Several results which are quite interesting by using this distribution. A new researcher can use the reliability work, can go through the paper 1969, and this paper will give us the fullest properties. By these properties, possible for anyone to start the new work. This is the cumulative distribution function of that model, the expression 5, and okay, and T follows alpha, beta are the moments. E of T and E of T, the other one is given by this expression. And Owen and Batch 1999 shows a 3-parameter generalization of BS distribution. It applies a tensile sense model deriving using cumulative damage argument, and from Owen and Batch 1991 1998. Then there are some other paper also. What is accelerated failure time model with the probabilities? So suppose TH is a logarithm of the failure term H into and the cluster I, J equal to 1 to N, I equal to 1 to N. This is a censoring underband. We know this logarithm Cij. We observe Tij equal to minimum over this, and for each J and I dot is integrated function. The linear regression of accelerated failure model is given by the Tij, Xij, beta plus epsilon ij. You can refer to a paper by Lee et al. 1993. Xij are observed covariance and beta is the unknown regression coefficient beta is of primary interest. We assume that censoring time the covariant random vector are mutually independent. Random vector independent to each other, but the multivariate failure time beta that correspond are generally. The marginal independent approach, Lee et al. 1993, estimates beta by ignoring the possible correlation among the components psi a. In contrast, we propose the finality of the explicit model, possible correlation among the failure time. Especially, we assume that hazard function and random variable set A is I to 1 given by this expression. So the other approaches, we can see this paper. I will give the possible reference to that. Some derivations also derived, and since Ej, Tij for Xij, logarithm failure time, joint survival function of original time scale E per Tij is given by this expression, and we can go the real data set example. Okay, so we can generate some 100,000 independent replications for the estimated regression coefficient beta not equal to 1, marginal independence of proposed approach. This Monte Carlo mean standard deviation of 1,000 independent replication. This is the number. So then B is given, then marginal mean square standard error is a gamma, and other things are given. And the covariant gender estimate regression coefficient respect to 1.54, 1.62. Using the usual jackknife, we obtained the estimate of standard error 0.61, 0.81 from two approaches. We also applied bootstrap 500 bootstrap replication, estimated 0.53, 0.54, corresponding to 98% confidence interval also given. Difference between male and female more evident from our approach than from the original marginal independent approach. The estimate of theta equal to 5.0, and but theta may be upward bias according to the experience. Also, there is one paper by Clifton 1989. You can go through the paper. Note this previous simulation, we reached theta equal to 2,000 repetitions, and the other parameters are given by this. And theta equal to 5.0, the Kendall tau is obtained by, and the using the gamma finality model estimating theta is leads to the value tau equal to 0.2. Even though this first the estimated within cluster association may be downward bias in our approach, for this it appears association between two inflection time of the same period in B. Another, the principal aim of analysis determine the diagnosis for this data set for kidney graft. First kidney graft 350-11 patient and 31 transplant center in the UK, and examine the extent to the survival time between the centers. The patient age 18 over received organ cardiac hepatic donor. So this is the explanatory variable given, and 1 year and other data is given. Following the approach of Yamaguchi 1992, Desmond 2008, Kendall et al. 2004, and you can go to the Balakrishnan paper 2009, 2014, and 2010. The application of AFT model using Binomial distribution for reliability by comparing other distributions are shown in the following way. Values of 2 logel Pareto model is considered, and the table is also presented here. And it is evident that probability-based approach for estimating linear regression AFT model for multivariate failure time data, it is especially taken into account the possible correlation with failure rate. Our simulation study shows that improved efficiency of the marginal independent approach. In this paper, discuss the role of AFT model with random for analysis of kidney graph several times. This model flexible approach parametrical survey data variety. Very often the distribution random component will be not critical. We see the analysis of the transplant data. Model normal distributed random component may be adopted. We advertise being straightforward using SAS. We are having under the using SAP program. SAS is installed in your system. The table is so visible and not possible for you to screen wise, it is not given. Comparing other log normal, log logistic, other distribution, we are using the Birnbaum sounder distribution, the application of Balakishan paper. A new for this distribution, the AFT model is generated, and these are the reference Nielsen paper, Paget, and Paget Birnbaum sounders, and Birnbaum sounder estimation library distribution 1969, and the stochastic model for Canadian statistics Desmond, other paper. There is some other paper also. If you are really interested in going through some work relating to this distribution, you can refer to Amakochi 1982, Desmond 2018, Kendall 2014, and Balakishan paper 2009, 2014, 2017. We go through the paper in 1969 and observe all the properties, and by application of the AFT model, we introduce this distribution by generating 1000 repetition by choosing the parameter, and this Birnbaum sounder distribution give more consistent result than the other distribution, because the abstract itself it says that it is the but the normal generalization of this model, so that this distribution will be useful for new researchers to start work in BS distribution. Yes, thank you, sir. This is my work. Thank you very much, sir. Hello.
Thanks, sir.
Thank you very much.
Thank you.
Hello, sir.
Yeah, thank you, sir.
Sir, Dr. Lembold, sir, please.
Yeah, please, sir.
Sir, in this data, we applied, is it possible for any other model, sir, that is variable or log normal, etc. already?
But we apply for variable, log normal, and log other distribution. But this newly introduced distribution by BS distribution gives better, consistent, more robust result by using the procedure and the properties. This is better estimate, sir, for reliability analysis.
Oh, for reliability. Okay, sir. Okay, sir. Students.
Professor, how?
Yes.
Please.
How to fix the parameter values?
Pardon, sir? Hello?
Please.
Please.
Equal to 4.1, 4.2. Which basis?
Okay.
Theta value.
Listen, sir. This is we give some 1000 repetitions, replications, and the parameter value we can give the values as per the range of the distribution. We go through the paper with the properties of the distribution range, and for complete simulation for the repetition of 1000 replication, that particular value gives a better result compared to the log normal, gamma, and other distribution. We choose the result. There is no hard and fast rule for this. By simulation only, by repetition, repeating the replication for several times, we can get the estimate for these particular values. There is no fixing the values as per the properties of the distribution. We can fix this. Properties and range.
Sir, I am Vijay Shankar. Thank you, Professor.
Yeah. Yes, sir. Yes, sir.
Thank you, sir. Thank you, sir, for your nice presentation and valuable explanation also. Any scholars, any queries, please?
Oh, sir, scholars, my sincere advice is you can go through the paper in 1969. That paper will give you complete picture of this distribution with the properties moments. By using this, it can apply to any reliability data set. And by applying this distribution and comparing to the normal scenario data, it will give better result, more consistent, robust result. The estimates are very, you can repeat the application more than 1000 times. Repetition in the simulation, it will give the better results.
Okay,
Anyhow,
okay,
that paper, there are 2 or 3 papers appear in the most of the reputed journal. That journal, you can go through the papers, and that paper will give you a complete picture of the BS distribution.
Journal name, sir?
Sir?
Thank you, sir.
Please give that any one of the journal name, please, sir.
Anyone?
Any one of the journal, please. Journal name of the
journal. That is Canadian Journal of Statistics and Statistics and Probability Letters. Then another journal is one paper in IEEE transaction by all the papers referred by Balakrishnan is applied in IEEE transaction reliability. There are 3 years already given in my slide. These papers are published in IEEE transaction reliability, and there is much of work also done in this area.
No. Thanks a lot, sir. Thanks a lot, sir.
Thank you very much, sir.
Scholars?
Sivaranjani.
Yes, sir. Yes, sir.
Okay. Okay, Mrs. Sivaranjani?
Yes, sir.
Thank you.
Professor, thanks a lot, Professor.
Thank you.
Hello, Dr. Ilangovan. Very nice talk, Dr. Ilangovan.
Yes, sir. Yes, sir. Yes, sir.
That paper is in advances in applied probability.
Yeah, advances in applied. Good morning, Gopal, sir. Gopal,
yeah, 1969.
1969, yes, sir.
But in the talk you mentioned the 1996.
No, 1916 is the one of the paper, the initial paper. That paper.
That Binbaum's paper.
Yes, paper.
In your material, it is mentioned as 1996.
Okay, yes, professor.
Yes, sir, 1996.
Okay.
Okay, very nice.
Okay, professor. Okay.
Professor, good evening, sir. Dr. Gopal, sir.
Yeah, good evening, Dr. Jayashankar.
Thanks, sir, for attending this session also. Dr. Satish Kumar instantly invited me for the session, sir. So, thank you, sir. Now I request Ms. Sivaranjani.
Yes, sir.
Please share your screen and also present it.
Okay. Good evening to all. So my topic is about to estimate the control chart using special distribution. So I am Sivaranjani, a research scholar of Department of Statistics, Annamalai University, under the guidance of Dr. N. Vijay Shankar, Assistant Professor of Statistics, Annamalai University.
Hello.
So my abstract is, the modified board 3 distribution is a new exponential family of distribution that we have introduced in the process of control chart. The proposed model is positively skewed with a declining or unimodal form, depending on its parameter values. The modified board 3 distributions statistical features are investigated and derived to evaluate the process of control chart. We have created box-Cox control chart in mean and variance for 3 sigma level, as we assume that the data is non-normal. Finally, as an example, an application to be stimulating data set that is fit in the derived equation of 3 sigma levels of test. The control of the selected distribution is shown. So introduction is sigma rating can be used to define the maturity of the manufacturing process by expressing its yield or the percentage of the defect-free products it's produced, and how many standard deviations of a normal distribution, the proportion of this free outcomes corresponding. The researchers are frequently drawn to the flexible approaches for analyzing the lifetime data, regardless of the fact that several continuous univariate distributions have been built in the recent years. Numerous sets of data from reliability, economics, insurance, medicine, and other disciplines do not stimulate distribution. As a reason, finding solution within this field with modified, extended, and generalized distribution is justifiable. The box-Cox control chart can be used to determine whether the sigma minimum value is located. 2 more lines appear in the box-Cox plot. The upper and the lower confidence limits, the potential standard of sigma minimize the variance are found in the region between the confidence bonds. Based on creating the Pearson differential equation, construct a system of 12 types of distribution functions. The density function comes in the variety of shapes that can be used in the variety of situations. Inside the Bohr distribution network, the Bohr 3 distribution has been the most widely used approach. This is also referred as the dragon distribution, as an assignment of income and prosperity distribution. The inverse Bohr distribution is recognized in the actuarial field, while the Kappa distribution is notable in climatological profession. The number of distribution hazard function has been only growing, decreasing, or stable shapes. As a function, they cannot be used to respect lifetime data such as human mortality or equipment life cycle with bottom space shaped hazard function. For decades, statisticians have worked on numerous non-monotonic forms such as the bottom shape, the unimodal or modified unimodal shape, and other are required for certain longitude statistics. Many academics have spent years developing the numerous modified variant of the parent distributions using various strategies to generate monotonic and non-monotonic geometries. Due to the variation, the modified Bohr 3 distribution has periodic decreasing, rising, bottom, unimodal, and essentially constant hazard rate shapes. In reliability, survival, and the selection of sampling applications, the Bohr 3 distribution is being used to design well data in finance and economics. Along with failure data information, there are various modified, extended, and generalized variation of the Bohr 3 distribution in the research. Namely, the inverse Bohr 3 distribution, the modified, extend, and generalized distribution are created by applying a transformation to the base distribution or by the adding one or more parameters. Frequently, these newly generated distribution fit the better Bohr. The Bohr proposed the Bohr family of 12 distributions for fitting cumulative frequency distribution on the frequency data. The density function comes in the variety of shapes that can be used in the variety of situations. In this research, we assume that the quality variate follows the modified Bohr 3 distribution and established control limits for that data in the same way as Shewhart's control limits are developed. The online method of the such a quality can be monitored using the theory of modified Bohr 3 distribution. If a process quality characteristics is believed to be follow the modified Bohr 3 distribution. In the absence of any such population model specification, we use the normal distribution and any related constants that are available, although it is extremely difficult to verify and abbreviate sample data that follows a normal distribution. The normality assumption cannot be sustained without any goodness of tiny. In SPC, a control chart provides effective tools towards assigning the industrial process. An incentive monitoring of the production process is required to enhance the high quality of the made items. To manufacture the product according to the supplied requirements and to reduce the inspection cost. As a result, the control charts are a tool for achieving the excellent product quality. The central lines are the CL signifies the average level for the process under control. So while the two horizontal lines, well known upper control limits and the lower control remain significant in such a technique that when a process is under the control, almost all the data points fall in within these limits. The control chart can be used to investigate both variable and attribute features. The control charts keep a track of manufacturing process using data from individual items or subgroups of the things in the process. A measurable quality attributes such as length, diameters, or thickness is associated with each object. The control chart will be issue a signal identifying the process as allotted. If the control chart statistics exceed the control limitations of following such a signal in SPC approaches required that a such be conducted to identify the particular cases that are to blend process engineering that to apply their process knowledge to assist in the identification the special case. So relating existing distribution in the statistical quality control. So these are the authors and the distribution, the descriptions. So next, the design construction of modified board 3 distribution. The cumulative distribution function of a modified board 3 distributions with 3 parameters specified as. So cumulative distributions 1 plus sigma x power beta whole to the power of minus alpha divided by sigma. The probability density functions PDF specified as alpha beta x to the power of minus beta minus 1 into 1 plus sigma x minus beta whole to the power of minus alpha divided by sigma minus 1, when alpha, beta and sigma are the shape parameters of modified board 3 distribution. The restricted distribution for sigma tends to 0. The modified board distribution is generalized inverse well-built distributions. So performance measure of the modified board 3 distribution. The statistical properties include mean, variance and ordinary moments. The ortho moment of the modified board 3 distributions are obtained as. So these are the ortho moment of board 3 distribution. Sigma alpha sigma power r divided by beta minus 1 into q of p or q r. Yes ma'am.
Time is over. You directly go to your result, please.
Okay sir.
Please.
Sorry. These are the numerical illustrations. So we fitted the data. Then these are then the graph, box plot for the graph. Then my conclusion: based on the modified board 3 distribution, we create the box for control chart. The control process is sentenced using a new algorithm because to the non-normal nature of the process. The table 1 along with the figure 1, 2, 3 shows a box plot of the control chart for 3 sigma level with the appropriate parameters value. The LCL upper control limits was found to be the greater than beta is equal to 1, whereas UCL lower control limit was found to be the greater than beta is equal to 5 and 10. This demonstrates that the estimated value increased as the beta value is increased. It is possible to use 6 sigma limits also to further refining model. Thank you, sir. These are my reference. Thank you, sir.
Okay, any questions from Audience, Professor Gopal sir. Any questions from audience?
No, sir.
Okay, thank you, Sivaranjani.
Thank you, sir. Thank you, sir.
Okay, next participant, Abhirami. Abhirami is available?
Yes, sir.
Okay.
Yes, sir. Good afternoon.
Please give your... Okay, very good afternoon. Abhirami, only 10 minutes, please.
Good afternoon to all. My topic is statistical process control using new generalization of exponential Mukherjee-Islam distribution under the guidance of Dr. N. Vijay Shankar, Assistant Professor, Department of Statistics, Annamalai University. My abstract is statistical process control is often used in the area to monitor processes when the quality of interest follows a normal distribution. In practice, it is not always true that the variable of interest follows the normal distribution, but may also follow non-normal distribution. The variable of interest may follow some non-normal distribution, such as an exponential distribution or a gamma distribution or any other. The use of control chart designed for a normal distribution may not be workable in this situation and may cause an increase in the proportion of non-conforming product. In this paper, the techniques of length bias distribution have been used to exponentiate Mukherjee-Islam distribution to the applications of statistical process control to check the performance of the production process. The main objective of this paper is to introduce a control chart using new generalization of exponentiated Mukherjee-Islam distribution in order to study the production system and monitor the same. Introduction. Statistical process control is a process improvement methodology widely used by modern manufacturing and service organizations. This methodology is mainly based on the use of control chart and frequency distribution of process and quality characteristics data. Common and well-established control chart include the Shewhart control chart. W.A. Shewhart first proposed the use of control chart. The control chart are important tool for quality control. The use of control chart is to control ongoing processes by identifying and correcting problems as they occur, predicting the expected range of outcomes from a process, determining whether a process is stable, analyzing pattern of process variation from special causes, non-routine events or common causes built into the process, and determining whether the quality improvement project should aim to prevent specific problems or to make fundamental changes to the process. The use of control chart lead to produced more quality product. Timely action about the process should be taken based on the control chart. That is, no action is taken when the analysis of control chart shows that the process is in control. However, if the control chart shows that the process has gone out of control, then appropriate action should be taken to bring the process back under control. Therefore, a control chart indicates the right time or to which observation corrective action should be taken. The two control limits called the upper control limits UCL and the lower control limit LCL are used to monitor the process target mean or variance. These limits are very helpful for reducing defective products and alternatively for increasing the profits of industries. The maintenance of quality through control chart bring a good reputation for an industry in the market. Next, description of the distribution. Exponential Mukherjee-Islam distribution. The PDF of exponential Mukherjee-Islam distribution is f of x equal to alpha beta x power alpha beta minus 1 divided by theta power alpha beta. This is the limit of 0 to infinity, and alpha beta theta greater than 0. Then the CDF of x cumulative density function of exponential Mukherjee-Islam distribution is f of x equal to x divided by theta power beta and the whole power alpha. Length biased exponential Mukherjee-Islam distribution. Let x is a non-negative random variable with probability density function f of x. Let w of x be the non-negative weight function. Then the probability density function of weighted random variable xw is given by f of x equal to wx f of x divided by e of w of x. So x greater than 0. Now substitute equation 1 in above. We will get the required PDF of LBEMI distribution f1 of x equal to alpha beta plus 1 into x power alpha beta divided by theta power alpha beta plus 1, where e of x equal to alpha beta theta divided by alpha beta plus 1. And the corresponding CDF of length biased exponential Mukherjee-Islam distribution is obtained as f1 of x integral theta to x f1 of x dx f1 of x equal to x divided by theta power alpha beta plus 1. Next, performance measures of the length biased exponential.
Abhirami.
Sir?
Excuse me, Abhirami.
Yes, sir.
Show your data and result, please. Time is going on.
Okay, sir.
Please.
This is the control limits of length biased exponential Mukherjee-Islam distribution, sir. UCL, CL, LCL, and numerical example. An example regarding the construction of control limits considered in the order to illustrate the practicability of proposed model. In the parameters alpha, beta, theta being a random variable, we construct 4 tables. These tables are here. The parameter alpha, the control limits increase whenever the parameter beta increases. Also, they increase whenever theta increases, as well as for the increasing of parameter alpha with a fixed beta, the control limits increase whenever the parameter theta is fixed and the more theta is increases. Now alpha value equal 0.6, beta equal 0.7 and theta equal to 0.5. This is the chart, exponential Mukherjee-Islam distribution control chart. Then conclusion, in this article, the process control is developed. The usage of exponential Mukherjee-Islam distribution is the technique is a non-normal distribution. A novel algorithm is given for sentencing. The method is production. The manipulate limits are given for the exponential Mukherjee-Islam distribution with exponential value of the parameter alpha, beta, and theta. The control chart is drawn by a way of wondering about the parameters alpha equal to 0.6 and beta equal to 0.7, then theta equal to 5. This is the reference. Thank you, sir.
Okay, any questions from audience? Okay, thanks for Abhirami.
Thank you, sir.
Next, Subhatra or Subhatira. Or Subhatra is available?
No, sir.
Okay, J. Kamala. Kamala, please.
Yes, sir. Yes, sir.
Okay, start your presentation, please.
I am Kamala, research scholar in Annamalai University.
Kamala, share your screen, please.
Okay.
My guide name Dr. N. Vijay Shankar. My topic is application in an existing structure, though a specific grade system. Abstract. We go over some of the challenges that occur when studying probability in relation to stock number distribution at various phases, as well as
Kamala,
a numerical comparison. Sir.
Excuse me, Kamala, share your screen, please.
Sir.
Already shared. Sharing, sir.
Already shared, sir.
Okay.
No, sir.
Okay.
Not in. Okay. Fine.
Okay.
Yeah.
Comparison of the different requirement stages. The organization begins recording when the cumulative loss of manpower on many occasions exceeding a random threshold level. The Kumarasamy expanded inverse reeling distributions, inter-decision duration, and threshold distribution are intended to be formed on exponential process in the numerical dispersion support the finding of the analyzers. Next one, introduction. The practice of estimating the optimal amount of employees required completing a project job or objective on time is known as manpower planning. Number of workers, different type of talent, time period, and other parameters are all part of manpower planning. It is a never-ending process to ensure that the company has the best resources accessible when they are needed, taking into account planned project as well as the replacement of departing staff. Human resource planning is another name for it. Introduction, worker. Other refer to the staffing process, which involves focusing and planning for talent requirement, deployment, development, and attrition in response to the organization changing needs. Belts view that manpower or human resource must be used as efficiently as possible. Since it is dependent on accurate forecasting and control when dealing with labor supply issues that could have been avoided with the manpower planning. Here I submit some of existing distribution in stochastic process. Kumarasamy exponential inverse relating distribution. The Kumarasamy distribution as a probability density function for double-bounded random process in 1980, and since then several scholars have continued to explore the distribution. John Gray, Nadraj, etc. In particular, introduced the Kumarasamy generalized gamma distribution as a capable distribution for modeling both group saved hazard rate function, studied some of its properties, estimated its parameter using the maximum likelihood method and a Bayesian procedure, and demonstrated it is utilized on two real data. First one is probability density function. Here is given by. Second one is cumulative distribution function can be here this assumption of the model. The company is moved upon above a single source secured control the threshold individual random variable inter-arrival time which or IID random variable depending on requirement promotion training and wastage are used to make policy judgment. The process that lead to policy changes and the should random variables are statistically separate. First methodology is this one is cured parameter theta y follows cured with parameter theta. It's can demonstrate their probability xi less than y equal to integral 0 to infinity g of k g of x h of x noted. These are my equations. The probability that the cumulative should will fail only after time t is given by the several functions. S of t is equal to probability capital T greater than small t equal to probability that the total damage service beyond time t. These are my equations. These are my table, expected time of cure table. This is my figure. First one is initial stage of parameter mu versus inter-arrival time c. Second one is outcome at a later stage of parameter mu versus inter-arrival time c. Next, my figure is stochastic outcome at an initial stage of parameter alpha versus inter-arrival time c. Second one is later stage of parameter alpha versus inter-arrival c. Second, the fourth one is theta versus c. Then initial stage. Second stage, later stage, theta versus inter-arrival time c. Discussion. At the inter-arrival time, increasing the observed stochastic result for the parameter decreases as shown in table 2 at an early stage and later stage. Figure 2 and 3 show the initial and later stage of parameter where parameter with the inter-arrival time c, whereas figure 4 and 5 show the initial and later.
Kamala, please. Kamala.
Etc. When developed the stochastic model using the additive Wibble distribution, it has been noted that as the duration between a employee's arrival and departure goes, so does
Kamala?
the time required for requirement, sir?
Kamala, please. Show your result and conclusion, please. Yeah.
My conclusion, we have here property in this work to suggest the cure as a replacement model for an organization. The control we tended to believe that the proposed model will find ways to use the fields such as engineering, survival, and logarithm data, hierarchical, and others. These are my reference. Thank you. Thank you, sir.
Or Subhatra, please. Subhatra is available. Subhatra.
Not here, sir.
Subhatra is available.
No, sir.
No. Okay. Only 3 participants presented for this session.
Okay, sir.
Okay. The session will be handed over to coordinator. Dr. Satish Kumar, sir. Professor. 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 Madam.
Sir, Jai Shankar, sir. I am Vijay Shankar from Annamalai University.
Yeah, I know very well, ma'am. Very well, sir. How are you, sir?
Fine, sir.
All the participants are under your supervision, I think so.
Yes, sir. Yes, sir.
Okay, congratulations for your guidance.
My guide Vijay Ilangon, sir, participant. Invited.
Yeah, I know. Okay, congratulations for your scholars.
Thank you, sir.
But another one candidate, Subhatra, is under your supervision?
Yes, sir. Subhatra is a college here, a network, sir.
Okay.
Private college in Chennai, sir.
Oh, now, okay.
Yes, sir.
Oh, now, okay. Sir is available, Satish Kumar, sir? No.
No, sir.
Okay, then how to hand over the session to hosting persons?
Yes, sir. I will call, sir. Wait, sir.
Okay. வாங்க விஜய் சங்கர் ஒரு நாள் யூனிவர்சிட்டிக்கு வாங்க பாரதாசன்.
கண்டிப்பா வரேன் சார். நீங்க சிதம்பரம் வந்தா வாங்க சார்.
வரேன் சார். எங்க சார் இங்க டிபார்ட்மெண்ட்ல ஆல்டர்னேட்டிவ் பர்சன்ஸ் யாரும் இல்லையா?
ஆமா கேள்விப்பட்டோம் சார். இந்த சதீஷ் குமார் சார் ஜாயின் சார்.
ஓகே. Professor?
Hi, Professor.
Dr. Satish Kumar, sir? Professor? Yes. Yeah, in this session, Dr. Ilangovan already presented for the invited talk, and also 3 persons presented.
In fact,
but 1 person, Dr. Subhatra, is not available.
Okay.
So, Abhirami, Kamala, and Sivaranjani, 3 persons already presented.
Okay, Professor.
Their topics. Okay, thanks for giving the opportunity, sir. Okay, session is over or continue, sir?
Next session will start in this platform. In fact, we are now 3 platforms are running parallel.
Sir, please, sir.
Parallel section.
Parallel sessions. I was there in that parallel sessions. Like this.
Okay, another sessions. Okay, sir.
Yeah. Now, okay, on behalf of the
sir, I will be joined at the validity function also.
Yeah, University of Kerala, we extend our thanks to you, Professor Jai Shankar, for your support to our activities as the chair of this session. Now,
thank you, sir. Thank you for giving the opportunity.
Thank you so much. And also, we are grateful to the speakers, especially the special invited speaker, Professor Ilangovan, whether he is in the group. Okay. And he has to share another session in the other platform. Probably he may join that there. Anyway, thank you, Professor, and thank you, Vijay Shankar, and other all the speakers. Let us give a big, let us extend our gratitude to all the speakers of the session. Now, let us move to the next session, Professor.
Thank you, sir.
Vijay Shankar. Thank you so much.
Thank you, sir.
Thank you, sir. Thank you, Professor.
Thank you, Vijay Shankar. Thank you, sir. Please.
Thank you, sir.
The speakers as well as the chair of the next session are waiting. And we
okay, sir. Thank you.
Yeah, 4:35, I think so, isn't it? Yeah, 4:35. 4:40. There is some time.
4:40, sir. 4:40.
So 2-3 minutes are there. Okay. So,
thank you very much, sir. I will leave.
Thank you, Professor Jai Shankar. You can also join with us in the meantime. Other programs, several. And now the next session also an excellent session on biostatistics. Several are there in this group.
Okay, sir. Okay, sir. Please, sir. Thank you.
We hope to have a great, better sessions here in the next when Professor Yadav Professor Eliamma, Professor N.C. Matthew, and Professor Dr. Preeti, Dr. Jagannath are also there to wait. And Dr. Baiju is here to chair the session. And in fact, this is the session number 37, isn't it? 38. Aishwarya is here in the group. Just a minute, because the time is 4:40. Some people may also join into this group from the other platforms and otherwise from outside. Let us wait for 2-3 minutes. Aishwarya? Oh, yeah, okay. Aishwarya is ready. You are ready, isn't it? Okay. So after 2 minutes, you can introduce the chair and invite him to do the further proceeding. Professor Yadav, how are you? Can you see me? Professor Yadav? Probably you... Hello, Professor? Can you hear me? Professor Yadav, you have muted your mic. The power there, Dr. Baju?
Yes, sir. Now it has been restored.
Restored, okay.
Thank you.
Professor Kachashvili also in the group, I think so. Aishwarya, now you can introduce the chair so that 1 minute, no problem. Introduce.
Thank you, Aishwarya, for your nice introduction about me. So we are now in the technical session 38 of this edition of Wsta 2022. So at the beginning, I would like to express my gratitude and pleasure to Professor Satish sir for assigning me as a chair of a session of this international webinar. I have been really honored by this one. So, you know that every year Professor Satish sir is organizing such a type of mega events where high-ranked statisticians all over the planet are converging into this virtual platform. It will enhance the research aptitude of many researchers and also teachers like us to hear the world-famous statisticians around us. So for that, I would like to congratulate Sadiq sir for organizing this type of webinars every year. And also Sadiq sir with his
cannot hear anything at all.
Statistical brain. He has a very punctual, very time-bounded manner. This has been carried out. So let us move to the business. The session, technical session 38. And Professor Sadiq sir is always a distinguished professor in the sense that in every event, almost all sessions covering areas where statistics has been applied is incorporated in every lecture hours. So I think this session is devoted to the new findings, the new developments in the field of biostatistics, especially in epidemiology and clinical research. So we have this section mainly concentrated on biostatistics. And we have learned professors with us for delivering their talk. And the first talk is entitled How to Streamline Data Analysis Workflow, a Clinical Methodology Perspectives. It has been taken by Dr. I.P. Yadav, a distinguished surgeon of Department of Surgery, Government Medical College, Kollam. So Dr. Yadav is a medical practitioner as well as a statistics practitioner, especially in health science. Dr. Yadav is also associated with clinical methodology development in Trivandrum Medical College. And he is a trained epidemiology, qualitative research, and biostatistics and data analysis. And also, he is well versed with sophisticated statistical packages such as R and Python. And moreover, he is holding positions of various local bodies and state organizations. And he has been associated editor of BMC Journal, as well as he has published more than 19 publications in peer-reviewed journals. Dr. Yadav sir, I warmly welcome to deliver your talk. Now the stage is yours. Thank you.
Thank you for the warm welcome speech. Thank you for giving me this opportunity to present at this statistical conference. Let me start. Share my screen.
Okay, sir. Sir, it's given 30 minutes.
Okay. Can you see my screen? Can you see my screen?
Not yet.
But now?
No, sir.
No.
This one issue the screen sharing. Permission is not granted, I think.
That may not be the fact. That may be due to your computer settings. But just to go. Press the now button and then
okay.
Try again.
Please. Is it visible now?
Not yet.
Is it visible?
No.
Not yet. I have shared the PPT file to Sadiq sir. Can it be open from their side?
We shall try. Process.
this screen is visible now. Yes. I think. Let me try.
Searching, Professor. I'm searching your. But okay, if it is okay.
Can you see that? Can you see it now?
Yeah, now it is. Yeah, we can see your screen is visible.
Okay.
Size
okay. It's visible now. Okay.
Now it is visible.
Okay. Let me. So let us start the session. Usually, when we design a study, when we start before analyzing the study, we initially when we start the study itself, we discuss with the clinicians. Then after discussing with the clinicians, once the clinical question is very clear, then I make sure that I discuss with the statistician, one or two statistician, before I finalize the protocol itself. Then we present the protocol to the ethics committee and research committee. Once it is approved, by the time it is approved, we make sure that all data analysis steps will be already written in predefined codes. All tables and all results, dummy results will be made even before we start collecting the data. This is the way we work there. First, we discuss with the clinicians, and when they come with the clinical research question, then we discuss with the statistician. Then we make the dummy tables, dummy codes, everything. Actually, it is about the teamwork of the clinicians, clinical methodologists, and the statistician. So the most important thing is we have to be very clear about the research question in the initial phase itself. Then we need to be very clear about how the data was generated. Then we will have a data analysis plan in place well before we start the study. So in the data analysis plan, what we do for the last few years is we make each project compartmentalized. That means each project will be in a separate compartment with that will be whether it is in a Python code or whether it is in R or Stata or whatever it is. It should be separately compartmentalized in a project-wise manner. So we start with if it is in a case of R, we start with an R project. But before going to an R project, we start with the version control. We start with the version control so that every step will be audit-rated, every step will be version controlled. And we make the syntax or the codes and the interpretation in the same file using Notebook or Quarto at present. And we make sure that the naming conventions are as we said earlier. So now we discuss about the project management. Project management, we start with the version control. We go to GitHub and create a new repository, and from the repository we get the SSH code, and then we start a new project in the RStudio. Or if you use Python, we will use Visual Studio Code. Then when you start a new project in the R, we make sure that it is always version controlled and cloned from the Git repository we started earlier. I'll show you how we do that. So first, this is can you all see this screen? Hello?
Yes, sir. Yes, sir. We can continue.
Okay. I open my GitHub account, then I start a new repository. You can see at the top end there is a button called new repository. I click at the new repository. Then what I do is I start a new repository, give the name for the repository. Here is a demo name I have for this particular project for the presentation. Before, in the initial period, I think in 2015 or 14 time, there was only limited private repositories available in the GitHub. You'd have to pay money for getting private repositories in the GitHub. That time I used the Bitbucket. Now we use this repository GitHub only, and you can see that I have clicked the private option for the repository. Then I create in the lower part you can see the create repository button, and I create the repository first. Then the naming convention will be what I give for the naming convention will be like the study is about some diabetic mellitus foot ulcer. I'll name like diabetic ulcer GMCQ. That means GMCQ means Government Medical Column / design of the study also will be there. Then I write the name of the author, then / date. This is a naming convention we use here.
So now we have created a GitHub repository as a private repository. Then what we do now is we have to take the SSH code. You can see the right side, there is a code here. This code can be copied with here, that github.episurgeon.demo.git. This code will be copied. This is what we use to create a version controlled art project. Now we go to R Studio. Now we used to open the R Studio. Then what we do is we go to the upper aspect, and there is a file, and create a new project. If we click the create new project, then this particular, this will be open. You will be given three choices: new repository, or version control, or existing repository like that. We will go for the new version control option. Once you click the version control option, you will be shown this particular screen. Here we will we'll paste that SSH code we took from the GitHub. Then we copy paste here, and then we create a project, and making sure the open new session is clicked. Now this is a new session in R. So this is a self-contained docket. You can see there is a demo project on the right side. You can see on the under files, you can see there is a demo project. The name of the project is demo. That is, so whatever is our project, we will give that name as such project. So this is version control. So whatever changes you make in the whatever codes you write in the R, that will be there in the GitHub or in or version control. So it will be easy easy for later going back to the particular previous codes, or you can even have all versions of the code there in the GitHub. Now what we do is now we need to create a file. Previously what I used was in 2012-13 times I used the R scripts only. Later I changed over to R notebook, then R markdown, and later to R notebook. Now I use the Quarto document. Actually, it is that's the Quarto and the R notebook or R markdown are almost same. The Quarto is the latest version. Is very useful also. But I make sure that the initial cleaning file is always in the R script. Then it is sourced to the notebook or R markdown or Quarto. Then we start analyzing. I'll demonstrate how we do each step by step. So first file we create is a R script, and this is for the cleaning purpose. And we never touch the Excel file as such. As a CSV file we never touch. We always modify or do all data wrangling or cleaning only in R. That particular folder file will always be named clean.r. So this is a naming convention I use. So now we create an R script. Then you will get something like a something like that. We will take clean.r files. Then we import the whole Excel sheet. We never change or we never do any kind of data wrangling in the Excel sheet. We keep the Excel sheet as such. Whatever we gave the name, we keep it as such. Then we will read in the code, and then we do all data wrangling or transformation. All of the procedures will be done in this file only, this clean.r file only. We never do EDA or modeling in this file. This is entirely for cleaning purpose only. And once we clean the data and it is analyzable, then we'll save it as either .rds file, or we keep it as just another file. Then we will be sourcing this file to the next session. Next session is always, those are three sessions. First session is always cleaning purpose, cleaning file. Then second file is always exploratory data analysis. We call it .eda file. Then the last file is the data analysis file, that we call it a model file. This name convention I follow for all analysis. So now we created a cleaning file, and we know how we use all those scripts or codes in that cleaning files only. Whether it is a R projects, or it is a Python projects, or we did into Stata, we always have a clean file. If it is a Stata, I will create a clean.do files. We do everything in do files in Stata. So there will be the file will be named like clean.do files. So in R we call it clean.r files, and in Python we will be calling it as clean.py or ipd py. So this is a naming convention we follow. It is software agnostic. Whatever software analytical tool we use the same steps. So cleaning files is, so now we have the cleaned data from the Excel in analyzable form. Now we go start another file. That is previously I used to use only R notebook or R markdown. Now I change over to a quarter file. I will demonstrate how I do it in R notebook. We start a new files and click the R notebook. Then you will get something. You will get something like an R notebook. Like the use of the R notebook is you can combine all those codes, analyses, tables, figures, and everything together in a single file. You can even start writing. We even write the result sections and the discussion section, everything here in the R notebook or Koto. And we even put the reference software, this Sotoro, everything is linked to this Koto files. So it is easy. You'll have only one file for data analysis, and you'll have only just beneath the data analysis code block. You can write your interpretation. You can write the results. Everything. It is like a notebook. Actually, the Jupyter also can be used in the same way. But I don't use the Jupyter or Colab at present. What I use at present is a VS Code, Visual Studio VS Code. Now, this is a EDA file I created in the R notebook. Then I make sure the output will be in multiple format, in a PDF or Word format, and the sections and there will be section headings. We can write a CSS heading for the title and everything. Then we read the cleaned RDS. There are two methods I use for getting the clean file. Previously, I used only RDS files. I just pick in the RDS file from the clean file. This is how we never use the Excel here. We always use the clean file from the first compartment. First compartment, the cleaning file for compartment, clean.r. From that compartment, we source the file to the next session. Next session is EDA. We make sure that before we go into the modeling procedure, always we go for an exploratory data analysis before looking at the research questions we have written some time back. So one of the ways you can use this R notebook is, you see, we can even import the questions. My clinician friend has sent me the research question there. So we can just bring in the figure here and we can see the research question there, and we can just plan our analysis and all. Then at present, instead of this R notebook or R markdown files for the EDA purpose, I use the Koto documents. They are in the R Studio. You can have when you click the R file, there is a Koto document option. You can click that Koto document. Then you'll be seeing something like an R markdown shot. Then you just create what do you call that, Koto file. So a Koto file will be almost like an R markdown or R notebook files, and you will see something like this. Here also we can write the research question. Here I write the research question in the model file actually. The model files only I write the research question. Research question may be 1, 2, 3 or like that. So I write the research question. Initially what the clinician told me, the note and or the WhatsApp message, I copy paste under the research question. Then I write it under Pico format like. Quick, I'll demonstrate that. One of the uses of the Koto is you can render that files. There is an upper side, you can see on render option. Once you click the render option, this is a HTML for output I selected. I can select a doc output or I can select the PDF output. The moment I write the render function, you can see everything or the code and everything. You get an output just like on the right side itself. So it is very easy to see your codes and the results side by side, etc. Then this is the same thing with the doc format as doc instead of the HTML. So one of the another uses of this Koto file more than our R markdown notebook is if you use the slash buttons, you can see all those options coming up. You can put in their R code chunks or Python code chunks, or you can get the multiple blocks, bullet list. So you can bring in pictures, you can put in tables, etc. like that. This is how once we have the results and all, what we do. This is a model file I created. A model file means it's a third file. So we have 3 files. One is a clean files in pure R test, R document, .r, clean.r. Then we have an RMD or Koto files in the form of EDA. So second file is EDA file, first file is a cleaning file, second file is the EDA file, third file is the actual data analysis file, or we call it model file. In the model file, we write we source the file from the cleaning file. Then we write our codes. then we write our interpretation is just below the quotes. The results we can see on the right side when you render. Just I showed you in the previous slide. You can see all results on the right side. Then you can write your analysis or the interpretation on the left side, just below the quote block. So even we plan the results in the same quote or documents. Like in a result section, usually I give my either my statistician friends give the results, or if he's very busy, I do analysis and give the result to my clinician friend. Then the results as such is given. So we outline the results like paragraph 1, paragraph 2, and how many figures are needed, etc. Actually, this is all planned at the time of protocol itself. So we know what are the figures we expect. We know what are the tables we need. So depending upon what type of tables and what type of figures we need, we create codes for that tables and what you call the figures before we start the data collection itself. Then the moment you have the data collection, every code is ready. It is just click of a buttons. But there you have to do a lot of iterative process, because the actual data may be different from the codes. The codes may not work. So there may be some time you have to spend. What I found was most of the time, more than 80 to 90% of the time is spent on data cleaning only. Only 5 to 10% of the time is only needed for the EDA or exploratory data analysis or modeling as such. Once you have all those once you have all those results ready, then we start the discussion itself in the right. You can start writing the discussion itself in the quota files, and you can even cite. There is a citation option. You can see in the upper part there is a citation option. The second file you can see I wrote something. Then click the citation option. Once you click the citation option, you can go in for, if you to go for PDF and BibTeX, you can go for that option, or you can use your Zotero library. Then it will your all codes will come. I mean, citation codes will come up, and you can insert all those citations. What I discussed just now is actually how we streamline our data analysis. It's actually always from a collaborative work. The idea starts with the clinician, then they discuss with the clinical methodologists like me. Then I discuss the whole scenario with my statistician friends, because they decide everything. They give me a lot of ideas, because we are not mathematical people, or we are not statistician people. We know only a bit of statistician. We can never replace the statistician. So we always make it a habit to discuss everything with our statistician friends, and with the input we finalize the protocol. Once we finalize the protocol, then we discuss with the clinician and decide on the tables needed for the publication and for the figures needed for the publication. And even the tables, the table 1, table 2, table 3, everything is hard coded. We don't copy paste the results into Word. We just we have our own function where you have T1 function will give you the table 1, T2 function will give you. So everything is pre-planned, and all tables are even hard coded. Then once we start the analysis, first we bring in the whole Excel to the project as such. As it's a project-based approach, you don't have to use the file.choose, or you don't have to set the repository like that. It is because it is project-based. You just click the R, or just read in the Excel files or CSV file. It will be there. You don't have to worry about thinking about the file choose source or how to bring in those things and all. There is no confusion. It is project-oriented. Then, as I told you, what I do first is I clean the file. I never make any changes in the Excel file. It is kept aside as such. I just bring in the Excel file to my cleaning file. Then I do all kind of cleaning there itself. Sometimes I may use regex functions, sometimes transformations, sometimes cleaning, sometimes all those things will be done in the cleaning files only. From the cleaning files, I source that cleaned file to either in the form of RDS file or in the .r file to the EDA file. Then I do all kind of EDA exploratory analysis without thinking of the result question. Once I have an idea about the whole Excel whole data in the form of various pitches, I visualize all pitches in the EDA as a part of the EDA, various kind of bivariate things and all, and even multi-dimensional visualization will be explored under the EDA. Once I have some idea about the whole Excel sheet, our whole data, then I look at the I open the model file and copy paste the research question. Then start thinking only through the eyes of the research question and the hypothesis. There we will use the various codes to get the result we already planned. Already planned means how we are going to present that this is the result. This is the way we are going to present. So that way we will write the codes. Then it doesn't matter whether you use the R, whether it doesn't matter whether you use Python, it doesn't matter whether you use data, because everything is the same approach, the systematic approach we apply in R, whether it is R, Python or Stata. When I analyze in Stata, what I do is I never write random codes. I always make sure that I open a do file. Then first the whole cleaning process will be hard-coded only in the clean.do files. Then that clean.do files will be separately kept, and this will be sourced in the eda.do files. Then then I will start the once I complete the EDA file, EDA means exploratory data analysis. Then I create a model.do files. Then in the model.do files, I source the files from the clean.do files and do the analysis. The same procedure, same mechanism, the same name convention. It is replicated whether I do it in Stata or not. SPSS, what I advise my friends who use the SPSS is because as it is a point and click approach, I always tell them you always keep those syntaxes ready, because this is in reproducible research, or in there is another way of reproducible research is literate programming. It is very important to keep the syntaxes. The easiest way they can find their SPSS syntax is open the status folder. In the SPSS, there is a .journal file. That journal file contains all SPSS code. They can keep aside that SPSS code in an email attachment or somewhere separate. So if the publisher or somebody asks you how you analyze that, there is an audit trail. You can just go back and see what are the procedures you have done, whether you have used the point and click or syntax wise in SPSS. And Stata also, if people are not using, one of my friends is not using do files, he just write some codes or some point and click. So I always may ask them to keep a log, keep the log file intact and attach to a Google Drive or mail, so that that whole data analysis trail will be there. I used sometimes back Jupyter and Colab for the Python. Nowadays I use only VS Code, or if I am working on R, then I use in a package called Reticulate, so I can bring in all Python code to R session. Then I can analyze also. Sometimes some Seaborn and Seaborn library is very beautiful. I like Seaborn better than ggplot. So sometimes I use Reticulate to call in my Python function and open Seaborn and do the visualizations. Then so it doesn't matter which type of software you use, whether it is R, Stata, or SPSS, or Python. It doesn't matter. The same name convention, same version controlling methods, the same type of data analysis pipelines. Pipeline means the first pipeline is the cleaning pipeline, next pipeline is the EDA pipeline, then is the model pipeline. So the same thing can be replicated in every software. This is what we do in R. I mean in Stata. There is a Stata do file editor. We open that Stata and create 3 types of files. Then if it is I just had to mention I use the I like Visual Studio Code. So there also we create the EDA, the same name convention we use. Then previously in 2019-20 times I used this RNV. That means sometimes when there is R packages changes and there is updation, there may be a dependency problem. My codes may not work. Retrospectively, my codes, the previous codes may not work when we update the R and all. So that time we used the one particular package called RENV package, because so that is self-contained. So if it is self-contained, then you can install the various versions there. So everything will be intact in that particular folder, so you don't have to worry about the updates and all. That was something I used some time back. Then I also tried with the Dockerization also, but nowadays I don't use the Dockers or RNV or even Python. I don't create I don't worry much about setting the environment and all, because the easiest way is always create your own package. Once you have create your own package, the easiest way, once you create our own package for all data analysis steps and codes, the thing is you don't need to worry about all those updating and all. So that is what we do at present for the last 3-4 years. This is the way we do our research, do our data analysis. But it is always many times we hit a wall. So like what to do nesting. Then we discuss with our statistician friends. If they have the time to analyze, I make sure I don't do my analysis for my friends. I ask my statistician friends to do my analysis because they know the subject well rather than me. I am just a clinical methodologist and a clinician with some basic statistical knowledge and more software knowledge. So thank you for giving me this opportunity. Can you all hear me?
Yes. Yes.
May I stop my screen?
Yes, sir. So thank you, Dr. Yadav, for presenting such a wonderful talk before the audience. And you have made 100% justice in accordance with the title, that is the methodological part of the clinical research. And now it is the question timing. The audience, if you have any queries or suggestions, please ask it to Dr. Yadav. I think no questions are there. So once again, thank you, Dr. Yadav, for your presentation on behalf of Wsta 2022. Sir, you're muted. Okay. So now we are in. Sir, Yadav, sir, are you speaking? No. Your microphone is muted.
Okay. I thought.
Okay.
I'm not speaking. Okay.
Okay.
I was
Thanks,
waiting
sir.
whether there's any questions and all.
Okay. I think no more questions are there. Okay. Thank you. Okay. Now we are the technical section number 38. The next presentation from Professor Eliama Matthew. Yes. Are you there?
Can I? Am I audible?
Yes.
Can I request you to allow Preeti Sarajan?
Yes. Why not? Okay, ma'am. No problem. Shall I, with your permission, invite Professor Preeti George?
Yes.
Okay, thank you.
Yes, sir. I am ready, sir.
Okay, you are ready. Okay,
I am ready.
Okay. So the next presentation from Professor Preeti Sara George, and Professor Preeti is currently working as an additional professor in biostatistics in the prestigious Regional Cancer Center, Trivandrum. So, all of you aware about the contributions from Preeti. Every year, Professor Preeti is presenting paper in the international webinars, particularly conducted by Department of Statistics. And I have to give a brief bio of Professor Preeti. So, Professor Preeti has more than 60 indexed publications together with several monographs and chapters in books. And she has completed many research projects where he has served as a principal investigator and he has been guiding many students for their doctoral degree. She has achieved various national as well as international fellowships, and I request Professor Preeti to deliver your talk.
Thank you, Baji sir. Thank you very much for the warm welcome.
Okay, thank you.
Also, Satish sir, thank you very much for this inviting me to speak in this occasion, and it is a great honor for me. Indeed, my topic is entirely different than what we already presented here. But may I share my screen here?
So it is visible now.
It is visible?
Visible, but you have to put in the full screen mode. Then it will be much more better. It is not now visible. If you use the shortcut key Ctrl+L, then it goes to the full screen mode. Ctrl+L.
Not working. Is it visible? I couldn't.
Yes, it is okay. Okay, Professor. You can continue.
Actually, here it is not visible.
Oh.
Is it visible here?
Not yet. It is not visible.
Not visible.
Or you can present without the full screen mode.
Okay.
No problem in it. We can see through. The first time it has came. Okay. Okay, Professor, you can continue. Oh, it is not. So when you put in the full screen mode,
I cannot see the file. That is the reason. Now it is visible?
No, it is not visible.
Not visible, yeah.
So I think you need not put in the full screen mode. You just show the file. Sadesh sir, are you there? Yeah, now it is okay. Now it is okay.
But it is.
Yes, it is okay. You can present.
Yeah.
Okay, thank you.
My topic is application of geospatial temporal analysis and scanning statistics for identifying thyroid cancer clustering pattern in Truncated. The spatial analysis mainly focused on clustering and cluster detection analysis. Several spatial tools such as Geographic Information System, GIS, and remote sensing, RS, and novel spatial statistical analysis such as machine learning algorithm played an important role. With the development of geospatial information technologies in recent years, these and related technologies have been fully applied to discover the early spatial distribution of disease and early screening studies in potential disease areas. These and spatial exploration technologies have played an important role in fields such as influenza, hand, foot, and mouth disease, AIDS, cancers, and other diseases, helping to detect the spatial distribution pattern and potential pathogenic factors. Onset factors of cancers are complicated. In addition to genetic and variability factors, the geographical environment is also an important factor that can affect the incidence of cancers. A spatial analysis of cancer cases can provide theoretical and hypothesis research direction for the role of related environmental factors in the cancer research field. The spatial distribution pattern and the evaluation of of cancer cases can help administrative departments to make reasonable health policies. This information can provide a decision-making basis for cancer prevention, screening, and the rational allocation of public health resources. It can also provide data support for a rational formulation of cancer diagnosis and treatment. Many studies also found that cancers can have significant clustering characteristics in their spatial distribution, and they can also have characteristics of complex influencing factors. Therefore, the application of geographic information technology in the spatial analysis of cancers can improve prevention and promote the formulation of regional cancer screening policies. This and spatial exploration technologies such as spatial autocorrelation, cold and hot spot detection, and spatial statistics are widely used to detect the spatial distribution pattern of disease, detect areas of high and low incidence of disease, and the quantitative calculation of the relative risk of disease. Then spatial statistics, how it is spatial statistics applied in epidemiology. Statistical tools that are used to mainly map, explain, and predict the spatial distribution of health problems. Mapping means it is the visualization of the disease count or rate. And the second one is the clustering and the cluster detection analysis. That is the exploratory spatial data analysis. The third one is the correlation analysis. And the fourth one is modeling. That is explain or predict the disease or rates or counts. Therefore, some statistical analysis are required to evaluate the observed pattern of disease occurrence statistically. Spatial clustering and spatial detection techniques can consider location and attributes by identifying the hotspots and cold spots of the disease. So the very first step in spatial statistics is linking the disease counts or rate data to their corresponding locations and visualize them as maps. So the mapping helps to reveal some useful information, can also conceal the actual affected areas. Using a proper model, the possible relationship between the disease frequency, rate, and several explanatory variables such as environmental and socio-economic factors can be explained. A properly developed model can also be utilized to predict spatially or temporally disease distribution. Then next one is our study objective. This study uses geographic information system, GIS, and spatial analysis methods and scanning statistics for identifying thyroid cancer clustering patterns in Truncated. So This study uses the spatial data and the G-spatial analysis method, such as global Moore and I statistics, Ansleen local Moore and I, average nearest neighbor, that is ANN, and Getty's or cold and hotspot analysis, then kernel density estimation. Also, another spatial temporal analysis for identifying the geographical disease pattern. Also, scanning statistics to study the spatial temporal analysis incidence in Trivandrum from 2012 to 2016. So, this is our study area, Trivandrum district. We divided it into blocks. So, this study used the spatial data around 1,683 thyroid cases from Trivandrum during 2012 to 2016. So we have some exclusion criteria, that is the patients without address is difficult to track. So we exclude them and the address is outside the study area, that is also excluded here. So this is our methodology. First, you identify the spatial attribute information of the case data. For this, we use the Google Earth map address space matching interface was used to obtain the latitude and longitude coordinates of the cases. Around 41 cases of missing addresses, which account for 1.12% of the total. And the population data were obtained from the census population of 2001 and 2011 from the census of India, used to estimate the corresponding population. And the boundaries of 20 administrative area used in the study area were taken from DIVA-GIS database. And the landforms and geomorphological maps are prepared using the satellite remote sensing techniques. And major sources of elevation information of the study area were obtained from the Indian remote sensing satellite Cartosat-1 and provide the digital elevation model DEM of the area at a spatial resolution of 30 meter and captures the more detailed information. Then the relationship between the elevation and cancer type was assessed using the distribution map of cancer cases. So this is our flow chart of the study of this. We did complete this work. So first we can obtain the cancer registry from our population-based cancer registry, and we create latitude and longitude for the cancer registry data, and the spatial data obtained from the Trivandrum district, taluk, village and block, and the population data from census, and we estimate the population 2012 to 60, and primarily we create the geographic map to identify risk areas. And the slope maps of the study were created using 3D analyst and the spatial analyst extension in ArcGIS software 10.2 by using Cartosat-1 based on DEM, and the SATScan 10.2 version used based on the discrete Poisson models to analyze the case-wise space clusters. And then first we did the disease mapping. So the disease map can disclose the spatial pattern in the data that are not readily detectable in a tabular format. So some application of disease mapping are basic descriptions of the spatial disease distribution, hypothesis generation of possible relationship between factors and the health outcome, and spot areas representation useful for budget and resource allocation. But it has some limitation that is shaded mapping for area with a small population can lead to a high variation of estimated risk compared to the large population. So in this study, here this is our red area. It is more than 50 can rate per 100,000. So the map shows that the Varkala, Chirangir and Kalkuttam block of Trivandrum district, these are the three blocks, shows the high incidence of thyroid cancer, which are primarily coastal area, and it is the northwest region. Next, we did the global moral and statistics. This is a global normalized statistic. The global normalized statistics was used to estimate the spatial autocorrelation of feature attribute or variable, that is cancer incidence rate and feature location, that is the study area. And the measure evaluates whether the spatial pattern of the cancer incidence is clustered or random or dispersed based on the index value. And it is provided by this equation, and n is the number of spatial units and x is the variable of interest. And here it is the incidence rate, and weight Wij is the weight sharing the border or the point of k nearest neighbor for buffer. So the value close to the value of minus 1 indicate the dispersion, and the value close to the value plus 1 related the clustering, and the values close to 0 indicate the randomness. So in this figure, here we get the global model. I showed the statistically significant spatial autocorrelation of thyroid cancer in the entire study area. And here, Moran statistics is 0.49 and Z-score is 2.83 and the p-value is 0.004. And next thing is local cluster detection techniques. That is odd. That is for cold and hotspot analysis. It is a local measure of spatial autocorrelation and used to identify the location of the statistically significant hotspot or cold spot based on high or low values of the incidence rate. And it is provided by Gi star and computed as Gi star equal to this equation. And here n is the total number of spatial locations, and xi is the incidence rate of thyroid cancer of the ith location, and xc is the incidence rate of thyroid cancer for the jth location, and x bar is the mean incidence rate of the thyroid cancer for all the location in the overall study area. And Wij is the elements of the spatial weight matrix that represent the relationship between the location I and j. Here also, the Gi star analysis also, we identify a statistically significant hotspot of thyroid cancer incidence in here, Chittirangi and Karakottam block of Trivandrum district. Then here it is the kernel density estimation. Kernel estimation is a density-based point pattern method. It was applied to identify the hotspot concentrated the area of the distribution of spatial point elements, that is the area with a large number of patients. The area can smoothen with fewer cancer patients and obtain the overall spatial distribution of the number of patients by the conversion of the kernel density estimation. So the calculation method is given by this equation. Here k dot is the kernel function and r is the analyze the radius, and x minus xi is the distance between the point x and the estimated and the sample point xi. The kernel density KDE is a good way to locate the hotspot places. Here, this is the high area. The red places are the high area of thyroid cancer incidence. These findings in KDE indicated that the red colored area near the coastal region of Trivandrum district was classified as hotspot with a high density of cancer cases. Next one is the side scan risk scan. Here, side scan spatial temporal scanning was used to provide the quantitative risk value of cancer incident in identifying the detecting the risk areas. It performs the multiple scans and risk value calculations in the study area based on the incidence rate and inter-regional population base. So, side scan spatial risk scan statistics use relative risk and log likelihood ratio to judge the high value of risk areas. The relative risk, that is RR, is defined to the risk of a region compared to the risk of all other areas. So the calculation method of LLR, that is log likelihood ratio, is here. Here LLR is a log likelihood ratio, and N, capital N and small n are the total population in the area and the window respectively. And the C and the small c are the represent the number of cases or events in the area and the whole area. So here in this study it is 2012 here and 2013 the thyroid cancer spread is here, and 2014 the major part is the Chirangir Taluk, and 2015 it is also in Chirangir Taluk, and 2016 this is to the both Kaiputta block, Chirangir block and Varkala block. Very high incidence, and when we club together 2012 to 16 these three areas have high incidence. So in this study we used the SAT scan based on the discrete Poisson model to analyze the case-wise space clusters from 2012 to 2016. A maximum spatial clusters of size 50% of the population at risk and a circle of radius of 1 kilometer was selected for analysis. The corresponding p-value and z-score were computed to determine the statistical significance of observed spatial pattern based on the null hypothesis that the cancer cases are randomly in the study area. Based on this hypothesis, we start and so here between 2012 and 2016, the thyroid cancer varied widely throughout the Trivandrum district, ranging from no incidence to more than 20 per 100,000 patients. And several non-random hotspots and cold spots of high thyroid cancer incidence were revealed by its own GI star analysis at the block level. A significant spatial cluster with a relative risk of 1.61, here 1.69, here 2.04 and 2.02 and 3.98, and a log likelihood ratio LLR is 7.28 here, 7.20 here, and 14.34, 2.71 and 6.89 were observed respectively. So statistically significant hotspot of TC, thyroid cancer incidence observed in Chirangir, Varkala and Kadakuttam, and the same was observed throughout the study period. During the study period from 2012 to 2016, SAT-scan analysis detected a significant most likely cluster with a relative risk of 1.6. Here it is 1.6 and the log likelihood ratio is 4.53. So conclusion, the result shows that the spatial data can better achieve spatial matching and visualization through address conversation. Through point pattern analysis, spatial autocorrelation, kernel density estimation, cold and hotspot analysis, and scanning statistics, we can comprehensively identify the regional cancer distribution pattern and its changing process. We identified the spatial clusters of thyroid cancer incidence based on spatial scan statistics. Application of these spatial analysis methods and scanning statistics identified possible cluster of TC and provided an indication of possible target population for future studies using spatial data. The temporal and spatial analysis of TC incidence provides a scientific basis for the rational allocation of health resources. So the research results can provide a national policy reference for future regional cancer treatment resource allocation and cancer prevention screening. Thank you.
Thank you, Professor Preeti, for the splendid presentation regarding the identifying the thyroid cancer using statistical methods, a case study relating to Trivandrum district. And now the participants can ask any doubts to Professor Preeti. I think there isn't any doubts from audience side. So Professor Preeti, once again, we are so thankful for presenting your topic before the audience. Thank you.
Thank you, sir. Thank you very much.
Okay. I think Professor Eliama Matthew is now ready to. Sir, Sadish sir, do you want to add anything to Professor Preeti's presentation? Your mic is muted.
Yeah. Given a clap to the presentation of Dr. Preeti, that is all.
Okay.
Thank you very much, sir. Thank you very much, sir.
So now I think Professor Eliama Matthew is ready to.
Okay, welcome, madam.
Okay.
Welcome.
Am I audible?
Yes. Madam, please wait a few minutes because I have to, even though Professor Eliama Matthew needs no introduction in our circle, but since it is my duty to say a few more words about you.
And there are several international participants, so you have to give.
Yes. Even then, because when you talk about a Malayali biostatistician come epidemiologist, the first name that flashing over our mind is Professor Eliama Matthew. And today, Professor is presenting quite interesting because the integrated models for forecasting cancer incidence with a combination of AR and MA models. So Professor Matthew has a huge experience over more than 30 decades of teaching and research experience, especially in clinical field as a biostatistician, and a major pie of service is in Regional Cancer Center at Trivandrum. Presently, Professor Matthew is holding the position as Professor and Head of the Division of Cancer Epidemiology and Biostatistics. And moreover, Professor Eliama possesses a dual PhD both in epidemiology and statistics. And also, she has bagged many national as well as international fellows. To mention a few, because fellow of Academy of Medicine, Singapore, like that one. And earlier, she served as a postdoctoral fellow in National Cancer Institute, USA. And he has published a huge volume of research outputs. More than 100 publications are in her kitty. And many citations are there. Many book chapters are also there. And she has received many awards from India, Japan, USA, France, etc. So these are a few things about Professor Eliama Matthew. And I invite and I request on behalf of Wsta 2022 to present your work before the audience. Thank you.
Thank you, sir. And thank you for your kind introduction. At the outset, I thank you, Professor Satish Kumar, for giving me this opportunity. Okay, my topic of present, some echo. Are you getting?
Yes, a slight some echo.
Okay.
Now you can please.
No problem.
I think now it is okay.
Yes, it is okay.
Okay, my topic of my presentation is application of autoregressive integrated moving
whether
average.
you are using two computers or two devices.
Pardon?
Whether you are using two devices now for presentation. Whether you are using computer and a mobile or computer, two computers or anything like two devices. The sound is from there, so that the other device should be muted. That is why. Or Preeti, Professor Dr. Preeti or someone else is there using the nearby? Okay.
The screen is not moving.
I think Professor Elima Matthews joined from 2 devices. Maybe one is a mobile phone, so that is to be switched off.
That is what I mentioned.
Or she can mute the speaker of the mobile phone.
Yeah.
It is muted.
Now let us try.
Topic is, and I'm not able to move it also.
In that case, you can just share it once again. Stop sharing and then once again, please. Or in case of difficulty, we shall help you. No.
Now it is okay. So, Professor, you can unmute your microphone and continue.
Whether you utilized the mobile phone to enter into the meet earlier, and not
audio output from mobile phone, and that may be the reason.
Now it is moving, isn't it?
Oh, okay. Oh. So my topic is application of autoregressive integrated moving average. It is in short called ARIMA modeling for forecasting cancer incidence. Before coming to the topic, I will briefly explain cancer in worldwide statistics. So it is estimated that around more than 10 million cancer cases are diagnosed annually in males. Lung, prostate, colorectal, stomach, liver. These are the common cancers among males. And we have made a transition of cancer and proportion of leading cancers in world. This has come in the encyclopedia. This is published in the Encyclopedia of Cancer. We contributed a chapter. The common cancers in 1990 in high-income countries were lung, prostate, colorectal, etc. So oral cavity cancer, the 10th leading cancer. When we looked into the data in 2012, we observed that prostate cancer, kidney cancer are on the increase. And melanoma, malignant melanoma, it is a skin cancer. It has come in the 10 leading cancer site. Whereas when we look into the low and middle income countries, again, liver cancer, prostate cancer, and urinary bladder cancer. These are on the increase. When we see the data in females, breast cancer is the common cancer, followed by colorectal, lung, and cervix uterine cancer. And thyroid cancer is, of course, it is one among the 5 cancer worldwide. Then transition of cancer among females we can see that cervix uterine cancer, ovarian cancer, thyroid cancer, these three are on the increase. Among low and middle income countries, lung, corpus luteum cancers are on the increase. Now when we see the data in India, we see that these are the common cancers: lip, oral cavity, followed by lung, stomach, colorectal, esophagus. So it is these are the estimated number of cancer cases. Nearly 6.5 lakhs cancer cases are detected annually in India. Again, when we see the transition of cancer, in India, we can see that stomach cancer, it is increasing. Prostate cancer, stomach and prostate cancers are on the increase. Then when we see the picture in females, again, breast cancer is the common cancer, followed by cervix uterine, ovarian cancer, lip oral cavity, colorectal. These are the common cancers among females in India. When we see the transition of cancers, colorectal, corpus luteum, and lung cancer, these are on the increase. Now, when we see the data in Kerala, the cancer registry data, this kind of incidence rate and mortality rates are provided or obtained using population-based cancer registry data. In South Kerala, we have population-based cancer registry system covering all the 5 districts in Kerala. Southern districts, these are Trivandrum, Kollam, Alappuzha, Pathanamthitta, and Kottayam. These 5 districts are covered by RCC. These are the cancer pattern in South Kerala. Lung cancer is the common cancer in all the 4 districts in males. Oral cavity, colorectal are the common cancers in all the 5 districts. Slightly higher, we can see that lung cancer incidence quite high in Alappuzha district, followed by Kollam district. Then in females, again, breast cancer is the common cancer in all the 4 districts. The rates are high in Trivandrum, followed by Alappuzha district. So transition of cancer data, we can, with time trend analysis, we can use regression models, setting simple linear relationship between cancer incidence rate, that is our response variable, and the calendar year is our independent variable. This model describes overall changes of cancer incidence by fitting of a single straight line. But cancer incidence data are time-related observations, and hence the assumptions of linear regression independence and homogeneous variance may not hold. This makes simple linear regression model for logarithmic transformation response variable. Kim in 2000 introduced to fit trends in cancer incidence or mortality rates over a given period of time. This model identifies suitable location of points and estimates trends for each join point by measuring the annual percent change, APC. This joint regression, the National Cancer Institute developed a software for this, for estimating this joint point regression model. That model is linear and log linear joint point regression. This was modeled on significance of trends that was performed by BIC and Monte Carlo permutation method. Its advantage is over linear regression was we fit several straight lines. Using recent annual percent change, we predict the future cancer incidence rate. In both regression models, we fit only linear relationship, either single or multiple straight line for measuring trends and also for prediction, forecasting. However, cancer incidence need not be always linear. It changes. It can increase, I have already shown you, or decrease may happen due to increase in various exposures. We call it as risk factors, or introducing new cancer screening programs. Using this log linear regression model, these are the trends in incidence rates of common cancers in India. So we can see that breast cancer increasing, prostate cancer is increasing, colon cancer is increasing, rectal cancer is increasing. Then female ovarian cancer increasing, corpus luteal cancer increasing, lung cancer in women increasing. Unfortunately, cervix luteal cancer, it is declining. So all these kind of transition of cancer data, trends in incidence rates are plotted using joint point linear regression model. So this is another model which we fitted in using our data. We fitted, this is breast cancer incidence rates. So you can see that this is by age specific, by age. You can see that this is not linear in nature, but we predicted the cancer incidence rates, breast cancer incidence rates using this 15-year data we predicted up to the year 2020. Here comes the importance of ARIMA model. So autoregressive integrated moving average, or in short ARIMA model. In 1970, Box and Jenkins introduced ARIMA methodology to fit best model for time series. So linear combination of past values, that is AR, autoregressive, and previous errors, moving average, along with the difference for non-stationary data. Only requirement is prior data of the study variable in ordered sequence to make prediction. So here fit models, AR, moving average, and ARIMA with the different orders. These models are fitted only for stationary time series data. So forecast is suitable only for those series past values has sufficient pattern and information to its future values. So ARIMA, this is the ARIMA PDQ model. Yt is equal to delta plus summation I equal to 1 to p phi I into y is pi minus. Here p is the order of autoregressive process and q is the order of moving average process. Phi is the parameter of AR process. Theta is the parameter of MA moving average process. And epsilon is the error with the mean 0 and constant variance. And D is the order of differencing for D. Here P, D, Q. D is the order of differencing for non-stationary. So in ARIMA modeling, first is model selection, plotting observations in time sequence, that is to get an idea about the components of time series. That is trend. Autocorrelation, then autocorrelation function and partial autocorrelation function, we make a graph to determine the series, whether it is stationary or not. Then we perform statistical test for stationarity. So model identity, we apply. If it is not stationary, we apply differencing method or transform logarithmic or square root using. Then identification of order of the model, that is ARP model, MAQ model, and then ARIMA PDQ model. Then parameters are estimated using maximum likelihood estimate. Then third step is model selection. We select the model with the lowest AIC and BIC values. So then second is residual diagnostic checking at residual analysis. So checking of adequacy of the model. Errors are independent and identically distributed with the mean 0 and a constant variance. Then residual plot of ACF and autocorrelative function and partial autocorrelative function. Then statistical significance of residuals, Elgin box test is used. Forecasting, this is similar as the ARIMA model. Here T plus K. K is periods in the future. So then we find forecast error using root mean square and MAE, absolute error. This is the flowchart for representation of ARIMA model. First check whether the data is stationary. If not, we go for transformation, either differencing or logarithmic or square root. Then make it as stationary. Then the significance testing, ACF and PACF, and then coefficient estimation, diagnostic checking. Then we fit the model. This is the flow chart for fitting ARIMA model. So why then we use in the present presentation, we used cancer incidence data reported in Trivandrum during the from 2005 to 2011. This is our cancer registry data. This is 15-year data. We used thyroid and breast cancer incidence data, and it is crude incidence rate used for modeling, and we forecasted the incidence rates up to the period 2025 using ARIMA modeling. So this is the thyroid cancer data during this 15-year period, and the breast cancer data using this 15-year period in Trivandrum district. So this is the stationarity test. So we can see that this KPSS test is for checking of stationarity. So we observed that statistically significant. So we can use ARIMA model applying first order differential itself. So these are the AIC and BIC values. So minimum value observed before this ARIMA 1010 for thyroid cancer, and for breast cancer ARIMA 110, that is PDQ values. The lowest value obtained for thyroid and breast cancer. So we have chosen that lowest value, and the estimated model is using this lowest value. This is the ARIMA model for thyroid cancer and model for breast cancer. And this is the plot. The blue indicates actual value, and red the estimated incidence. This is for thyroid cancer, and this is for breast cancer. And these are the forecasted values for the year 2025. Forecasted incidence rate nearly 29 per 100,000 female. This is thyroid cancer is quite common in females. This is female incidence rate, and breast cancer, this is nearly 84 per 100,000 population, and these are the lower and upper confidence limits. And these are the forecasted plot. We obtained ARIMA 010 PDQ values, and here 110. In conclusion, ARIMA model can be used to predict cancer incidence based on its past values with stationary data. The incidence of thyroid, we have observed thyroid and breast cancers are increasing in Thiruvananthapuram, and we forecasted the incidence rate of thyroid cancer. This will be 29 per 100,000 population, and then breast cancer will be, sorry, it is not vast, will be 83 per 100,000 population. So in conclusion, ARIMA can be used for forecasting cancer incidence rate if we have a long time series data. These are the publications. These three are our publications. We used log linear joint point regression model and estimated time trend analysis. That's all. Thank you.
Thank you. Thank you, Professor Eliama, for your great presentation regarding the ARIMA modeling for forecasting cancer. And we felt that this ARIMA modeling is the masterpiece for econometricians because they are regularly using this one. And I think that ARIMA equation, there is some typing. Professor Eliama can later check some D is absent there. It may be a minor typing mistake. And now...
Error time?
No, in the ARIMA equation, you have a D term. The integration order is not typed, I believe. If you show that one, we can clarify this one. This may be a typing mistake. This may be. Madam can later check it because in textbooks it is given as delta D phi. D is the difference number of times it is differentiated. So that D is absent there, but the D is explained in the following steps. So it may be a minor typing mistakes.
Okay. I will check.
Yes, okay, ma'am. So now the audience can ask questions to Professor for your doubts regarding this ARIMA modeling. It is a very sophisticated tool for such an analysis. We have to give a big clap to the Professor Eliama Matthew for turning the direction to this area.
I am very sorry that this echo.
No, not too much disturbance from your side. We clearly heard everything that you have explained.
Okay.
Which software you use for this analysis?
What's the question?
So the once more you can ask.
Which software you use for this one, analysis of this one? SPSS or any other one?
This is R software.
R software.
R code.
Yes.
Coding R code is available. So we can use R software. R program, it is freely available, and the codes are also available. We can use that.
Forecast is also getting there from that one. From R software, you get the forecast also.
R software.
Forecasting is also done in the R software.
Yes. Sample data. In fact, you will get this prediction, this health economics 50-year data, per capita income forecasting, sample data, several other sample data provided using R code. You can plot, you can extrapolate, and you can forecast also.
Okay, thank you, madam.
Because in SPSS it is not available with that. That is why many of the researchers ask this question. Sir, Sadish sir?
Yes, very fine, excellent talk. Thank you.
Okay, madam. Thank you. Now our next, yes. I think Jagannath is available here.
Yes, sir. I am available. Yeah.
Okay. So move on to the next speaker, Dr. Jagannath Krishna KM. Is an associate professor in the Biostatistics Department of Regional Cancer Center. And Dr. Jagannath is an active, young, dynamic, and hardworking researcher, especially in the field of biostatistics. And moreover, Dr. Jagannath is an alumni of our Department of Statistics, University of Kerala, where he did his MSc and obtained the rank in that MSc course. And later on, he moved on to KUSAT, Cochin University of Science and Technology, for his doctoral program. And from there, he has got the PhD degree. And Dr. Jagannath started his professional life as a lecturer in biostatistics, Amartya Institute of Medical Science, Cochin. And later, Jagannath joined as a scientist in CSIR, Central Leather Research Institute, Chennai. And after that, he has joined the Regional Cancer Center as an assistant professor in the Biostatistics Department. During this short span of his service, he has more than 30 publications in international, national, and other reputed journals. And also, Jagannath bagged many awards, national as well as international fellowships also. So with a great pleasure, I invite Dr. Jagannath for your presentation on behalf of WSTA 2022. Over to you, Jagannath.
Thank you, sir. Thank you for the introduction. I would like to thank Sadish sir for inviting me for this, for presenting my study here. Is my presentation visible?
Yes.
Okay. So today I will be talking on intermittent state-wise cancer survival risk estimation using multi-state frailty model. In cancer survival, we have come across several problems, and one among them is regarding the cancer survival. For the breast cancer data, that forms the motivation of the study. Not only for the breast cancer, all the other cancer survival data also, we come across with such situation where after a person has been diagnosed as cancer, they may after treatment, after giving a completion of treatment, they may again have a recurrence. That means in the same organ, it can again come on, the tumor can come on the same site, or they can, after treatment, they can be free of disease. That means they are free from radiologically and clinically in sense, and some may end up with death, and some may pass through recurrence and then end up with death. So these different stages or stages is being observed. So that structure forms the multi-state framework. And with this, some background on the study. In survival studies, the covariate information of the patients is collected longitudinally at different time points during the follow-up period. And these patients may experience multiple events during the follow-up, as I mentioned in that graph figure. So in this situation, the simultaneous estimation of risk of these events can be done using multi-state models. And multi-state models are typically used to characterize the progression of a set of individuals through a succession of states until they come to a certain endpoint or the observing state. The example has been mentioned earlier. So under a more complex scenario, there can be a number of intermediate phases called transition state with a complicated chain of transition interconnecting them before one of the several possible observing state is reached. So the important function for estimation in a multi-state model are the transition counts of individuals moving from one state to another, and the number of individuals at risk of transition from a particular state to another state. So the exact evaluation of these two stochastic processes is particularly and practically hindered by the presence of several types of censoring. In cancer survival studies, the most commonly observed and occurring censoring is the right censoring. And that happens when we lose track of the movement of an individual at some point of time while the individual was in a transient state of the model. A basic objective of a statistical analysis is to estimate the transition and at-risk processes, which in turn can lead to the estimation of the state occupation probabilities for the different states in the model. So these estimated probabilities are important since they provide an idea about the chance of individual occupying a certain state in the model at a specified time point. In particular, the concept has been extended to the survival function in the context of lifetime data analysis to a multi-state framework. And the generalities about multi-state models can be found in Anderson et al. 1993 and Hogarth 1999. The role of different timescales in modeling chronic disease is detailed in Kerjing 1991, while description of how to treat incomplete observation is described in Klein and Mosberger 1997 and Comenges et al. In 1998. Anderson and Kerjing 1993, Hogarth 2000, Putter et al. 2007, Anderson Premi 2008 are some among them who has discussed in detail about the multi-state modeling. A multi-state model is a continuous time stochastic process allowing individual to move among a finite number of states. Multi-state models have become increasingly useful to understand complicated biological process and to evaluate the relation between different types of events. Hence, it has been now applied in cancer survival studies also. Different model assumptions can be made about the dependence of the transition rates on time. And the Markov model is used for the transition intensity to estimate the transition intensities that only depends on the history of the process through the current state. And the process OIT for t greater than 0 is a Markovian if and only if for any st with 0 less than or equal to s less than t, we have equation 1. That it doesn't depend on the history. And it has been dealt with Cox and Miller 1965, Chiang 1968, Tai 1986. That's some of the literature, and the basic literature is in Chiang 1968. And the book by Hogarth 2000 explained different types of standard multi-state models such as mortality, competing risk, disability, alternating, and recurrent event models. And these are some of the models which depicted here. And among them, two of the models is explained here. The illness-death model. So the Markov models become mathematically tractable if we denote the transition intensities as lambda 1, 2 of t, lambda 1, 3, lambda 2, 3, and then we get equation number 2. So this result follows from the relation between the hazard and the survival function in survival models. And lambdas are the hazard rates or transition intensities. In this case, let t denote the time of exit from state 1 and note that t has hazard function lambda 1, 2 of u plus lambda 1, 3 of u. So similarly, the transition probabilities P12 and or P13 can also be estimated in a similar fashion. And the surgeon time probability is given by equation number 3. So by considering the exit from state 2 as failure, this expression gives us the probability a surgeon in state 2 exits P minus s, given that it started at time s. And this also discussed in Chiang 1968. And coming to the competing risk multi-state model, and the competing risk is the term used to describe situations in which an individual may die or fail from different causes, or simply have different modes of failure. For in cancer survival, we can observe that the patient may fail either due to the cause of death will be the cancer, and it can be due to other causes like accident or heart attack also. So heart attack or accidents are treated as competing risk. Consider a model with the 3 modes for convenience, labeled as state 0, 1, 2, 3. Let us consider a Markov model and assume that t equal to 0 corresponds to the time the person is put on the first course. Denote the 3 transition intensities as lambda 01, 02, 03. We consider exit from time 0 as a failure time. Its hazard function is lambda 01 of u plus lambda 02 of u plus lambda 03 of u, and therefore we have equation number 4. And corresponding to the survival function, we note that P0k of 0t is given by the expression given in equation 5. And since if a person is in state k at time t, there must be some time u less than or equal to t for which they were in state 0 at u minus. And then make the transition to state k at u. So that means there is some lag time. In the competing risk literature, the function phi are called the cumulative incidence function, since they give the cumulative probability of failures of each mode up to time t. And this regarding the competing risk multi-state model, one can refer to Anderson Kurtzing 2002. Basserman et al. 2011 discussed in detail on competing risk in a multi-state model using R program and their application in R. This article illustrated multi-state model to access the treatment effects on multiple paths along with the disease process that patient could experience in a clinical trial. Excuse me. Tenru et al. 2020 also discussed in detail on the computing risk in multi-state setup. Cook and Lawless 2018 in his book have given a detailing on multi-state model, and he has explained several applications of a multi-state model using our program. Excuse me. Given a fitted MSM with absorbing state, one can estimate state and marginal specific life expectancies. Ruiz Castro and Senga 2020 constructed a piecewise multi-state survival model and illustrated the application of this model using breast cancer data. Jackson 2011 focused on multi-state for panel count data and their implementation in MSM package in R. Coming to the multi-state model, many of the multi-state introduced in literature assume the intensity to be homogeneous. Hence, Koch's proportional hazard model is used for estimating the risk at each intermittent state. And Koch's proportional hazard model is given by equation number 6, equation number 7, 6 and 7. And here, lambda naught t is the baseline hazard and beta is the vector of regression parameters. Excuse me. Avoiding the hidden heterogeneity may affect the inference in multi-state model. That is one of the main problems encountered in many of the survival analysis. So in such situation, the concept of frailty introduced by Clayton in 1978 and Opel et al. In 1917 will be more useful. The concept of frailty is, let Z be an unobserved random heterogeneity factor for survival. Then the frailty model, an extended form of CPH, is given in equation number 7, where lambda naught of t is the baseline hazard function, beta is a vector of regression coefficients, and x is the vector of observed covariate, and z is the frailty variable. The inclusion of frailty into multi-state model can provide complex survival models accounting for dependence between grouped subject as well as between times to event of different types within the same group. So the multi-state model with frailties, which was introduced by Allen in 1988. So let ZLM as the unobserved random effector frailty, which are assumed to have independent distribution specific to the transition from L to M. The intensity function is given by equation number 8, where ZLM corresponds to the frailty term and lambda naught LM is the baseline hazard and beta LM are the regression coefficients and XLM are the vector of covariates. Bhattacharya and Klein 2005 considered progressive multi-state model with exponential baselines. They used correlated frailties within subject and obtained by summing independent gamma random variables as suggested by Ashin et al. 1995. And gamma frailties are the most commonly used frailty model in all the survival modeling approach. Putter and Van 2011 discussed some aspect of more general multi-state model with dependent frailties within subject. Pickless and Chausley 1995, Govindaraj et al. 2011, and Putter and Van 2015 used the multi-state frailty model for various application in medical data. Bhattacharya and Klein 2005 presented a non-homogeneous Markov model for multi-state frailty model. N et al. 2010 considered multi-state frailty model for modeling adenocarcinoma in large bowel, and in the same year, Ma et al. Presented in a working paper a similar model with gamma frailties for time-use pattern analysis, explicitly formulated in terms of transition-specific hazards. Both these models assume frailty which are independent for different transitions but shared by groups of subjects. These assumptions are more in spirit of shared frailty model. Both the approach, the shared-like and the univariate-like frailty multi-state models are used with quasi-semi-parametric inference and prediction by Linguet et al. 2012, who showed an application to intensive care units. Anderson, Kerjing, Lee et al. Are some among them who have applied this multi-state frailty model Rotlo et al. 2019 also use this model. And the estimation is possible via maximum penalized partial likelihood function. And this model can both account for risk differences between groups and models and risk of different events simultaneously. And log normal is not that much used, but even compared to other models, log normal is also used for modeling frailties, and some of the references are given here. And coming to the study, in the present study, we consider a 4-state multi-state frailty model for estimating the risk for breast cancer survival data. The first figure, what I have introduced there, was a transition from no evidence of disease to death. But for our data, what we have considered, such a transition is not there. So we have only a 4-state model. And we fitted, we have our multi-state frailty model is given here. Let ZLM be the unobserved random frailty model, which are assumed to have independent distributions specific to the transition L to M. Here we have used two different frailties. One is log normal and the other one is the gamma frailty model. And we compared it with the multi-state model. The incorporation of frailty in the multi-state model, we have 5 transition intensities that is given in equation 9 to 13. And the estimation of the model is done here. And Marrow multi-state models with proportional hazard can be expressed in terms of the transition-specific hazard for transition of type L for all the ordered couples ML in and the subject M, and it is given in equation number 40. With lambda L naught of t as the baseline hazard for transition of type L, beta the vector of transition-specific covariate, the coefficient vectors beta L, and XLMT as a vector of transition-specific covariate derived from the covariate vector XL by transforming data from wide to long format. For each transition type L and each subject M, NLM of T is the counting process being 0 at the beginning and increasing by 1 whenever the subject experiences an event of type 1. OLM of T is the at-risk stochastic process. Once the multi-state data transformed into long format, the model can be treated as a Cox model, stratified on transition type and with left truncation at the time of entering each state. Then semi-parametric inference for regression parameter is based on the partial likelihood, that the likelihood profile with respect to the baseline hazard lambda 1 naught of t to lambda L naught of t. For the multi-state model, the partial log likelihood function is given in equation number 15. With OLM naught beta t as given in equation is the weighted risk set at time point t. So estimating the multi-state frailty models for this model 16. In the frailty model, the frailties are unobserved realization of random factors which are assumed to be independent and identically distributed with a common frailty distribution ZLM. Here ZLM is considered as log normal and gamma. In a semi-parametric estimation approach, no parametric form is assumed for the baseline risk. So the obtained penalized partial likelihood expression in terms of counting process is given in equation number 70. That is the likelihood function mentioned in equation 15 plus the log of the frailty term. So for the illustration, we have considered 492 breast cancer patients registered in Regional Cancer Center Trivandrum during the year 2006 and followed up till 2016. The covariate considered for the present study was stage, age, laterality, lymph node involvement, history of metastasis, comorbidity, and tumor size and diagnosis. And MSM package in R was used for the analysis. We found the number of times each pair of state were observed in successive observation times is given here. There is the frequency of a patient being in a state is given here. That is from diagnosed to recurrence, there are 42 events. Diagnosed to stable disease, that means no evidence of disease, it is 274. And diagnosed to death, it is 175. And recurrence to stable, no evidence of disease is 13. And recurrence to death is around 30. So the corresponding transition probability matrix is shown here. We can observe that recurrence to death has higher probability, and recurrence diagnosis disease to recurrence is also showing a higher probability compared to diagnosis to death. And here we use the information criteria to identify the best fitted model. And we found that the AAC and BAC criteria showed that log normal fidelity model, multi-state log normal fidelity model is better fitted for all the covariate. And hence, for the univariate analysis, we can use the log normal fidelity. Even then, we used all the three models for the estimating the risk. And the univariate analysis shows that almost all here from state 2 to state 4, that is from recurrence to death, the risk is high for all the states. And all the models are giving almost the same result for all the transition. Between transition, the same pattern was observed, only the risk was showing higher in either of the models. And here this is for the covariate stage, and this is for age. Also, you can see that from recurrence to death, it has a higher risk, that is 13.4 for the log normal fidelity model. And for laterality also, we can see that from recurrence to death shows higher incidence, higher hazard rate or failure rate, that is 11.9 for Cox, and it is little bit overestimated. And here log normal fidelity shows 5.74. And lymph node involvement also is showing a similar trend. And other from diagnosed to death, it is somewhat risk is there, but it's not that much high. And this is for history of meds. The same pattern was observed. Comorbidity as a tumor size is also shown here. Now, these three models has been then compared based on the predictability of the model, the ability to predict the risk. And we observed that the C index, that is a concordance measure, showed that it is higher for log normal frailty. And this LCV, that is likelihood cross validation, also shows it's better for log normal frailty model. So it is better log normal frailty to be used for estimating for this data set, at least for this data set. And coming to the multivariate analysis, we observed that the multi-state log normal frailty model is giving the better concordance, and AAC, BAC is least, and also the LCV is least, and the frailty parameter is highly significant, and its p-value is also showing significant. Even then, the gamma is also having a significant frailty, but other measures like concordance, AAC, BAC, and LCV are favoring log normal frailty model. And the corresponding multi-state frailty model, here stage is not a significant factor, so it has other variables. We got it as a significant joint predictors for each of the states independently, that is for recurrence to death or diagnosed to death or diagnosed to recurrence is given here. Here also we observe that for the joint model, for the multivariate model, the risk for age more than 50 compared to less than 50 is 3.59 times. For lymph node, it shows the protective effect. And comorbidity, again, it is not significant, but here for comorbidity is not showing significance for any of these variables. And coming to the concluding remarks, multi-state models provides the information on how each covariate was affected in the movement of a patient through different states. Thus, for state-wise analysis, multi-state models are the best choice, as multi-state model allow the state-wise estimation of risk, transition probabilities, and predict the survival pattern. In the present study, we observed that frailty had a significant role in intermittent state-wise risk estimation. And based on the AAC and BAC, it is found that multi-state log normal frailty model as the best fitted model, followed by gamma frailty. The hazard rate obtained based on all the three models showed that the covariate stage was independent predictor for the transition from recurrence to death, and however, the frailty was not significant. The covariate age, lymph node involvement, history of meds are found to be independent predictors for the transition, except for diagnosis as disease to recurrent status. The frailty corresponding to log normal was also found to be significant with higher C index, that is concordance variant. The covariates, laterality, comorbidity, and tumor size also found to be significant predictors for transition from recurrence to death, and their corresponding log normal frailties were also significant. But in this case, gamma frailties are not significant for all these covariates. Thus, the univariate analysis showed that each of the covariates was an independent predictor for either of the events in at least one state of transition. The C index and likelihood cross-validation show that multi-state log normal frailty as a better predictive model compared to multi-state gamma model and multi-state model. The AAC, BAC, and LCV were minimum for multi-state log normal model in the multivariate setup also, and the C index and significant frailty parameter also showed multi-state log normal frailty model as the better predictive model. The multivariate analysis showed that covariate age, lymph node involvement, comorbidity, history of metastasis, tumor size, and laterality together were significant predictors for mortality due to breast cancer. Also, the covariate age, comorbidity, and tumor size together forms significant prognostic factors for patients in the recurrent state to move to the observing state, that is death. So thus the study identified the prognostic risk factors that contribute to the risk for recurrence and death in breast cancer patients. And this study also highlights the application of multi-state log normal frailty model in cancer survival study to assess the risk at intermittent state of transition. Here are some of the references. Thank you for giving me the chance.
Thank you, Dr. Jagannath, for your outstanding presentation here. I hope that the participants have much benefited from your research findings and all those things. And now it's a questioning time. Participants can ask any doubts or suggestions to Dr. Jagannath Krishna. I think nothing. So Sadish sir, do you want to add some more thing?
Yeah, in fact, he did a very good work. A big clap to him.
Thank you, sir. Thank you so much.
And now in the there are students from the biostatistics area also there in the group. Probably they can ask something.
Yes, yes.
I think Sudesh has something to ask, probably. Dr. Sudesh is
Jakarta.
Yes, yes.
We can use some non-parametric method. You are using everything log normal, gamma, and other thing. Non-parametric methods are there.
No, not being used now. Yeah. Not been used for this study.
We need to assume.
Yeah.
Now, is there any method? That is what I am asking.
No, we haven't looked into it actually. It's we start with this model. We have tried with other models also, like inverse Gaussian, positive stable, and all those things. But somehow we are not getting a convergent values. So then that is the reason we have chosen only log normal and gamma frailty. And we are also planning to look into the non-parametric aspect of it.
Okay, thank you.
And the simulation study is also pending actually. It is not shown here. We have to look into the simulation study.
Okay. I like it. Very nice.
Oh, thank you so much.
Okay, thank you, Jagannath, once again. Now we can move on to the next presentation. The next presentation is from Dr. Anil C. Matthew, currently working as Associate Professor of Biostatistics, PhD Institute of Medical Sciences and Research, Coimbatore. And we have seen Dr. Anil as a motivational speaker for statistics students in many platforms, and he has always been advocating for the betterment of biostatistics. And today, Dr. Anil is presenting a work entitled Competing Risks in Survival Analysis, Applications in Clinical Research. And as far as Dr. Anil's bio is concerned, he took his doctorate degree in biostatistics from Bharatiyar University, and also he has served in various prestigious institutes like CMC Vellore, All India Heart Foundation, etc. And he has received many fellowships, national fellowships, and he has more than 30 publications of international as well as national level. And he is a member of many bodies such as International Biometry Society, life member of Indian Society for Medical Statistics, and so on. So I request and I invite Dr. Anil C. Matthew for presenting your work before us. It is over to Dr. Anil C. Matthew. Thank you. I think your mic is muted. Please unmute your microphone.
Yeah. Is it audible?
It is audible, but I think you have signed in from two devices. Some echo is disturbing us.
Now?
It is okay now. It is very much audible now.
Yeah. Slide open. Thank you, Satish Kumar sir and the organizing team for giving me this opportunity to give a talk in this workshop. And the talk is basically meant for the research scholars who is working in the field of statistics to get an orientation towards the subject of biostatistics. And my talk is competing risk analysis. This competing risk is a common topic to many people are familiar with it. I just wanted to highlight how it is applicable for a clinician, for those clinicians who are working in the clinical research field, how far it is relevant. This is just to get a motivational talk for the research scholars of statistics and biostatistics to get an overview on the subject. It is not an in-depth subject, in-depth matter, I'm not discussing it, but the basic of this competing risk analysis. So the outline of the session is definition of competing risk survival data with the examples. Competing risk events and cause-specific analysis. Describe the independent assumption required in the analysis of...
Your slides are not moving.
Slides are not moving. Is it moving?
No.
What to do? Yes.
Yeah. Repeat it. That's good.
Is it moving now? Hello?
Try just up and down because now it is,
yeah,
the contents are visible.
It's moving.
No.
Yeah. I think yes.
Yes, okay. So the outline of the session is definition.
Please go to the next slide.
Is it moving?
No, still it is on the first page only. Yeah. Now it is coming.
So the outline of the session is definition of the combating risk survival data with examples, combating risk event and cause-specific analysis, describe the independent assumption required in the analysis of combating risk data, describe the cumulative insights approach for analyzing combating risk data, and finally, the concluding remarks. So the picture itself tells we have only one option, which is that option, that is the question. So what is the definition of combating risk? Combating risk are events that occur instead of the failure of events, and we cannot treat them as censored. For example, in the study on recurrence of breast cancer, the cancer occurring in another location is combating risk. For example, when we are planning to study the recurrence of the breast cancer, if the patient getting a lung cancer, how we are going to treat it? The combating risk might be dependent and it's difficult to test it. And we cannot treat combating risk events as the censor. In a very basic level, this is a basic flowchart of the survival analysis. As we all studied, there is an event is there. There are so many people having the event which is of our interest. There are so many people will be censored category. There are so many people who are withdrawn from the study. They also keep us under the censored category. For so many people, we have to stop the study and we have to study how it has to end it. They are also censored category. And there are so many people which are lost to follow. They are also censored category. But the question for it is, when we have occurrence of another event which is of interest happens, how we are going to treat those patients. This is actually what is a branch of survival analysis, which is called a combating risk analysis. So basically, when there are at least two possible ways, a person can fail, but only one such failure can actually occur. For example, in a clinical trial, a person can die from cancer or CVD. Deaths due to CVD can mislead the results, but both cannot happen together. Another example, in a clinical trial, a person can die from cancer or CVD, and death due to CVD can mislead the results. So when you look this phenomena in a randomized control format, the primary concern is we are interested in seeing the hazard ratio for the treatment when it compared for the placebo. Basically, hazard ratio is equal to treatment versus placebo is equal to 1, allowing the combating risk from the CVD. And the null hypothesis is the cancer death rate, the treatment group, is not different from the cancer death rate in the placebo, allowing for combating risk from the CVD. In a clinical trial, a person can die from cancer or CVD. Death due to CVD can mislead the results. So we have objective number 2 can be the hazard ratio of cancer deaths versus CVD deaths is equal to 1, allowing for all predictor variables. That means the cancer death rate is not different from the CVD death rate, controlling for the predictors. So basically, when we look in a randomized control trial format, the major objective of all this survival analysis, all these objectives maybe, they compare the survival time in months or placebo versus treatment for prostate cancer patients to measure the efficacy. But patient can die with a combating risk, cancer deaths, CVD deaths, or deaths due to other causes. So the main objective of this, let us take the objective, effective treatment for a prostate cancer patient, controlling for the predictors. As we know, the general data entry format will be, the outcome variable will be the time, survival time. And the main predict exposure factor which we are interested in is the treatment. And we have the covariates which is called under consideration. For example, in this study, the treatment is the exposure factor and covariates are the age or other predictors are age and size of the tumor. And how to approach this thing? The first method is actually called a cause-specific analysis. In cause-specific analysis, separate models for different types of events. That means cancer deaths is the event of type of interest. All the combating risks we can be there considering as a censored. So basically, once again, I'm just explaining you for the beginners, the outcome variable, let us in a simple way, if you look into it, the column part, the first dependent variable is the time, which is the time factor. The exposure factor is the treatment. And we have the covariates. And we have one more factor, which is status of the thing, which is actually event happened and sense order. But in this scenario, we have three things we have to consider. One is event happened, second is sense order, and third is called a combating risk. The whole scenario, how we are going to address this issue, particularly when we look in a randomized control trial. And the first and simplest way of looking into it, very easiest way if you look into it, keep the combating risk also as sense order. That means there are only two types of event. Event happened, rest of all the things comes under the sensor category. So the hazard ratio in this scenario is, hazard ratio for the treatment is equal to Cox proportional, simplest model which we are going to take. Baseline hazard into e raised to beta 1, the treatment, plus beta 2 age, and beta 3 the size. And treat for, and when you do the results, so what I got is treatment has a significant positive effect on the survival for cancer deaths with the combating risk from CVD and other risks. And the same approach can be used for the other combating risk also. But the main issue is, what we are going to do is, in this scenario is, we are going to keep them as sense order, combating risk and the sensor category together. But here we are going to violate, we are going to think about one important assumption related to the sensory, which is actually what we call it as independent assumption of the sensory. That means issues related to the Kaplan-Meier estimation, when this assumption of the independent, how we are going to consider it. What is the meaning of independent assumption? The independent assumption of sensory, what is the meaning when we say sensory is non-informative or independent? Here what it means is all subjects have the same values of covariate predicates. That means health, poor health and God health. Sensoring is non-informative or independent means a person with poor health and good quality are equally likely to drop out from the study. That means we require that. The risks are independent, that means non-informative. How informative sensoring leads to biased results? People who have censored due to poor health are more likely to have died than those who not censored. That means what will essentially happen is the estimated survival probability at any time t may be overestimated if a large of those censored have actually failed. So how can we determine that the combating risks are independent? We can never prove that combating risk or they are not independent for a given data set. We can never prove that a subject who died from CVD at time t would have died from cancer if he has not died CVD. So nobody can predict it. So the first combating risk, the alternate strategies which we can look in this independent assumption is, the strategy one is decide assumptions satisfied on clinical or biological ground. That means subjects who were censored because of the CVD deaths were no more or less likely to have died from the cancer deaths. Only clinicians can have to look into their clinical background, they can look into it. And second strategy is include the common risk factors on the survival model. That means age and smoking were the common risk factors for both the CVD and cancer models. And third strategy is actually what we call it as sensitivity analysis. That means we can determine the extreme ranges of the parameters under violation of the assumption and observe the difference. So sensitivity are two extreme situations. The situation number one is convert the CVD deaths and other deaths also as event one, along with the cancer deaths, and obtain the hazard ratio for the treatment. Assuming that if they have not got CVD or other deaths, they would have died by cancer deaths. And situation two is consider CVD deaths and other deaths as censored event and change the time as the maximum reported time for all individual, which is CVD or other deaths, and obtain the hazard ratio for the treatment. Assuming that if they have not got the other deaths, they would have died due to the cancer deaths also. And if the difference between these two hazard ratios are small, then independent assumption is satisfied. Here is just one example how the Kaplan-Meier can misguide the results when this assumption is violated. For example, 99 people have died due to the CVD and 1 people only died due to the cancer. What will happen is the conditional probability of surviving more than 5 months becomes 0 if you do the same approach. But what proportion actually died due to the cancer? Only 1 cancer death among the 100 initial subjects. Now the question here it is, how many of the 99 CVD deaths would have died cancer at 5 months if they had not died CVD? Because we cannot answer this question. See, this is an unobservable question actually. So nobody can give an answer to this question. What we can do is only sensitivity analysis. The two extreme scenarios we have to look for it. The scenario number one is, suppose all the 99 subjects who had died with the CVD at 3 months would have died of cancer at 5 months. If they had not died CVD, the 100 subjects also died due to the cancer. Then the Kaplan-Meier survival probability at 5 months is 0, which is the same as obtained earlier. But why these two results are the same? This is because in Kaplan-Meier, we assume censoring is independent. Those who were censored at 3 months were as likely to have died from cancer at 5 months as those who were in the risk set at month 5. And in the sensitivity analysis too, suppose 99 subjects died of CVD at 3 months would not have died cancer if they have not died CVD. Also, the 100 subjects died due to the censoring as before. Then what will get is the 5 months risk of cancer death is going to be 0.01. Which of these two risk estimates is more informative in a clinical perspective? The risk 0.01 is informative from the standpoint of view of treatment utility for cancer. That means the proportion of patients needing treatment is very small. The risk 1 is informative from a etiological standpoint of view that the cancer survival is unlikely after 5 months. So what's the final conclusion from all these things? The simplest conclusion is, when there are combating risks, Kaplan-Meier survival curve may not be very informative because it is based on the independent assumption about the combating risk that cannot be verified. And we have an alternate approach which is actually called the cumulative incidence curve. This cumulative incidence curve is originally suggested by Kalbeflesh and Prentice in 1980, estimates the cumulative incidence function in the presence of combating risk models. So in the first step, we calculate the Kaplan-Meier estimate of the survival probability from all the events, even under interest as well as the combating events. In the second step, the conditional probability of experiencing the event of interest are calculated, and the cumulative incidences are estimated using these probabilities. The cumulative incidence of a failure up to a given time is the probability that the individual dies at that time. The cumulative incidence of a failure is the sum of event incidences occurring up to that time. The CIF is a converse of survival function, and cumulative incidence at a given time is 1 minus survival. So the steps in the CIF is calculate survival probability using Kaplan-Meier curve, taking both events under interest as well as combating event as event. That's step number 1. Step number 2, take only event of interest as the event. Calculate the failure time as the ratio of number of failure to the primary event, to the total population. And step number 3 is use survival probability up to j minus 1 the time as point as obtained from the calculations in step 1. And step number 4 is find incidence of jth time point as a product of failure rate at jth time point and overall survival up to j minus 1 the time point. ITJ is HTJ star into STJ minus 1. And calculate the cumulative incidence up to jth time point. That is the sum of the incidences in this interval and all the previous time intervals. So this is a technical part of, when you look into it, it's very simple. As I told you, there are 3 events are there. Alive is censored, death due to breast cancer is the event, and alive is the censored, or death due to other cancer is the combating risk. So first step, event is considered the combating risk alone we are giving as star, and censored we are keeping this under number 1 and do this probability. So second step, what you have to do is, you just keep this probability 1 step below and keep the hazard ratio from the incidence of 1 and multiply it, then go to the cumulative incidence. It's a very simplest procedure only, not much of the complicated things. And how the users of the CAC, the data of a hospital, 100 patients underwent a transplant, 60 died without relapse by year of 2 and 20 relapsed during the year of 4. And in hospital B, another hospital, 100 patients underwent a transplant, 20 non-relapse deaths by the year 1, 15 relapses during the year 2, 14 non-relapse deaths due to the year 3, and 5 relapses during the year 4. And if you see the Kaplan-Meier curve and CAC estimations, what I'm going to do, that not much of the details, basically what will happen is that the Kaplan-Meier probability are different for the 2 hospitals because the combating risk contribute a different pattern of censorship in the 2 hospitals. However, the CAC curves are the same at 4 years. This is because cumulative incidence curve gave marginal probabilities that are not influenced by the pattern of censorship of the combating risks that are treated as censored. The disadvantages of the CACs, it is not estimated using the product linked estimation. And most of them are wanted how to some statistical softwares to use it, SPSS, SAS, data. These things are not available in any of these packages. And modeling CAC with the covariates is more complicated because today's by univariate analysis alone, nobody is going to satisfy. People want to do multivariate analysis. I don't think we have the facilities for it. And comparison for CAC curves and other statistical tests. For example, log rank tests we will do for the survival analysis. We don't have facilities to compare the CAC curves. And we have some extension works out. Gray 1980 developed a test to compare 2 or more CACs. This test is analogous to log rank test. However, this test does not adjust covariates. And 1999, Fine and Gray provided a methodology for modeling CAC with the covariates. And we have some more latest advanced Lund MCNA approach in 1992. There are some more modifications are there. We have the condition, anyway, this I am going to tell. So the concluding remarks is, the combating risk are events that occur instead of the failure events, and we can't treat them as ignored. Remember, please, the word I have used is ignored. When combating risk are present, we should look at CIF instead of the survival function. Assessing covariate effects on the CIF using Hawk's regression is difficult, and instead, the use of Fine and Gray approach will be more meaningful. And as you know that our Shankaran sir in the Cochin University has published a lot of papers in the combating risk, bivariate combating risk models under random, left truncation and right. A lot of papers are there. But what I have presented is the applications in the field of clinical research. And we have saw some of the papers are very good, not on combating the survival, and British Journal of Cancer is published in 1988. So many publications we have done in this field. And these are some of the good references which you can look into it. I have mentioned some of the references. And this is a good book actually. Those who are interested in the research scholars can refer this book, Melania Pindelay, Combating Risk, a Practical Perspective. It's a very good book which those who are interested in the research scholars can read this book. Again, it's a great pleasure to be with you in this evening. I just wanted to have just a motivation talk for the those research scholars who are interested in this particular subject, combating risk analysis. Thank you.
Thank you, Dr. Anil, for your nice presentation regarding the topic. Now, the audience can ask questions if you have any.
Hi, sir. This is Dr. Yadav. Can you hear me?
Yes.
In Stata, there is a few functions for computing risk analysis, like STC, right, etc.
Yadav sir, your voice is very meager, so you can louder.
I just want to mention in Stata, there are a few functions like STC, Raj or something like that for computing. And there are some user-defined functions also, some ADO files also for the computing risk analysis available.
Okay, sir. Okay, sir. It's okay, sir. Because I was not aware about that. It can be able to compare that covariate adjustments are possible or not, sir.
Yes. There are other functions also for other implementation of sub-distribution result functions are also available in Stata. A lot of functions are in like ADO files, or user-defined ADO files.
Okay. Thank you.
Any other questions?
Yeah, I'm Satish. Actually, I want to add on a point here. There are some recent development where we can specify the cumulative incidence function using linear transformation model. So there is a paper by Mao and Lin in 2017 in JRSS. So they discuss this aspect.
Okay, sir. If you have the abstracts and if you can share in this group, it will be better. We can go through it. At least the abstract part of it, if you can share in the group, it will be useful for the other people also. So it's good.
Yeah, I will write to you about that paper.
Thank you, sir. Thanks.
Yeah. Okay. Thank you.
Is there some?
Yes. So In fact, we have concluded this session within the time.
1 minute, sir. Actually, I forgot to congratulate him because he gave a nice way of presentation about this computing risk. So I just add some comment that is not a good idea. Anyway, it is a very nice one.
Thank you, sir. Thank you. It's a pleasure to hear good comments from you, sir. Thank you.
Okay, now our technical section, especially devoted to the biostatistics research, is now over. All the talk were excellent, and it covers different areas of research, right from the methodology part to ARIMA models to risk analysis. And I hope and believe that this session has benefited much to the research students. Now, over to you, Dr. Sandeep.
Yeah, in fact, a very excellent session and very good talks, very informative talks, especially to the biostatistics people. They are much benefited out of these sessions. I would like to extend our heartfelt gratitude to professors in this session who have given these talks, especially Professor Adil C. Matthew, Professor Eliama Matthew, Professor Yadav, Professor Preeti, and Professor Jagannath. And let us give a big clap to each of the speakers. And in fact, we are very much benefited out of your deliberations. And also, we would like to extend our gratitude to Dr. Baiju for chairing this session and introducing the speakers in a very nice way, and also managing the session in a very beautiful. Thank you so much for your support.
Thank you, sir. Thank you.
Thank you. Thank you, sir.
Thank you all.
Thank you.
Can you hear me? This is
Yes.
Yes, okay.
Yeah.
I have to actually put my slides because I cannot get the screen. There is no scope.
In fact, we have scheduled the next session at 7:30, and probably several are there to watch for those sessions. Next two sessions are the two plenary sessions. In fact, several are waiting for watching those sessions. So it is better to start at the time itself.
Absolutely.
Yeah.
I have no problem at all. And I was, it's Saturday, so no problem. No rush.
Also, if you want to check whether the sharing, the presentation, that we can do.
Yeah, as long can someone flash the slides? That's it.
Yeah, Professor. Yeah, we can do. Or in case of any difficulty, we shall do it from here. I think I'll send it.
No, I cannot do it. You have to start. Somebody just put the slides.
Yeah, Professor. So by the time, let us utilize this time for interaction. That's
yeah. It's so nice. See so many people.
Professor Ghosh and Professor Rao has said something extra to us beyond these talks, especially to the young researchers. Those who are,
just one question. I thought this is a memorial session for late D. Basu, but I see it is a special invited. That's why I had my talk, because I thought I'd do something related to his theorem by which is identified. Otherwise, I could have given my own research, current research, but that's okay.
Okay. that we could understand. Yeah.
This was a memorial session for Dr. Basu, D. Basu.
In fact, the next session is devoted to D. Basu, and thereafter PC Mahalnopis.
Okay.
One of these sessions, yeah. And
I'll
two
talk about
legends in the area are honoring these legends of our great birthdays. Yeah. In fact, several are waiting. In fact, no.
Dr. Malagosh, good evening. This is TJ Rao from India.
Hi, hello, after so many years.
How are you? How are you doing?
I'm doing fine. Where are you now? In, Hyderabad or?
No, I'm in Visakhapatnam, my hometown.
Oh, the hometown.
Yeah, my Hyderabad tenure is over. I was there for about 10 years.
I saw
and then it's now, I think it's a cryptology and cyber technology institute mostly. There aren't many people except for Prakash Rao visits once in a while. BLS Prakash Rao.
Oh, yeah.
Yeah, and SB Rao, I think, is some kind of a emeritus and all that. Otherwise, there are no other statisticians as such.
I mean, where you are or where it is in Hyderabad also? Yeah. Hyderabad, there are quite a few.
BLS Prakash Rao.
Yeah, he is in Hyderabad.
Yeah, he's there. Yeah, he visits once in a while, apparently. Yeah.
He is there.
That's
And who else would be there? B.V. Rao, where is he now? B.V. Rao. Where is he?
BV is in Chennai Mathematical Institute, CMI.
Karandikar is also there.
Karandikar has, I think, finished his term and is going to Calcutta to join one of these cyber technology institutes. I think he will take over as director at Calcutta very soon.
Oh, I see.
Otherwise,
COVID.
In fact, I lost touch with Calcutta. There aren't any that I know. Most of the people retired. So only once in a while I go to NSS, National Sample Survey. And that was in the other building.
That office is still in Calcutta, right?
Yeah.
They had one in Kamak Street, but I don't know whether that exists anymore. There is one post in BT Road, of course.
That's right.
But there is one in Kamak Street also, isn't it? NSS?
Yeah.
There must be another one.
Good. Nice talking to you.
Nice talking to you.
Professor Kalyan, sir, and Professor Sinha also in the group. Professor Vimal Sinha is an.
Vimal is there. Yeah, I can see Vimal. I'll be back in a second. Just a minute. Good morning, Molada. Good morning. Good morning. Now I can. TJ Rao. This is Bimal. How are you, TJ? Bimal Sinha is talking. The TJ is muted. Anyway, okay. Muted? I don't know. Yeah. I think he's muted. Yeah. Yes. That's all right.
Yeah, Professor.
Good morning, Satish. Good evening, Satish.
Yeah, good evening. Good evening, Professor. Yeah, good morning.
Yeah, good morning. Yes.
Good morning, Let us wait for 5 more minutes, Professor. Let us wait for 5 more minutes. 5 minutes. Yeah.
Yeah. No problem. Anytime. Start anytime.
Kalyanam, sir?
Yes, I'm here.
Hello, sir.
It's only at 8 to 8:15 now.
Now, 7:26. We have to start at 7:30, sir.
7:30, 8:15.
The second session. Next session is 8:15. First is 7:30. 7:30 to 8:10.
Am I coming for 7:30 or 8:15?
Sir, 8:15.
I just reached back.
Yeah.
So, it is said that I will be there for 8:15.
Yes, sir. Yeah.
Am I right?
Yes, sir. Yes.
Okay. So I am attending. Just now I came and joined.
Hello, Ashish. How are you? Ashish Sengupta is there.
Professor Ashish. Hi, Professor.
Hello, Ashish.
Hi, Ashish.
Oh, thanks. Hi, sir.
Can you hear me now?
Yes, Professor.
Okay,
Can hear
good.
you.
Yeah, okay. So, good afternoon, everybody. And TJ, I think you could not hear me earlier. My mic was muted.
Okay. Oh, yeah. Earlier,
I could hear you, yeah. So, please don't mind. I could listen to you, I could hear you, but I could not answer because the mic was muted. Molada.
How are you doing, Ashish?
I'm doing fine.
Are you traveling as much now because of COVID? You are always out of India.
No, not this year, not so much this year. But
Not
COVID
so
has
much.
come back. Sort of.
Oh, that's great.
But I'll be traveling. I'll be seeing TJ soon.
Oh,
I'll be meeting a person in this month in Vizag.
Okay, very good.
We have a ISPS conference there.
Okay. What about
Molada, you look great. Molada, you look great. I think fresh and energetic as usual.
I took it. Ashish, and Molada looks great as always and energetic. Yes.
You too.
And Molada is I think, the finest person I have met. Such a wonderful human being. Molada, thank you so much for being a big part of our lives.
Yeah, I think it's a universal statement.
I'm here.
Whosoever I've met who has been acquainted with Maulana, they say the same thing. If you remember,
Yeah.
during his retirement ceremony, there's a felicitation ceremony, and place in Baltimore. People were saying so many things, and no word for him.
I was not retired. That's the thing. Yeah, some people thought it was retirement party, but it was not.
No. That's what I'm saying. It's a celebration program for you.
Alan Kaufman said, "Well, I see you again. I'm not retired."
Maulana doesn't retire.
No, I have not retired. I'm still teaching. I think maybe we should start now.
Yeah, I think it's time to start.
Okay, Satish, yeah. Can someone?
Satish, it's time possible.
Yeah, now it is time. Let us start the program. But the chair has left by the time. That's why I am calling. Jayakumar is given the chair to session.
Okay.
So I'll turn off my camera. The internet is somewhat slow. So please don't mind, okay? I'll just turn off my camera.
He's joining. He's trying to join.
He's trying to join. The chairman?
Yeah, we are given the.
Yeah, that's all right.
Hema? Hema Mallin?
Sir.
Are you ready to introduce the chair? Excellent, isn't it? Okay.
Yes, sir.
Okay. Just a minute. Earlier he was in the group, I think so, but just left. Okay, Hema, you please introduce him and.
Okay, sir. Welcome everyone to Technical Session 39. It is a plenary session chaired by Dr. K Jayakumar, who obtained his PhD in the year 1994, University of Kerala. His areas of research are distribution theory, time series analysis and forecasting, probability theory. He served as the General Secretary and President of Kerala Statistical Association. He has more than 25 years of teaching experience. Currently, he is a Professor and Head of Department of Statistics, University of Calicut. I warmly welcome Professor Jayakumar to chair the session.
Thank you very much. And today we have the speaker, Professor Marrow Ghosh. And let me introduce the speaker. Marrow Ghosh is currently working in University of Florida, and he has, to his credit, he has so many awards and so on. And so the host was a faculty member at the Indian Statistical Institute in 1970s before he joining at Iowa State University. And in 1982, he joined the University of Florida. Ghosh is well known for his research in non-parametric inference, sequential analysis, decision theory, Bayesian statistics, and small area estimation. As a recognition of the seminal contributions of Professor Ghosh, he served from 1996 to 2001 in the United Nations Census Advisory Committee. And he has co-authored 2 books, and he is the author of more than 250 research publications, and he is the advisor of over 40 PhD students. So with great pride, I welcome you, sir, to deliver your talk. Plenary talk. Professor Ghosh, please.
Thank you very much. Can someone put the slides? Please put the slides, and then I can start. And you have to do.
Yeah. Nikhil, he will do, Professor. Yeah, he will share for me. Yeah.
Only it's fine.
In fact, this session is devoted to honor our great legend, Deepasu. And welcome, Professor Ghosh.
Thank you. The slides, please. Who has got the slides? Yeah. Yep. Correct. That's interesting. It's not coming? Something wrong.
Yeah, some technical. It will come. It will.
I tried blank page. It should be there.
He's trying to share it once again.
Yeah. Oh, until the slides come, I can say a couple of things about Professor Basu. And actually, I'm very glad to present something in a session honoring Professor Basu. Professor Basu was a man of vision, by all means, not just a great statistician. He could see the future, really. He started his career, of course, in Dhaka University in a master's in mathematics, came to Calcutta to study actuarial science, but very soon got disillusioned and joined the Indian Statistical Institute. He's the first PhD student of Professor C.R. Rao. And then, of course, he has traveled all over the world, including Berkeley, and I can name a large number of places. So Professor Basu started as a Raymond Pearsonian for many years, but he could see the futility of it also. And he started getting more and more interested in the foundations of statistics, also a Bayesian. Can I do a Control-C to see the whole thing? There is something I'm seeing which is not coming. It's okay. If you can see, that's all right. In fact, in 1971, of course, at that time, Layman's testing of hypothesis was my Bible. I used to teach that all the time, Indian Statistical Institute, and I've taught it even later. And he said, Malloy, a time will come when nobody will teach all this material. That was 1971. And now in 2022, I see most of the departments in the United States, it may not have happened in India, have abandoned completely the testing of hypotheses. They do lots of other things because the problem is it is kind of artificial setup, uniformly most powerful and biased, invariant and all that, give the optimality of F-test, T-test and all that under normality. But real life is much more difficult, and that's what it is. So he was a man of vision, which what he saw in 1971 has materialized now. Now, what I will do today, I will just state and prove even the theorem for which is identified, in case some of you don't know it, possibly most of you know it. But I will show a few of his applications. I wrote a paper a long time ago. When Professor Basu passed away, there was an issue of Sankha, memorial issue in Sankha when I wrote it. And I've taken a few things out of it for today's talk. Next slide, please. So I will first prove the Basu's theorem. I'll show multiple applications. Applications in distribution theory, point estimation, hypothesis testing, and finally, my favorite, empirical Bayes analysis. Of course, Dr. Basu actually got disillusioned with his theorem. I remember, which year was it? 1976. He said it is one of the most useless theorems in statistics. I don't believe so, and I still cherish its value. And there are others who are still using it, believe me. Next slide, please. What the theorem says. All it says, if a statistic is boundedly complete, if it is complete, of course, it is boundedly complete. The converse is not necessarily true, but most examples, it is complete, and U is ancillary. A statistic whose distribution does not depend on any parameter of interest. If they are so, this is Basu's latest version. They are independently distributed conditionally. That's the thing, conditionally, he added in one of his 1982 papers, because at that time he was a Bayesian. And that's why for a given theta, that's why he's saying conditionally on every theta, given theta. You can forget about it if you're a frequentist for every theta. So just write P equal to a probability of U less than equal to U, which does not depend on theta. So it is same as conditional on theta. And now define GT. I'm trying to prove the theorem is the probability of U less than equal to U given T equal to T. T is sufficient. So GT does not depend on any parameter. And I wrote it in terms of the indicator function. So what is the iterated formula of conditional expectation? Expectation of GT is expectation of indicator. Expectation of indicator U less than equal to U, which is probability of U less than equal to U, which is P. And GT is boundedly complete because it is a probability, bounded between 0 and 1. So since the expectation is P, because of the bounded completeness, it is equal to P for all theta. And now take the joint probability of U less than equal to U and T less than equal to T. Again, given theta, you can forget it. As I said, if you're a frequentist, but Basu eventually wrote it that way, which is expectation of GT times indicator T less than equal to T. And then the GT is common, so that indicator is equal to, then probability is equal to P. So P times probability of T less than equal to T, and that is the joint probability for all theta. So that is simple, but so versatile. Let's see some of the applications. Any questions? Please stop me, okay? Anytime, and I have no problem with that. Next slide, please. Thank you. A very simple thing. I could have written in one dimension, but I wrote it just for fun, multi-dimension. I have a bunch of normal distributions, mean vector mu, variance covariance matrix sigma. You can think about mu sigma square, doesn't make any difference. Then I have the Wishart matrix X, S, and the sample mean X bar. For every fixed positive definite sigma, X bar is complete sufficient for mu, and S is ancillary. Why? Because you can write it as xi minus mu minus X bar minus mu. If you write it that way, it is free from mu. It is ancillary. So proves the independence for each mu belonging to the p-dimensional place and each fixed sigma. So just write probability statement, and that will give you independently distributed for all mu and sigma. Of course, there are other ways of proving it. Helmholtz transformation, that's how I learned it. But if only independence is concerned, not the distribution as such, it is possibly the most simple thing to use. Next slide, please. The one important thing is boundedly complete. That is important. I took a logistic distribution. There are some nitty-gritties here. In fact, Basu once proved a converse to this theorem, which is not completely true without some extra conditions, and that was eventually discovered. I'm not getting into that, but I'm trying to emphasize the bounded completeness. Here, the order statistics is minimal sufficient. You cannot do any further reduction of the data, but T is not boundedly complete because you take any bounded function of, say, you can take any two order statistics actually, but if you take the difference, the sample range, it is a constant, non-zero constant, not depending on theta, but it is not equal to. The probability is equal to that constant is not 1, in fact, equal to 0. And in fact, xn minus x1 is ancillary because it is a location parameter, but it is not independent of t. So that is important, this bounded completeness. But interestingly, next slide, please. Interestingly, if you augment the class of all continuous PDFs, then of course it is known, Fraser, Lehman, and others, then indeed T is complete for the whole family, a large family of distributions. And Basu's theorem then asserts doesn't exist any non-constant function of that T which is ancillary. That's exactly what it says. Now the point is, MLE is always a function, not necessarily equal, the minimal sufficient statistic, but need not be sufficient by itself. Think about a uniform theta to 2 theta. The MLE is half of the max. But with the not sufficient, what is minimal sufficient? Augmented ancillary statistic x1 over xn. But the minimal sufficient statistic is not boundedly complete. And the bounded completeness of T actually precludes the existence of such a U. But if it is not, there could be many such functions which are not independent of the complete sufficient statistic. So this is an important thing. You need the bounded completeness. In fact, there are many other examples of this type, but we are not getting into that. There are some interesting applications. Basu himself didn't talk about much of an application, believe me or not, but the people took it. In the 50s, it was Hogue and Craig who actually capitalized on Basu's theorem. Although Hogue didn't want to call it Basu's theorem, that's another story. I had some personal correspondence. And then another person is Herbert David, H.A. David. He also was very, very familiar. But later, other people took over. Almost lots of places, Basu's lemma using this very simple thing. Next slide, please. One interesting application of Basu's theorem, evaluation of moments of ratios. I will show it later also with empirical base. The basic result is if x over y and y, I'm not saying x and y, the ratio, x over y and y are independent, then you can write any moment of this ratio as the ratio of the moments. The proof is very simple. All you have to do, just write y as x over y times y. Okay, they're independent. Take the kth power, and then it is, because they're independent, it is the product, and then that gives it. Any question about it? Very simple theorem. Expectation of the kth moment of the ratio is the ratio of the kth moments, provided, very strong condition, x over y are independent. A simple example, sample mean over sample maximum from a uniform distribution. So what happens? Xn is complete sufficient, we know. X bar over Xn is ancillary. Y, divide all the observations by theta. Then this ratio, X bar over Xn, is independent of theta. Therefore, it is ancillary. So it is X bar over Xn is independent of Xn. So take the ratio. It looks like a very complicated thing, but it is not, because expectation of the ratio is the ratio of the expectation, and that of course cannot depend on theta because it is ancillary, and the calculation becomes trivial. So it is very, very handy thing, and for me, in my empirical Bayes analysis, that has proved to be a great thing. Next slide, please. There is another interesting thing. I learned the joint distribution, I don't know, even now possibly it is taught in undergraduate courses in India. When I was a student, Professor Anil Bhattacharya taught it. Joint distribution means variance and the correlation coefficient from a bivariate distribution. The proof becomes very simple if we can do certain things. The first thing is, so I have a bivariate distribution, means mu1, mu2, variance sigma 1, sigma 2 square, and correlation coefficient rho. So I take the sample means, sample sums of square deviations, and the correlation coefficient. Under the null hypothesis, rho equal to 0, then the rho is 0, becomes two sets of independent. All you have, the means and the variances. That's complete sufficient. And the correlation coefficient now, because rho is known, 0, it is ancillary. This thing does not depend on rho at all. So it is distributed of R when rho is 0. Next slide, please. Thank you. Due to the mutual independence, when rho is 0, the joint PDF of the 5 statistics, the x1, x2, they are all mutually independent all the time when rho is 0. So you take the derived joint PDF of the 5 statistics for any arbitrary rho. And of course, I need to be positive definite. And now I use the factorization theorem of sufficiency to get it for an arbitrary rho. Why? Because look at the likelihood L. If I write the likelihood L, it is a product of this thing, the function of all these statistics, multiplied by some h which does not involve parameters. You take the special case, means is 0, variances are 1, correlation is 0, and then you get the same. You take the ratio, the h disappears, and all you have, this ratio is, I better not get this one, standing in the line, is the ratio of those two Qs. So in one line, you can get the joint distribution of 5 statistics just by from the null distribution, which is a very, very elegant way. Bimal knows more about it. He and I once tried the same trick for the Wishart distribution. We derive the distributions in the case when the variance covariance matrix is identity, min vector is 0, get the Wishart, and then just use the factorization theorem to get the joint distribution when it is the means and variances are arbitrary. Okay, but before that, we use Basu's theorem to get the independence in the null case. Next slide, please. Point estimation. It is a very important example due to Kolmogorov first. x1, x2, xn, the IID normal mu sigma square. Kolmogorov found that uniformly minimum variance. And if you use, I don't know, he would definitely at that time didn't know Basu's theorem, but he got the right answer. The easiest thing is, look at it. Probability of x1 less than equal to x, you can write it as x1 minus x bar over s less than equal to x minus x bar over s, right? And x bar s is complete sufficient, but x1 minus x bar over s is ancillary. So even if what? You condition on x bar over s. But as soon as I write that u less than equal to x minus x bar over s, then u is ancillary, its distribution does not depend on x bar s, so just get directly the distribution of u. So UMVV is just given by that quantity, and marginal PDF is given in RAL 323. I don't know whether he applied Basu's theorem, possibly not, but the result is right. He wrote it in one line, possibly, so whatever. But there is something more to it, a little interesting thing. Next slide, please. It was discovered by Joe Eaton and Carl Morris. They found, suppose you have an unbiased estimator of a parameter theta, a gamma theta, any function of theta, h of x, which is a function of the complete sufficient statistic and the ancillary statistic. Okay, t is complete sufficient for theta, u is ancillary. So UMVV is just given by expectation of WTU just evaluated using the u. Keep the t fixed. EU denoting expectation over the marginal distribution. Here, you use two things, the Basu's theorem and the Rao-Blackwell, Lemon-Shaffer wrote, Rao-Blackwell you can call it. So all it is, what is the UMV? Expectation of H given T, which is WTU given T. And T, since the distribution of U does not depend on T, it is independent. Now Basu's theorem, so it becomes W of little tu given T, and then all you have to do, compute it, because U is independent of T, just compute its expectation with respect to W T, little t U, over the, and you get gamma star T. Kolmogorov is an example of that. And I will give you another example right now. Kolmogorov, another example, because what was U? X1 minus X bar over S. What was T? Just X bar and S. And you eventually find the expectation with respectation X1 minus X bar over S. Next slide, please. Another example I have given, please. X1, X2, Xn, independent IID, common Weibull. Now, here, of course, I try something similar to Kolmogorov. Summation xi to the power p, complete sufficient, and U is x1 over p to the power p over summation xi to the power p is ancillary, and I try to get exactly the same way. Is UMV is given by expectation of U x to the power p over t, and this x1, x2, etc. exponential with scale parameter theta. Simple thing, U is beta, 1n minus 1, and just use the beta distribution. You have to be a little bit careful because U has to be between 0 and 1. So if t is smaller than x to the power p, it is 0, it is 1. Less than equal to something bigger than 1, then it is 1. Otherwise, just use the beta distribution to get it. So these are point estimation. I will try the Hogan-Craig example. Next slide, please. Oh, no, there is another interesting thing. Monte Carlo swindle. It was a paper by actually Johnston and Wellman. Normal distribution, you want to estimate the variance of the median. You do not get a closed form. You use numerical integration. But what they found that it requires a much smaller sample size, Monte Carlo sample size, to attain the prescribed accuracy. If instead you get a Monte Carlo estimate of variance of m minus x bar, and then add the usual estimate of sigma squared by n, say square by n, whatever it is. Why? For every fixed sigma square, x bar is completely sufficient, and median minus mean is ancillary because you subtract of the mu. It is location invariant. And therefore, variance of n is variance of m minus x bar plus variance of x bar, which is giving you that formula. And they also, here also comes Basu's theorem, actually. Very simple, but very useful. Next slide, please. Now comes Hogan-Craig. They really made their career in the 50s. And let us take I could have started with just a rectangular distribution, which would have been possibly simpler, but they took a very general one, which includes the rectangular. For example, if little h is 1 and capital H is just theta I, or what is it? It is uniform 0 to theta. You can have power series distribution. You can have, for example, k times x to the power k minus 1 and theta to the power k, correct? 0 is less than equal to x, less than equal to theta. So HU is the distribution function, and that's the form of the density, all these forms, and because if you integrate out 0 to theta, it is 0 to u, it is h of u. So we're testing the null hypothesis. All the thetas are equal against the alternative, not all of them are equal. And I give the notation xi for all the ith component elements, and x, the overall thing. Next slide, please. So I'm taking the Ti, which is the unrestricted MLE of the thetas, and T is the maximum of the maximums, MLE of the common theta under H0. I can always define it anyway, but it becomes the MLE of the common theta under H0. So the generalized likelihood test statistics takes this particular form. If, as I said, if you're uniform, then it would have been very simple. Product Ti over T to the power n. So take the minus twice log lambda. It is given in this particular form. Just you take the ratio and then the log, and it takes that form. So under the null action, so the T's are always independent because we are using the fact if Z has a continuous distribution, say capital F or capital whatever distribution function, f of capital Z is distributed uniform 0, 1. And that's why the T's are independent with that distribution function. So under the null, it is H and Ti, H and theta are uniform 0, 1. Next slide, please. Accordingly, under H0, this distribution use the fact if x is independent, uniform 0, 1 minus 2 log x is chi2 square. So you have a bunch of independent chi2 square. Sum is chi2k square. The interesting thing is under H0, the distribution function of T is given by that. It is uniform 0, 1 under H0. So under H0, it is a chi square with 2 degrees of freedom. Now comes the interesting thing. You write the minus twice this thing as minus twice log lambda plus minus twice. The two components in the right-hand side are independent. Why? Because T is complete sufficient, where lambda is ancillary only under H0, not under the alternatives. Alternatives for power, you have to do other calculations, but under the null, it is ancillary. So now you use the fact there are two chi square. If W1 and W2 are independent, W1 is chi square, the sum is also a chi square, then just use the moment generating function technique. The other component has to be a chi square with degrees of freedom subtracted. Very simple result. And you use that minus twice log lambda. What did I use? The Basu's theorem again, and so did Hogue and Craig. And they have multiple papers. I think they have at least 4 papers in the late 50s, maybe even 60, using Basu's theorem. Although Hogue had some concern. He once told me he got the theorem for the exponential family distribution earlier, but his paper was rejected. Basu's was definitely more general, and they published Basu's result, apparently. And that's the story. And for a long time, he did not call it Basu's theorem. And it was only in the later stage of his life, he started calling it Basu's theorem. In fact, when I was in Florida, he came once and gave a lecture. The whole lecture was Basu's theorem. That was the title. Next slide, please. This is another interesting, and very quickly gloss over it. Hogue and Randall's. They took the situation for non-parametric setup. Order statistics are complete sufficient for IID sample. The ranks are permutation invariant. They take the value 1 over factorial n. It's because they're IID and does not depend on the distribution of x. Therefore, it is ancillary. So use the independence of the order statistics and the rank statistics, and that helped them get a whole bunch of results. My final set of slides, and that's what I'm most interested, empirical base. Let us say a little bit about it. Next slide, please. Very simple model. Really, the whole thing started with Stein. He did never care to give the empirical base interpretation. It all came from Ephron and Morris, and Ephron and Morris I counted. They wrote exactly 12 papers out of this kind of thing and its generalization. So xi over theta is normal theta I1. independent normal mu. Theta is an independent normal mu tau squared. Bayesian formulation. Look at it as x given theta, normal theta IP. Theta is normal mu 1p tau square. Take the posterior. The posterior is normal. The mean is a weighted average of the sample mean and the prior mean. You can see that. And B is 1 plus tau square inverse. So if tau square is very large, the prior variance is very large, B is going to 0. It shrinks towards the sample mean. If tau square is quite small, B is tending to 1, it is shrinking towards the prior mean. So posterior mean is a weighted average. The empirical Bayes interpretation, which came from Efron and Morris, the mu and tau square are unknown, so estimated from the marginal. Marginal here doesn't mean component-wise marginal. It means the distribution of x after integrating out theta. And what is it? It is very simple. Look at it. X given theta, normal theta. Theta is normal mu, so the means are added up. Expectation of x is mu 1p, correct? Which is expectation of theta. Variance of x, just all you have to do, 1 plus tau square IP, and that thing, you can write it as B inverse in view of my notation. So marginally, look at it. There is no theta, x bar, and S are complete sufficient. So use the UMV. Why UMV? You can use MLE also. For mean, it is x bar still. B hat, it is different. But it is, they had a good reason because that gives you the James-Stein thing. So P hat is P minus 3 over S. You need P at least 4. Otherwise, the whole thing, the reciprocal, has infinite expectations. So X bar is given by this. S is B inverse. EB estimator is B hat X bar 1P. That's the estimate. How to compute this Bayes risk? And it has some important thing. Next slide, please. I have used quite a few. Bayes risk is given by expectation of the joint distribution of x and theta, which you calculate what this is the trick. And the trick works for normal. Doesn't work all the time. But for normal, this is a great trick. Subtract of the Bayes and add the Bayes. And then the product term vanishes. So the first term becomes theta b hat minus theta b hat minus theta transpose. The next one is given by that. Why the product term vanishes? Just take any one of the terms, condition on given x, then the theta hat EB minus theta hat B is a statistic, it is constant. Expectation of theta given x is theta hat B, and that makes the product term equal to 0. So for normal, in order to find the joint expectation of the product, rather than conditioning on theta first condition on x. And that holds true for any estimate. Believe me or not, it is a great thing. The idea is very simple because the Bayes estimate is the projection of the parameter using it as a random variable on the sample space. Now, Basu's theorem will come. Next slide, please. The first term is very easy. I can just calculate it, expectation, and again, condition on x first, it becomes 1 minus IP. The next one is very easy. Theta hat B, I wrote it in that way. And due to the independence of x bar and x minus x bar, again, Basu's theorem again, expectation of x bar equal to mu, there is more of Basu's theorem. You compute it as from the first term and the second term, again, the product term equals to 0. The first term is very easy. I calculated it. And I just remind you, B hat is P minus 3 over that sum. Next slide, please. Writing x minus x bar, that thing is W. This is given by this. That's just a writing. Now, S is a function of the complete sufficient statistic where W over S is ancillary. Apply Basu's theorem. So first thing is expectation of W. It is simple to calculate right from the beginning. I calculated B square expectation of W, no Basu's theorem as yet. Next one, I told you the ratio. You can get it other ways also, this one, but then the final one is great. So expectation of W is expectation of W given S multiplied by S, which is expectation of W given over S times expectation of S. So now all you have to take the ratio, you get it immediately. The next one is even better. W over S squared. W over S squared, I'm writing as W over S times 1 over S. Now, again, W over S is ancillary. S is complete sufficient. I get that particular form, and combining all the terms, I get this particular result. So what it says, in terms of the Bayes risk, the empirical Bayes, the matrix risk of the empirical Bayes estimator is smaller than the risk of the classical estimator. And it has some, my last slide, interesting consequences. Next slide, please. Now consider the quadratic loss, where Q is a non-negative definite matrix. Now a scalar is equal to the trace of the scalar. I wrote it alternately as trace of Q, A minus theta transpose. And by virtue of the previous result, we know that that is less than trace of Q, or expectation. So now take one of the elements of Q, that one diagonal element, 1, is non-negative definite, rest all zeros. What you get? The ith coordinate of the empirical Bayes, the mean squared error of the ith component of the empirical Bayes estimator is less than the ith component of X bar. It is stronger than Stein's result. Stein's result only says that if you take the squared error loss, sum of squares, then only you can beat the classical estimator, which is P. It does not provide component-wise dominance. But Efron and Morris could show that the component, they did not prove it that way, by the way. But anyway, it doesn't matter. This component-wise dominance is achieved by taking joint expectation of X and theta. So in that way, if instead of the frequentist risk, which is conditional on theta, you cannot get component-wise dominance, if you take the Bayes risk, you get component-wise dominance of everything. Thank you very much. I really appreciate your time. And if there is any question, I'll be very happy to answer. Thank you again. Thanks for putting the slides for me. Otherwise, I would have
Thank you, Professor. Thank you very much. Any questions or comments?
Molada, I'd like to make 2 comments.
Pardon?
I'd like to make 2 comments. Okay. On the very last slide, I think this follows because of the IID nature of the original setup.
Last slide, you were saying.
Yeah, this particular result, component-wise dominance, follows essentially due to the IID nature. From the very beginning, we have very nice IID setup.
Right.
Music, square, everything kind of.
Right.
And symmetric and all that. So that's what we expect. That no component should be otherwise. It should be component-wise. Probably that is expected.
What they wanted to, actually there is more to it, right? Because Q, you can take all sorts of non-negative definite matrices. You can get Efron Morris possibly tried to emphasize only this special case.
Yes.
They are saying, I mean, their point of view was Stein's procedure does not provide component-wise dominance. But what you were saying is right, because you are now essentially going to the marginals in some sense.
That's right. Yeah.
In order to get the result for the marginals,
right?
I prove it. They proved it in a very different way. They make a They can do it, I'm sure. Make a transformation for the non-negative definite matrix and all that. But I think a more elegant proof is Basu's theorem, which I many years ago. I love it because I love Basu's theorem, and therefore I gave it. So that is one comment. What is your second comment? You're right.
The second point is, when I was at the University of Pittsburgh, I believe that was 1982. So Basu came to visit Pittsburgh, And of course, it was a great view to see Guru Shishya together, Shiyada and Vibhasu together, And then Pranav invited Vibhasu to be the interviewer. And the whole group, the audience, all state faculty, most of them are Indians, and probably all the graduate students are Indian too, not to say Indian people. The doctor mentioned to Basu that Basu, you can speak Bengali or Hindi. English is not necessary. And the title of Basu's talk was Independence Without Tears.
Independence without tears.
Yes, that's right.
That's exactly right. I find it so much useful. Several years ago, that's my personal anecdotal story. I was working with Dr. Kubokawa of University of Tokyo, and he was proving a result, and he took a long proof of one particular result. It was about a 7-page proof, if I recall correctly. If you apply Basu's theorem, the whole thing, it will turn out in a 2-page proof. And lots of those actually I have used over the years, where it is so easy to prove things. Independence without tears. Right.
This is something similar to what appeared in the Giri, Kipper and Stein's papers. University of all the very long papers in the Annals of Mathematical Statistics, AMS, in the 60s. Right?
Identify some of the proofs you think?
Yes, and of course, by applying this representation theorem, then you can simplify the problem. 10 pages, just 1 page. Wise one representation theorem.
I'm sure you're the expert there. I love to see.
Yes, I did a lot of work on that also. Same idea. You can apply Basu's theorem to simplify things. They are also something very, very interesting.
Right.
Thank you. It's a great talk. Thank you. Most so wonderful to listen to.
I love to hear it. Thank you very much. And I'm waiting for TJ's talk.
Yes.
All others.
Ashish, you want to say something?
I just make a quick comment, Maulana. This Basu's theorem, we had some occasions, in fact, to apply it to circular statistics, going away from the linear ones. So, if you look at the curved exponential family, the standard example is our circular normal distribution or the von Mises distribution. So if the kappa is known, it becomes a curved exponential family. And in that case, we want to derive a test for the mu parameter, mean direction. I found Basu's theorem very, very handy. So I obtained the test using the conditioning on the ancillary. And it so happened that Professor D.R. Cox was there, was visiting ISI, you had some discussions. So I showed the work, we discussed about it. And because it's a conditional test, I had little reservation, so I went into the more standard ones like the, let's say, the scored function or the locally most powerful test. Now, here's one thing I still remember. Professor Cox told me, or wrote to me rather, that Ashish, the conditional test can be really good. It's not so bad, even though you are thinking of conditioning on the ancillary, and the locally most powerful are the score statistics and conditional test. The ancillary condition on the ancillary, the test can be performing quite well. So I just want to have your comments on that. Any thoughts on that?
No, that is perfectly right. Because even Fisher, long time ago, when he was basically talking about, so when, say for example, the MLE itself is not minimal sufficient, he advocated do inference based on the conditional distribution of the MLE given an ancillary statistic. That was Fisher's recommendation many, many years ago. So Cox, of course, is a Fisherian. He loved it, I'm sure.
So it was in the direction of using Basu's theorem. So our test was based on the conditional distribution of the complete sufficient statistics condition on the ancillary.
There
That's
are
how we got that.
examples when you talk about, I don't want to get into that, although in my paper I talked about uniformly most powerful unbiased test. The derivation becomes so powerful when you use condition Basu's theorem. That is another. My paper, if it appeared, I don't know, early 2000 after Dr. Basu's passing away. Anirban Dasgupta was the guest editor of Truncated at the time. There are multiple examples, multiple illustrations, and there are some deeper things, especially regarding the converse of Basu's theorem, how to settle that, how to make it work, how to get it right. So that is another thing. So if anyone is interested, feel free to look at it. And in fact, I have a PDF file. So if you are interested, I can even send you the PDF file.
Okay, sure, I'll write to you about it.
Many years ago. But this is
what I'm trying to tell you, that this Basu's theorem is getting, I think we're getting more and more used in our circular statistics and directional statistics.
Maybe somebody now can enlarge the paper by including those examples. Bimal, you said something very interesting. Ashish, you said also something equally interesting. So maybe now new examples can be added to my list,
right.
Which would be great, actually. Very good. Thank you.
Thank you, Malana.
Most welcome. No, I think I'm taking Dr. PJ's time. Let him get into
You forgotten the time, in fact. Really interesting and fantastic talk, Professor. We would like to thank Professor Malekos for your very wonderful presentation of these concepts, and above all, reminding our memory to the great legend, the Basu. Thank you so much. We're a little bit late, but that do not affect our Professor Ravu's talk. We will have once again thanking you, Professor Ghosh, and the chair, Professor Jayakumar, for nicely managing the session. And once again thanking you. Let us move to the next session. We invite Kalyanaman sir to chair the session, and Professor, we are waiting to hear and see Professor Ravu's about our Mahalavis. I think Anjana, please introduce the chair, and please do the needful for the presentation.
So good morning, good afternoon, and good evening to all our participants from around the world. We have reached the last technical session of Wsta 2022, and one that is of paramount importance indeed. This plenary session shall be chaired by our Emeritus Professor K Jayakumar sir of Department of Statistics, University of Kerala. He has over 4 decades of professional experience in academics, consultancy, as well as research, and is a regular invitee to academic staff colleges in the area of quantitative methods, research methodology, and analytics. Professor Kalyana has published a number of research papers on theoretical and applied statistics in various national and international journals, and has been associated with the analysis of more than 1,000 PhD theses in various disciplines. He is an elected fellow of the Kerala Academy of Sciences and an esteemed member of the Wsta 2022 Advisory Committee. With great pleasure and honor, I invite Professor Kalyana sir to chair the session. Over to you, sir.
Please unmute your mic, sir. Please unmute.
Thank you, my child, for a nice introduction. And I'm very happy to be part of this seminar. Generally, I used to be attending all the sessions, but due to some personal requirements, I could not do, and I just rushed back to at least attend the last session. And I thank Dr. Satish for providing this opportunity for me to be part of the seminar. And they have been working for the last 4 days in a very tremendous manner. I know that. Right from morning 9 o'clock to night about 10 o'clock. You cannot imagine the kind of work that the children have put forward. And we should all appreciate that to the extent as elders, just to guide them and bless them for successful completion of this and the ensuing programs that we expect out of this department. I'm only very happy to chair this session with Professor Talluri Jagannath Rao. Am I correct? I think I remember that name, TJ Rao, who is ISI person, and he did his PhD in ISI, if I remember correctly. And also I remember that he was working in related problems. If these are all general observation when I was in service. It was about 20 years back, and I think that he was associated with the journals. I think he was an editor in some category as far as Sankhya for some time, and I only wish that the session on which he will be talking about remembering Mahalanobis Waves, a wonderful session. We all should be looking forward, because he might have personal experiences with PC Mahalanobis, which he will be able to share with us, which will definitely be a very important matter as far as statisticians are concerned. At this point, I would like to just remember that the first issue of Sankhya, second issue of, I don't remember, there was a paper published why the name Sankhya was included, as is coined as a name for the celebrated say journal, and taking the cue from that, one of my colleagues, late Professor TKS Unnitan, had brought out similarities between Sankhyan system of philosophy and the statistical methodology. And this is only for information.
Yeah, Professor Rao, please unmute your mic.
Professor Rao, you unmute your mic. Somebody can do it from here?
No, I don't think.
He can do it. Yeah. Professor
Rao, can you unmute?
I think he's trying. He's trying to do that.
Yeah.
Okay. Now it is fine.
Am I clear?
Yes.
Yes.
You can hear me?
Yeah, now
you can hear me?
Now yes.
Okay. Yeah. Thank you very much, Professor Kalyararaman. And this is the closing session in memory of Professor Prashanta Chandra Mahalanobis. And I will take you in the next 50 minutes through remembering his achievements, his innovative ideas, and so on, and his connection with the National Statistics Day, because this is the celebrations we are having for the last 4 days. And I'm sure that most of you are very much tired with lots of mathematics and statistics and so on for the last 39 sessions. So this is the 40th session. This is a bit light, and there is no mathematics in that. So we'll try to remember Mahalanobis, about his work, his achievements, and why he is called the father of statistics in India, and remember him through his work. I'll start once the slides are presented. Thank you. Should be towards the human welfare. This is the 16th Statistics Day that we are celebrating, and also the 129th birthday anniversary of Mahalanobis. I'll call PCM hereafter. PCM, as we all know, is the chief architect of post-independent statistical system in India, pioneering statistician, founder of the ISI, and Sankhya, a world-famous statistical journal. Just now, our chairman mentioned that. And he's well known for his concept of Mahlanabis distance, and so on and so on and so on. So I don't have to tell you people because we all know that thing. Next one, please. Statistics Day in some other countries. Africa started their Statistics Day on 18th November since 1990 with PCM as the chairman. Who are the other members of the NIC, the National Income Committee? The other ones are Dr. Godgill, who is an economist, and the other person is V.K.R. Rao, who is a champion in national income. On the 18th December 1949, Prime Minister, the then Prime Minister Nehru, decided that a sample survey should be there to get data because there is no data, there's a lot of gaps when this NIC started sitting and trying to get something done. So look at the date here. 18th December, Jawaharlal Nehru wanted something to be done. And within 1 week, 25th December, PCM comes with his expertise on large-scale sample surveys at ISI. He quickly prepares an abstract scheme for conducting a national sample survey for the whole country. It was approved by the government in 1950. And on the 10th March 1950, NIC recommended the use of sampling techniques to fulfill the gaps in the information. Next one. Around the same time, at ISI in Calcutta and Gokhale Institute of Politics and Economics in Pune, they were both conducting socio-economic surveys under the directions, as I already mentioned, under PCM at ISI and Dr. Godgill at Gokhale Institute. Thus, the government wanted that both these institutes should come into play, and they wanted Calcutta Institute, ISI, and the Pune Institute to entrust with the data collection. Data collection for the first round of national sample thus started in October 1950 for rural India. Next one. As you can see, after the first round of the NSS was completed, a report on the Pune schedules of the NSS was made available. Now, what do you see of this from this report? There was a conflict between Godgill, one of the members, and Mahlanabis, who is the chairman. Godgill doubted whether information can readily be obtained in India by a random survey because he's an economist, and at that time, it's not very well known. But Mahlanabis wouldn't agree with Godgill's doubts. Next one. Mahlanabis claims that a large-scale survey, like all large-scale reproduction in a factory, that requires a period of breaking in, and therefore the first round can never be looked upon as a definitely inquiry by itself. And then he went on, there was a discussion between both of them, exchange of letters, and then finally he said, I have experience of large-scale surveys. I find that NSS is functioning better than what I had expected. Thus, PCM got his way. And then, in fact, it's for his work in sample survey that he got an FRS in 1946, as most of us know. Next one. Indeed, it's PCM's tenacity which has given us the statistics world, the 72-year-old well-acclaimed phenomenon, which is called now NSS, National Sample Survey, and its data is being used for promotion of better lives through the policy decisions and research projects of government of India and other institutions. Actually, we all know that Economic Nobel 2015 was on the data based on consumption of NSS. It's given to Deaton and Deaton. And there was a big paper on that about the poverty debate. And then the welfare economics based on NSS data again gave Amartya Sen a Nobel Prize. And the Nobel of Abhijit Banerjee is also based on poverty data. So all these Nobel winners used the NSS data, and it's such an important area. Next one. The surveys greatly helped the government to introduce various reforms for the betterment of society and human welfare. As always, Mahlanabis insisted human welfare is his keyword. Next one. PCM also was responsible for creation of the Central Statistical Organization. On one hand, it is the National Sample Survey, and then there's an organization at the center, which he called the Central Statistical Organization. Then he gave a model for the second 5-year plan, because the first 5-year plan started in 50 was agricultural plan, but there is no industry, much industry in that thing. Therefore, he thought that there should be industrialization, and he thought the second 5-year plan in 54, which ISA was interested, and they prepared the draft for that thing. Not only he was satisfied with just the 5-year plans, he also plans ahead and then thought what is known as the perspective planning division, and he started that also in the mid-50s. Not only that, he thought that there should be education for all the neighboring countries. So he thought there should be an International Statistical Education Center, which is started in 1950. In fact, I headed it for a couple of years and had the privilege of working with the center. Next one. Now, PCM was interested in crop surveys because there was a gentleman, a civil servant called Habak, who was trying to throw some experimental circular cuts and trying to estimate the yields in Bihar and East Bengal. Then PCM started that this idea is quite good and he wanted to apply that. So he started his Jute survey in Bengal in the 1940s and he came up with the results. What did he do? He collected the whole area step by step, and then he got the estimates for based on his sample survey at 7540 bales. Look at the numbers. He employed 600 to 700 employees and he spent 8 lakhs of rupees as money. The government of India doesn't agree with this thing, so they did a complete enumeration as opposed to sample survey to satisfy themselves. They got an answer 6304 bales. They employed 33,000 employees and they spent 82 lakhs of rupees. Who is correct? Is it Mahalora BC's figure which is correct, or the government of India sent complete enumeration is correct? Then we go to a third referee. Here the third referee is the customs and trade figures. Jute is something which we do not eat and nobody will consume that thing. It is to be made out of gunny bags and etc. Made out of that. And at that time we didn't have many factories in India, in West Bengal and maybe towards Gujarat, Mumbai and so on. So they sent all these things to Liverpool and Manchester, and therefore the customs and trade figures are there. And a little bit is left for internal consumption. So total added up to 7562 bales. What will be the bales? Let's not worry about that. Now look at the figures. Mahalana is 7540, real figures 7562, whereas complete enumeration is minus 16.6% underestimate. Whereas PCM's figure is minus 0.3%. So this convinced worldwide that a crop survey can be conducted to estimate the area and then yield of the particular crop. Next one. At the same time, when PCM was conducting surveys in this area, P.V. Shukhatme, a well-known statistician, he was looking at the inquiry committee report on Bengal famine. He was much disturbed by that, and he also wanted to do crop production statistics in ICAR, Imperial Council for Agricultural Research Statistics. So he also conducted, but as opposed to Mahalodabis, where he was using a circular cut, he was using a rectangular cut, 33 feet divided by 16.5 feet. And then he criticized the Mahalodabis' small plots. He thought that the circular plots would give biases. Therefore, one should do a larger one like 33 by 16.5. Professor B.B. Adhikari, who was the director, he explained this based on the sociology of science in the sense that one comes from the Maharashtra area, which has got one kind of a tradition, and one's from the West Bengal area, which has got the British system and so on. Therefore, Adhikari's solution was that sociological side, and also Planning Commission did lots of surveys comparing these two, and then they found that it's not really the size of the plot, but the errors committed by the investigator. In the round plot, you make a mistake in looking at the yield, whether the crop is inside or outside, and same thing happens to the other one in the rectangular sides. So anyway, they found that there's not much of a difference between these two cuts and so on. In fact, there's a random sample revolution in India was the title of a seminar in LSE, London School of Economics, recently a few years back. So that was so popular about this crop surveys of India. Next. Now, let's look at PCM's views on statistics versus mathematics. What is statistics? In what way is it different from mathematics? This is the question he always asked. Ramanujan and others, they have theory of numbers. Mahalanobis and Ramanujan were together at that in England, and therefore they were friends. You know the stories about that. And Mahalanobis used to say, one side you have theory of numbers, and we practice numbers. Statistical thinking is practice of numbers. That is the statistical thinking. Next one. Let's look at this example to illustrate why Mahalanobis is thinking like that. There's a lawn in the shape of a right angle triangle with sides 3 units and 4 units in the front of a house. The owner wants to erect a fence on the hypotenuse side, and the charges are 100 rupees per unit. He wants to know an estimate of cost involved. He wants to have it on the hypotenuse side. Neither he nor his wife, they knew Pythagoras theorem. So they had to go to their son who is in class 9 and they ask him, here is a question for you in geometry. Next one. 3, 4, that is the diagonal, that is the hypotenuse. What is x? Find x, they asked him. Then his answer was as follows. He's in 9th class, remember. Next one. He says, here it is, x is here. He found x, so he said that is the answer. They were not satisfied with this answer, even though he's in 9th class. At that level, at the 9th class level, he should have used the following argument. Next one. Sum of two sides is greater than the third side. 4 plus 3 is greater than x, which is greater than 4, 3. And x does not seem to be twice 3. Therefore, x should be between 6 and 4. And you know that you have got the bounds. That is good enough. Next one. Mahalan is used to remark, based on this kind of a thing, that mathematicians say if P then Q, while statisticians say if P then approximately Q. Sometimes it is enough to know bounds for the third side, and we need not know Pythagoras theorem at all. So that is the approximately getting the answer. Drawing valid conclusions from data in the face of uncertainty is the basic idea of statistics, as we all know. Next one. Mahalanobis, Fisher, CRO, they all advocated cross-examination of the data. They never thought that we should use data whenever it is available, in whatever way it's available, take it and then use it. That's not the way we should use it. In fact, there is big gaps in the big data and so on. Without cleaning that, one should not do any analysis based on that. I'll give you a simple example to understand. Consider the following example. Ages of 10 employees in a Kerala government department are noted as blah, 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 blah. There are 10 numbers here, and what's the average? Everybody knows that the average is sum divided by 10. Here the sum happens to be, if there is anybody who quickly added them, I would tell them that it's 430. So what is the mean? Next slide, it is 43. But let's go back for a minute. Go back to the slide. Is 43 correct? Back, please, if possible. Yeah, please, thank you. So let us look at this data. 26, 41, 49, 16. Is it a 16 in Kerala government? And is it a 73 in Kerala government? Definitely not. Therefore, as a statistician, a good statistician, you look at the data, you cross-examine the data, you correct it, you remove 16 and 73, get a corrected error, corrected mean, and then plus divided by 8 would be the answer, one of the answers suggested. And you go back and ask them, why did you copy like this? What is the answer? Is it correct or not? And so on, and get the correct figure. So that is the cross-examination of the data. And Mahalanobis did cross-examination of one of the civil servant, Risley's anthropometric data, where he found lots of errors, and then corrected all those errors and published in Sankhya, volume 1. And Fisher said that was one of the best papers in statistics based on cross-examination of the data. So we all know the importance of cross-examination of the data. Next one. I'll continue with some more examples. Now, this is up, next, back please. Yeah, this example is very interesting. It's not the actual example. Look at the data. There are 30 points here, 9.0, 8.4, etc., etc., etc. I have translated the problem so that we all could understand, the present generation could understand. It's actually a problem which Professor Riar got in 1945 when I was doing the anthropometric survey of Bengal anthropometric survey 1945. If I start telling that, it will be very difficult to understand his problem. So I have translated that so that we can easily understand that. Look at the data and let's try to comment on that thing. The first thing, as a statistician, you all look and say, all our first year students will say, well, everything is less than 10. Agreed. And then I want to find the average. How do I find? I just add up and then divided by 30. That is the answer. Okay. And is it correct? I now request my young friends to have a look at the data more carefully and then see that. Let us look at the point here. What is the point here? 0, 4, 5, 5, 5, 5. Do you find a 6? No. Do you find a 7? No. 8? No. 9? No. So all these things doesn't have a 6, 7, etc. So what are these actually? Some of the youngsters in the audience who are cricketers will immediately say these are the overs bowled done models, several planning models, and so on. Mahalanobis' acquaintance with economics was neither systematic nor complete. The economics he learned was connected to problems he had to solve. That is one of our professors, Pony Mukherjee, an economist, which mentioned about his ideas and so on. Next one. Let us conclude by saying that Maulana was the chief architect of the Indian statistical system. He gave us the NSS, Indian Statistical Institute, which is regarded as a mighty monument of his handicraft. Thus, it's no wonder that a National Statistics Day is observed on his birthday, that is 2 days back. An international prize as well as a national award is instituted in his name. The building is named after him. A postage stamp and a first date cover is released, and so on and so forth. The list goes on. So there's no wonder that his birthday should be celebrated as Statistics Day. Next one. The United Nations Statistical Commission, in its resolution of the 17th session in 1972, condoled the death of Maulana Bis, remembering his pioneering efforts on behalf of social statistics, remembering him as a champion of statistical needs of the developing countries, and remembering the outstanding stimulus he gave to the statistical development throughout the entire world. It is much true indeed and well deserved. Next one. Now, next one. We conclude with Professor C.R. Rao's remark that above all, he left us an example of life filled with love, devotion, duty to mankind, and a life dedicated to action with knowledge and activity with achievement. It's up to us to work as he did, preserve what he left, and continue his unfinished task and bring glory to the country. That's what Professor C.R. Rao said. Next one. Now, next one. It's now the age of big data, IoT, AI, ML, etc., etc. And looking at the big data or IoT or playing with the AI alone is not enough. Big data, IoT themselves do not make better lives. Big data need not be better data. IoT has its own problems. Privacy of individuals has to be guarded. And all these cyber hacking and so on, that should be very much there, and it should guard all those things. So it is the better data, better understanding of concepts, better use of statistics arising out of these that leads to a better human welfare, which always Maulana Bis wanted. Thank you very much. Next one. Thank you for your attention. Happy Statistics Day celebrations. And I would like to thank Professor Satish Kumar for inviting me, and Professor Bimal Sinha also for suggesting this. Thank you very much. Thank you. Good night, India.
Thank you, sir, for a very scintillating lecture that makes remembrance of Professor P.C. Maulana Bis in high, with a lot of respects. And after hearing your lecture, I see lot of similarities between the works of P.C. Maulana Bis at the national level and Professor U. Shivaraman Nair at the Travancore level. That is pre-independence days. Before the start of the University of Kerala, there was a central research institute in which Professor U.S. Nair was handling the issues associated with statistics. And whatever that you have explained here, I could see all of them being done by U. Shivaraman Nair at the Travancore level. Perhaps that is what it makes Kerala to score 75 nowadays in the current evaluation procedures. Anyhow, it is a very scintillating exercise that you said. I thank you on behalf of all the participants, and I now invite participants for any questions and comments and the like. Field is open to participants.
Thank you.
Yes.
Thank you.
Thank you. I just want to add one thing also. Maulana Bis made his contribution. Nowadays, we talk about bootstrap and other things, the resampling scheme. And I think the first resampling was introduced by Professor P.C. Maulana Bis. There is a very interesting article by Peter Hall, you'll be surprised, the probabilist, where he brought out all the contributions which Maulana Bis made on resampling. The paper actually talks about resampling, and he is the one who brought to our attention all the contributions of Maulana Bis to resampling. It is a fantastic thing. Maulana Bis realized its importance even in the 40s, which in the 80s became popular as brute square.
Thank you.
Any further comments or questions?
Yeah, TJ, I want to make one comment.
Yes.
You talked about this cross-examination of data. So I found Dr. Rao at the University of Pittsburgh, as theoretical as he was, he spent an enormous amount of time looking at the data. Every PhD student who worked under him, of course, the work will be theoretical combined with some applications. And whenever there's any data set involved, he always advised, even me also, we don't rush to analyze the data. We must spend a lot of time trying to figure out what are the some pitfalls of data collection also. Make sure that the design was well planned and the analysis before the analysis. A lot of money on the data collection process. Make sure the data is correct. So now all throughout his life, he emphasized perhaps he learned from Marrow that to look at the data and critically examine the data before you do the analysis.
Yes. Any further comments? There is no further comments. I would like to wind up this session with a small anecdote, because you just mentioned about crop cutting experiments, and immediately after completing my post-graduation, I was in my village. We are raising paddy in that. One particular harvest time, my uncle said, "You have studied statistics, why don't you estimate it?" Then I put some kind of crop cutting ideas and estimated the output. Possibly the next day was the harvest. And my uncle went around that particular field once and he made an estimate. And I would be very happy to inform that his estimate was a better estimate compared to what I did with statistics. So that's a kind of experience is something more than what we do with data and the collection of data and all that. Unless we do it without what you call cleaning and all that, naturally that will result in very bad results. So thank you very much, sir, for a very nice session and interaction. Now I wish the conference to end with a happy note, and I wish Satish and his team for the best efforts that they have taken, and I would like them to continue this work for many more years to come. Thank you. I hand over the mic to Dr. Satish. Satish, yes.
Hi, Professor. Very wonderful talk. I'm remembering Professor Mahalobis. In fact, everyone really enjoyed and motivated the mainstays, in fact, through this informative talk by our teacher. Now let us
just a minute. Satish, there are few people who have raised their hands.
Yeah, okay.
Naga Swapna. No, is it request? Naga Swapna? Is there anything that you have to ask? No, I think that the raised hand is gone. So you continue. Yes. Satish, continue.
Yeah. Okay. On behalf of the Department of Statistics, University of Kerala. we would like to extend our deep sense of gratitude to Professor T.J. Rao for your wonderful talk, and also to our Professor Raman sir for chairing this session. Let us conclude this session. And now let us move to a brief valedictory and normal. Okay, stop share.
Hello?
Please mute those who are not sending.
Hello?
Professor Ilangavan, please mute your mic.
Hello? Hello? Thank you very much, bro.
Yeah. Just a minute. We have to just a brief valedictory. Yeah. In fact, we have planning, and in which we have to announce the results of a national level online quiz competition we have conducted in honor of Professor P.C. Mahalnabis. So the results of that we have to announce. Dr. Shubham, please let us start the valedictory. Okay?
Yes, sir. Yes, sir. So, good evening, everyone. We have reached the end of our webinar international series, and we have had a wonderful time having all of you with us. So, it is time to say goodbye to this year's events and get ready for the coming year programs. So first of all, I would like to request Dr. Satish Kumar sir, who is the convener of the WSTA, to address the gathering. Satish sir, please.
Respected professors from various parts of the country, parts of the world, in fact, and their delegates, researchers, students, those who are also joined in this gathering. In fact, we come to the close of this international webinar on that we conduct. This is the sixth of that type. We call it as WSTA 2022. And we, in this occasion, first of all, I would like to extend our deep sense of gratitude to each of the well-known great professors, scientists, statisticians, those who researchers who have associated with this program. In fact, they are the success. They are the real success is because of these people, these legendary peoples also there, especially in this group, Professor Malay Ghosh, Professor T.J. Rao, Professor Ashish Sengupta, Professor Bimal Singha. There are a lot of such people are such giants in our subject, the area of statistics and related areas are here. I would like to extend our gratitude to each one of you professors. And on this occasion, we have to we would like to know the response from the delegates. That's the main aim of this function. And also, I would like to say that the certificates of the delegates in various aspects, including the contributory papers, everything all will be uploaded in our conference website within a week time, so that they can download it from there. And we would like to inform you that during December we are trying to organize our international conference on statistics for 21st century during 16 to 19 December 2022. Even though we try to conduct it in a hybrid model, we don't know whether it is, or otherwise it is in the online mode itself this time also. If possible, we shall try our best to think of the other way also. Anyway, once again, thanking you all. I'll just hand over the mic to Dr. Shubha for the further proceedings of this function.
Thank you, sir. As Dr. Satish Kumar rightly pointed out, actually, we are all humbled by your presence, dear professors, and your support and the motivation that you give us by your presence is the energy that drives us forward for conducting more such events. I would like to request some of you to please say a few words of your experience, share with us your experience regarding this four-day journey that we had together. Please.
Oh, this was wonderfully organized. What can I say? I've been attending here actually all 4 days, at least part of it, depending on the schedule. It was very well done. It I mean, you could assemble a whole bunch of scientists from different topics of interest, and it was a big coverage. The coverage was excellent, actually, of topics. So, thank you indeed, from the core of my heart. Thank you.
Thank you so much. Thank you so much.
Thank you, sir. We would really like to hear your opinion. Yeah, please. Please, dear Professor Ashish Sen-Gupta. Please, sir.
Yeah, Satish, I'd like to say something at the end. Is there anyone else who would like to say a few words first? Especially who are from abroad?
If anyone else, please, and Professor Ashish Sen-Gupta to say something at the end. That's
Professor Balaji,
no,
please. So your mic is mute, sir. Your mic is mute.
I would be a bit hesitant to speak something because after the first day, I could not attend any of the sessions during the next 2 days. Only today I could rejoin. So even though it was because the conference was organized in collaboration with the ISPS, I could not participate much. So my apologies for that. Again, I would like to thank Professor Satish for his energy mainly. So I appreciate your energy. You have been sitting for the last 4 days and still you are looking fresh. So on behalf of ISPS, I would like to thank you for involving us also as part of this conference. And I think today, I mean, first day today I could see some of the sessions. Otherwise, everything went on well. And congratulations to Professor Satish and his team for this mega event. So thank you.
Thank you.
Professor.
Yeah, please.
Professor Satish. I'm Dr. Ilangon, Professor of Statistics, Namlai. We are very much thankful to you, Professor, for all. We are listening all your lections, all technical session also. Our scholars also presenting. I really appreciate the effort made by you, Professor, and your colleague. I am ever grateful to you for all your proceedings in this conference. On behalf of the Department of Statistics, Annamalai University, we are ever grateful to you. We are scholars regularly, 11 full-time scholars, along with two Inspire Fellowship, attend all the sections. Important talk also. Thank you very much, Professor Satish. Thank you very much.
Thank you, Professor.
Thank you.
Thank you, sir.
Balakrishnan sir, I know you last time you were fully attended, and this time you mentioned about your inability.
This time, yes, yeah. I was a discreet participant.
Yeah.
I think maybe there's some time
maybe
for Professor Ashish.
I think I should talk now, yeah. So anyway, so I think I am one of the very first person who was involved with this conference from the very first event, right? It's the sixth one in the series. So it has been always a pleasure. It started off mainly as a conference in distribution theory. That's one of the prime areas of your department, Satish. That's how it started off, I remember. We all came in here and we had to give talks on the not only on the conference but a workshop on the distribution theory series of lectures. So those were the initial years of your conference. And finally, I should not say finally, it has evolved into one of the iconic conferences, not only in our distribution theory, it has spread wings to a lot of different areas, and inference and modern data analysis and Bayesian methods and different statistical paradigms. So I wish your conference will now spread It's being higher and higher, and it will go into the modern areas of statistics as we advance. So again, hats off to your energy, to your team, to the way that you have presented this conference in spite of the big hurdles, big constraints the present times that we are facing. Still, you are able to get all the speakers. I did not see any dropouts. So that's a fantastic achievement from all over the world. You could get all of them in. Morada is smiling. We could get him in. So that's a big thing that we could get all the speakers. And that adds to your efforts, adds to the recognition. And I hope you continue for a long, long time. And we hope to see you in the near future. Not in the December. I'm talking about the extension of this conference next year also. And thank you one and all again. Thanks very much.
Surely, Professor, surely. Thank you so much.
Thank you.
Thank you so
dear
much for your.
professors. Actually, your words and your blessings, your wishes matter a lot to us. Now, Satish sir, shall we go to the next important event? Satish sir? Actually, we have got an important announcement to make. Shall we go to that, or Satish sir, please suggest?
Yes.
Okay, so we have got an important announcement to make. That is, we are going to declare the result of the PC Mahalanobis quiz competition, which was a nationwide quiz competition conducted by the Department of Statistics to commemorate the National Statistics Day. I request Dr. Satish Kumar sir to please declare the results.
Yeah. In fact, this is the winners of the national level competition, online quiz competition, in honor of Professor. We call it as Professor PC Mahalanobis national level online quiz competition. And the results, in fact, lot of participants were there. Among them, we have selected the top 12 candidates. The candidates, just I mentioned the name. If they are there in the group, please switch on their video and see to the outdoor. Mr. Tahagata Banerjee from St. Xavier's College, Kolkata. Whether he is in the group?
Yes, sir. I'm here.
Okay, just switch on your video, and
you can put on your video.
Just switch on.
Okay, am I visible?
Yeah.
Thank you, sir.
Yeah. Utkarsha Nishad from University of Lucknow. If she is here in the group, you can open or just to see and switch on the video, and then you can go. No problem. Okay. Vidushi Chauhan, Benares Hindu University.
Vidushi, yeah,
Vidushi Chauhan.
Yes.
Yeah.
Yes.
Hi. Congrats. Congrats.
Thank you.
Mavang Avasti, Lucknow University. Okay.
Yeah.
Pandhere Siddheswar, Srinivasa Pune University, University of Pune. Linu Benny, St. Thomas College, Pali. Elizabeth Joy, Marathanesius College, Kodamangalam.
Yeah, I think she's there, yeah.
Yeah.
Good. Right.
Yeah, congrats. Mr. Pratik Naravade, Pune University, Savitri Pune University.
No.
Sneha Rajiv, Vimela College, Thrissur. Sneha? Anjana Siriak, St. Thomas College, Pali.
No.
Okay. Yadav Pranali Taneji, Yeshwantra Chavan Institute of Science, Shastra, Satara. Maharashtra, yeah.
Yes, sir, present.
Okay.
Yeah.
Good.
Okay. Anne Matthew, St. Teresa's College, MG University. Pavan Hemraj Sapkale from Jalgan. He Mulchi Jeta College. Whether he is there in the group. Okay, congratulations to each one of you.
Yeah, congratulations to all the winners.
All the winners. Your certificates will be uploaded in the conference website and will be sent to you in person. Let us now move to the
so many faces, familiar faces are there. Dr. Jia Sadhugopan is there. Our respected Professor Kalyana Raman sir is there. So I think all your blessings and your wishes, we can conclude the program. Should we, sir? Actually, you are muted, sir.
Let us conclude this session. Okay.
Yeah.
We expect your continued support, blessings.
Yes.
And let us give a good night and goodbye for the time being. Let us rejoin that next time.
So officially, we have come to the end of the 6th International Webinar on Recent Trends in Statistical Theory and Applications 2022, which was conducted in conjunction with the 5th Annual Convention of Statistical Fraternity Kerala in association with the Indian Society for Probability and Statistics, Kerala Statistical Association and Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala. On behalf of the department and on behalf of all the organizers of the program, we wish you all a very, we like to extend our heartfelt thanks to you, our gratitude for your presence, and we hope to see you all again with us. We hope that we will have a more rewarding programs in the future. Thank you all once again, dear professors. Good night.
Thank you. Thank you.